is magnetic silica supported ruthenium nanoparticle, an efficient catalyst for transfer hydrogenation reaction.
Thank you, ma'am. Thank you for your nice introduction.
The speaker can go ahead with their talk.
Ma'am, I don't know how to
Okay.
upload the PPT.
Dr. Shiva, you can see
Shivaga.
the screen on the bottom of your screen.
Okay,
You
ma'am.
have a hand button, raise hand button. Next to that, there is an arrow button. You just click on that.
The present now option is
You have
there.
seen
If you can see the last third button, present now.
bottom part of your
Ma'am,
screen.
share. Ma'am, what can I do?
Pardon?
I will give the share button now.
Yes, you just click on that.
Yes, I
You
give.
can see entire screen, share entire screen. You have opened your presentation, right?
Yes, I open my PPT, ma'am.
Press. Yes, you click on share entire screen.
Ah,
Then you click on that and then share. Click share. You can see the screen on the window, right? So you just click on make it accurate and
ma'am, I don't know, ma'am.
Uh,
okay, please, it's okay. I can tell you and again. Uh, please click on the entire screen you have.
Yes, ma'am, I click.
Now you have seen a screen right there.
Yes, ma'am. Share
You
your entire screen like that on
yeah,
screen.
you just click on that and then click share.
One
Okay, now you open your PPT.
It's coming. It's
PPT.
coming. It's coming.
Yes.
Coming. Coming.
Now you go to full screen.
Ma'am,
Yeah.
viewer, ma'am.
Yeah. PPT done. PPT done.
Yes.
Ma'am, PPT view.
Yeah. Yeah. It's okay. It's okay. It's Adobe, no?
Yes.
Yeah.
PDF. Yes.
Yes,
Full
yes.
Yes.
screen mode, if there is, you do. Otherwise, you just continue. It is as per the chair. I think I will give the mic to the chair.
Okay, ma'am. Thank you
yeah.
for your time. Ma'am, ma'am,
There,
I continue, ma'am.
yes, you can continue.
Okay, thank you, ma'am. Thank you for your nice introduction, ma'am. Today, first, I wish to thank our conference chairpersons and the heads of the conference, other peoples. First, I wish to thank. In this presentation, today I am going to talk about magnetic silica supported ruthenium nanoparticles, an efficient catalyst for transfer hydrogenation reaction. I'm Sivagami, Assistant Professor, Department of Physics, Thiruvallur College, Papanasam. This is for my outline of the talk. Introduction, synthesis technology, experimental work, characterization, and conclusion. In the introduction part, I'm going to give you just a brief introductions about nano and the synthesis methods. Next one is depending upon the structure, properties, and performance of the materials can be changed. It can be analyzed by characterization techniques. And finally, I conclude my results. First, introduction. Nanoscience is the study of fundamental principles of molecules and structures, at least one dimension, sir, roughly 1 to 100 nanometer. At the nanoscale means the fundamental properties are changed. When we reach the nanoscale means everything will change, including colors, melting point, and the chemical properties. The materials of the properties can be defined at the two properties. One is quantum effect. The quantum effect can begin to dominate the behavior of matter, particularly at the lower end, affecting the magnetic and dielectric properties of these materials. Next one is nanosynthesis technology. There are two major approaches to the synthesis of nanoparticles and the fabrications of nanostructures. One is top-down method and another one is bottom-up method. Top-down method is to start with a chunk of material cutting into the nanoscales. But in this method, a lot of defects are there. And the bottom up method is the atom is built by atom by atom or molecule by molecule or a cluster by cluster. In this method, uh, less defect has approached in this top down approach. Next one is experimental technique. In this experimental technique, I will explain the magnetic silica supported ruthenium catalyst. In this synthesis, I take a zero point 0.1 molarity of ferrous sulfate heptahydrate is dissolved in 3 ml of double distilled water. Then ferrous sulfate Fe2SO4 is zero point 0.1 molarity is taken and then dissolved in 50 ml of double distilled water. And these solutions were continuously stirred until homogeneous solutions were obtained. And then the solutions pH were adjusted for 10 using 25% of ammonia solutions. After that, heating this water bath for 50 degrees Celsius for 1 hour. And this reaction mixes was cooled down to room temperature. After that, in the above solutions were added in the tetraethyl orthosilicate was added, and then these mixes were continuously stirred for 17 hours. And then after that, ruthenium trichloride was added. zero point 0.1 molarity of ruthenium trichloride was added, and then the pH was adjusted to 10 using the ammonium hydroxide solutions. After that, these mixes were continuously stirred for 24 hours. Then this magnetic silica supported ruthenium nanoparticles were separated using an external magnet. This magnetic silica supported ruthenium nanoparticles using this external magnet is shown in the image. This is the mixer, and the first one is mixer. After that, this is the separated the mixers using external magnet. Then the particle size were analyzed by using transmission electron microscopy. The estimated average particle size is 22 nanometer using histogram plot. Then the surface area of the iron supported ruthenium nanoparticles was analyzed using Brunner Emmett Teller surface area analyzer. This estimated average sizes surface area is 232 meter squared per gram. Then next one is catalysis part. After the successful preparation and characterization of magnetic silica supported ruthenium nanoparticles, its catalytic activity was examined for transfer hydrogenation reactions with acetophenone were optimized using isopropanol as solvent and KOH as base. Initially, the reaction conditions such as base, solvent, and the reaction temperature were optimized as expected. 22 nanometer of iron ruthenium supported silicon dioxide nanoparticles exhibited a good catalytic activity, and its reusability was checked by reusability test. This catalyst could be easily recovered by magnet using magnetic separation and reused for several cycles without loss of activity. These are my conclusions. We have developed a novel, highly active, stable, and magnetically recyclable catalytic system was developed for the efficient catalyst for transfer hydrogenation reaction. Furthermore, the catalyst can be recovered by a simple magnet and reused without any significant loss of activity. This catalyst exhibited high catalytic activities up to 85% in the reaction. The recycled catalyst were used 6 times until showed the high catalytic efficiency and that good potential catalyst for this industrial applications. These are my references. Thank you.
Thank you so much for your presentation. Now the floor is open for question and answers. If any of the delegates have any questions regarding the presentation or the talk, they can ask it now. the second talk of this technical session. I would like to call upon Supriya Mondal.
Yes, I am here.
Supriya Mondal,
Yes, Supriya Mandal. Yes.
yeah,
Yep.
from Government General Degree College, West Bengal, India. The topic of the talk is observation of photoluminescence Stokes effect photoconductivity in metal ion coordinated graphene oxide. So now you can go ahead with your presentation.
Thank you, Professor Samnandan. Now I start my presentations. Kindly off the presentation of Siva TV seen presenting now. So kindly off this presentation. Is it visible, ma'am?
It is visible. I can see your presentation. You can go ahead with it.
Namaskar. Good morning to everyone. Now, first of all, I want to thank the conference of International Online Conference of Nano Materials ICN 2022 and our the organizer and giving me a lecture on the topic of one of my research work is observation of photoluminescence, Schottky effect, and photoconductivity in metal ion coordinated graphene oxide. So this talk will be divided in five parts on its two-dimensional material, graphene and its derivative, and optical and electrical properties of graphene, and synthesis and characterization of the material, and resultant discussion and conclusions. So what is the two-dimensional material? The two-dimensional materials are the crystalline compound consisting of a single layer atoms, such as graphene, silicon, graphene, and there are two types of two-dimensional material. Number one is the same atom is exist in a particular lattice. Like in graphene, there are all these are the carbon atoms. In silicon, all are the silicon atoms, and in germanium, all are the germanium atoms. And there another type of the two-dimensional material like MX2 type, where M is the transition metal atom like molybdenum, tungsten, and X for the sulfogen atom. And there are also a two-dimensional material is boron magnet. In this lattice, there are two types of atoms are exist within this material. That's why we divided this by two types of material. And after that, what is the graphene? Actually, graphene is a single layer of carbon atoms forming the honeycomb type of lattice. And this type of lattice, the distance between the carbon-carbon bond length of this graphene is 0.142 nanometer. And if we extract the two graphene sheet, then the spacing between these two spacing in the z-axis, the interdisciplinary spacing, it will be the 0.334 nanometer. And the other types of also there are also other types of two-dimensional material like silicon. It's also the hexagonal honeycomb type of lattice structure, but there are some difference with the graphene, like the two atoms of the silicon is exist in a angle that we call in a Mahatma angle. But in graphene, there are the two atoms of the carbon. There are no Mahatma angle exist within this graphene. Like in silicon, the Mahatma angle is 0.44 angstrom, and for the germaniums, is the Mahatma angle is 0.54 angstrom. So what is the optical property of the graphene? Actually, the graphene has a zero band gap semiconductor, zero band gap. Okay, so it's obviously this is zero band gap. That's why it's not a fluorescent material. But so we studied that in reactive calculation there are due to quantum confinement effect we observed, we all the researchers have observed that there exists in a band gap of this of this graphene. So there is a creates an open band gap within this material. And what are the electronic properties of the material of this graphene? The electrical properties of the graphenes are zero overlap centimeter with a high conductivity. The mobility is 150 centimeter square. One inverse and second inverse, because of the both electrons and holes are responsible for their charge carriers. In this material, electrons and holes are moving in a comparatively the same speeds. Most of the electrons exist in the valence band and conduction band and holes on the valence band. We know the holes, comparatively holes are moving in the less velocity than the electron. But and Professor Andregi and Constantine also shows that this is the electrons and holes are comparatively moves the same velocity. And according to the geometrical structure of graphene, each carbon atoms are connected with the three other carbon atoms, and remaining one electron, there is a pi electron is available throughout the two graphene sheet and contribute the electronic conduction. And we also know that graphene has a lots of applications within various fields like solar cell battery, supercapacitor, in LED, chemical sensor, in biological applications, lots of applications we have observed. But our objective of this talk is to overcome the problem of 3-5 or 2-6 hybrid semiconductor compounds and silicon-based nano electronics, and the most commonly used in the current optoelectronic device are replaced by the two-dimensional materials and its derivatives for unique structure of its optical and electronic properties. And optical properties, especially photoemissions being here in the graphenes, are very good due to its zero band gap, but a lot of techniques has been sterilized to achieve the superior optical property in the graphene. A major application of today application such as graphene in optoelectronic device is both in solar cell and lighting limited to only for the transparent conducting coating because of the superior conductivity and high transmittivity. And however, the use of two-dimensional materials are active materials are limited to explore the optoelectronic devices. So the metal coordinate of the graphene oxide is used as an initial material for fabricating the photoconductor, and finally we shows the Schottky diode, the Schottky effect in this material. And the synthesis of this material. First we take the GA solution, and it's simulated for the 3 hours to oil disperse for oil disperse, and after dispersion the GA solution in the GA solution we added the cadmium chloride CdCl2 and ammonia solution and control the pH of 7, and we wash it properly, and we get our material. And this cadmium are coordinated with this graphene oxide. Actually, graphene oxide is the derivative form of the graphene. Oxidation form. There are lots of bonded like CAA, COA, or C1, OH bond, and these bonds are coordinated with the cadmium, and also we use the material for the geogenic, to zinc chloride and the mercury chloride. We have used it for this material and characterized it, and we characterize the FTR and XRD and Raman spectra of this material. And FTR spectra of this sphere 3440, around the 3440, 3409 or 3430 centimeter inverse for the hydroxyl groups, and the nucleus arise in 685, 612 or 632 centimeter inverse for the coordination of zinc, cadmium, mercury with the graphene, and the coordinates exist within this graphene for the and centimeter 3500 to 3000 centimeter inverse will exist within this here. And the 140 or 1422 and 140 centimeter inverse for the oxygen containing functional groups in graphene oxide. And for the vibration, of sp2 hybridization vibration of sisu bond in the plane vibration of the graphene, there exists a peak for the on 639 or on 618 and on 629 centimeters per gram. And excitability, we observe that the 2 theta of this value is 10.13 Armstrong to identify the graphene geozinc or geocadmium and geomercury respectively. And the Raman spectra, we have observed that the Raman spectra shows that for the geo solution in the two bands D band and G band, the D band exists for on 348 centimeter inverse and G band for on 602 centimeter inverse. But we tabulate the form, all the geozinc, geomercury and geocadmium, we tabulated and shows that ID by ID ratio of this all the materials are counted the same, so it's a same type of uniformly distributed within this material. And first we, because we take this material for the UV spectra and shows that there are two peaks exist for the UV spectra of A, the 230 nanometer corresponding to pi s transition, and for 303 nanometer attributed to the n pi s transition of COC bond. And PLP observed and we have measured all the material geocadmium, geomercury and the geozinc for excitation, varying the excitation of this material to 325 to 375 up to 375. So we all measure and we observe that there are three peaks in nearly 410 nanometer and 4 nanometer and 460 nanometer, and these are the which arises because of the restructuring of the sp2 cluster from the coordination of the metal ions with the graphene oxide. And we have also measured the photoluminescence, low temperature photoluminescence property, and we take the first geocadmium. Also, we also measure geozinc and geomercury, but we are not presenting now, and we just measure 300 Kelvin to 77 Kelvin, and we shows is the graph shows that the lowering the temperature, the photoluminescence property are increasing their photoluminescence property, and the luminescence intensity has increased on percentage at 77 Kelvin compared to the intensity of 300 Kelvin temperature. And we also measure the TC species spectra for all this material to their lifetime measurement, and for the geozinc, geocadmium and geomercury, and we shows that compared to the geocadmium shows the maximum lifetime 3.98 nanoseconds. And these are all the photoluminescence property arises, and we study this, and after that we study this material with a different structure and shows that the IV and measure the IV characteristics, current voltage characteristics of this all the material with a different structure of this material. First we take the ITO coated glass and the active material like geocadmium, geozinc and geomercury, and we deposit the aluminum. Then we measure the and measure the device of the current voltage characterization, and we shows that for the geozinc there are it creates some diode-like type structure, but in geocadmium and geozinc we observe that the Schottky type of diode have observed, but in geocadmium we observe that the cutting voltage of the geocadmium is nearly the 1 volt, so it's not so good enough. But in geomercury we observe that the cutting voltage is 0.38 volt, 3 volts. So I think geozinc is normally for that Schottky diode, for the Schottky diode the geozinc is more preferable and not in the geocadmium or the geozinc. So we measure this Schottky effect and the Schottky barrier of it by the equation I0 is equal to A star T square e to the power minus E5 B by KT, where A star and 5B are the effective diode area and the A star is the rejection constant and the 5B is for the Schottky barrier height. And we calculate it for the 5B is equal to KT by Q ln A star T square by and it's all the result in a room temperature. That's why T is 300 Kelvin, and for the geocadmium, 5B is calculated 0.58 electron volt, and 5B is 0.45 electron volt. And I0 is the for reverse saturation current, and we measure from the graph the reverse saturation current 3 e to the power minus 5 ampere, and T is for the 300 Kelvin, and rejection constant is the constant for this all materials 24 centimeter square. Temperature square and ampere. And the device IQ, geocadmium aluminum shows the completely Schottky junction with the higher cutting voltage, and finally the lower cutting voltage is achieved for the device of IQ, mercury and aluminum as achieved. And the schematic diagram of this Schottky effect is a schematic diagram. Actually, the 5B is comparatively greater for the geocadmium. That's why the cutting voltage is increased up to the on voltage. In the geomercury, it's not because the 5B is comparatively less, so that's why the cutting voltage is lower towards the 0.5 volt or 0.38 volt. And we have also measured the photoconductivity of this material, and we observe for the low voltage range up to 0.1 volt, minus 1 volt to 1 volt, and we for the case of Schottky, we have also measured the 0.2 volt or 0.2 volt to 2 volt, and in this case
You've got 1 minute to conclude your talk.
Okay, thank you. And we have observed that the photoconductivity, maximum photoconductivity has changed by illuminating UV light of 365 nanometer, and we have changed that the geocadmium shows the maximum percentage of photoconductivity. And so the conclusion is that the only graphene oxide, graphene we used in such a synthesis technique, and we create a photoluminescent property is a number one equal, and another is that it's also used in a way of Schottky diode effect, and in some cases it also is used as a photoconducting material with for the low voltage up to minus 1 volt to 1 volt. So it's our presentation, and the future perspective is that we have the development of modification of this material and necessary to take use to a more efficient optoelectronic device. Therefore, these materials are good prospect in future and with the device. Thank you. Thank you so much, sir.
Thank you so much for such an interesting talk. Now the floor is open for question and answers if anyone has any questions. So this is the time you can ask questions.
Professor Supriya, thank you for your presentation. It was indeed wonderful. I was just wondering, how did you identify this GOCD, GOAG, and GOZN composites through characterization?
Actually,
apart from, I think IB, it is clear that they are showing distinct curves. But apart from that, are there any techniques?
I have a question. It has been reported that graphene oxide causes some immune cell activation and problems to biological systems. So, are there any studies that are ongoing? Which,
actually, I worked on the optical and electrical properties of this graphene oxide, and there are a lot of, I know there are a lot of disadvantage of it, but actually I know the graphene oxide has a zero band gap. That's why it's obviously it's a poor optical property, and we create in such a way for the low voltage range. We use it as a photoconductor, as also a Schottky diode. Schottky diode for the low, compared with the higher range, we have observed it. And that's our motto to achieve with this material. if I show that the geocadmium is attached by the 8 tier, and we API, the geocadmium is coordinated the 365 nanometer, sorry, centimeter in mass, and it's a 685, 612, and 632 centimeter in mass. Six holes for the coordination, compared to the all coordinations for the geocadmium and mercury.
Okay.
Am
Thank you,
I-
sir.
uh, Thank you, sir.
Professor Supriya, thank you for your wonderful presentation. I
Thank you.
was just wondering how could you identify these three composites of GEO with CD, AG, and are there any characterization techniques you use to identify apart from IV curves which look distinct?
Actually, thank you for your questions. Actually, any material which is coordinated or functionalized it, so we first of all we show the Raman spectra if there are any shifted to the D band and G band, okay, and other is FTR. The if any material coordinate to the virgin material, so it will combine we have observed the differences between with this. So I think API spectra and Raman spectra, and also the XRD also. The peak to orders is in Geo, we observe that the 2 theta compared that toward the 10 degree, 10 degree, but it's shifted to the higher degree. That's why we comfortably confirm that these materials are geocadmium, zinc, and
Okay.
Have you taken the Raman spectra in the lower wave number region, because those are the regions where you get the heavy metals? I mean,
yeah, obviously I have taken it. These are the Raman spectra.
the lower wave number below 1000.
Below?
Below 600.
I think it's now time for our second presentation. So thank you so much, Supriya, for your
Thank you.
presentation, and all of you for your questions who asked the questions. Now I would like to invite the third talk of our technical session. I would like to call upon Prajwal Chetri, Department of Physics, Salesian College, Siliguri, India, and the topic of the talk is simultaneous enhancement of electrical conductivity and magnetization in graphene using silver nanoparticle.
Well, thank you, Professor Subramaniam. And also, I'd like to wish good morning to all the organizers and the participants and the speakers. So, I'd be talking on simultaneous, sorry, just to say this. Is my screen visible?
Not yet. You are sharing the screen, but it is your presentation is not visible.
Is it visible?
No, not yet. I think you need to open your PDF or your PPT and then start presenting the screen. Yeah, now it is visible.
Okay. So I'll be talking on simultaneous enhancement of electrical conductivity and magnetization in graphene using silver nanoparticles. Um, so these are the outlines, introduction, experimental results where I characterize samples using tame ramen, STM, squid, and 4-probe measurements. So this is just a basic introduction about graphene, where my colleague Supriya Mandal has vividly explained. So I will just go swiftly through the slides. I hope my slide is visible and I'm audible.
Yes, your slide is visible.
Thank you, ma'am. Thank you, ma'am. So I mainly worked on graphene oxide, which is a water dispersible form of graphene, and I used Hummer's and Hoffman method to synthesize graphene oxide. And this is just a schematic of how we can disperse graphite oxide using ultrasonication into water to result in the production of graphene oxide. So these are just a schematic of what are the functional groups present over the layers of the graphene oxide, which in turn plays a very pivotal role towards modulating its properties. So these are the merits and demerits of how bulk and the demerits of producing hazardous wastes and insulators. So we need to reduce graphene oxide. The reason behind that is that because we want some material which is functional in nature. Because when we produce or synthesize graphene oxide, it is usually contains a lot of functional groups, which makes it as an insulator, and it hinders its application in various electronics and optoelectronics related applications. It also Reduction allows one to tune its properties. It can either be electrical properties, optical properties, most importantly, and also allows pi-pi interaction with the molecule of interest. So now why I'm referring to pi-pi interaction is because people have used graphene to detect various molecules of interest, like the dye molecules or the TNTs, where pi-pi interaction plays a crucial role in enhancing its detection limit. So this can be either through optical source sensing or through electrochemical sensing, so on and so forth. So these are some of the applications of graphene which I worked on during my PhD. One is the photoluminescence as a fluorescence sensor, and another one as a search sensor. So because of its composite with silver nanoparticles, it provides an immense potential to the graphene structure in terms of detecting molecules of interest either optically or through plasmonically enhanced charge transfer processes. So people have usually used graphene mostly in detecting the molecules, usually in optical detection most often, and very little reports are there pertaining to its electrical properties, its magnetic properties, and most importantly, its atomic scale features. How does it look on an atomic scale? So that is what I have investigated in my work. So this is a schematic of how graphene oxide was synthesized. So we used a hydrothermal route, and where we used plant extract to reduce the graphene oxide. So plant extract can act both as a reduction as well as stabilizing agent. So at the top, we can see here I have written AGX. So here in course of time, you might be seeing 1, 2, 5, 10. Okay, so this just means that X refers to millimolar of silver nitrate used for the synthesis of this AgRGO composite. So silver nanoparticle reduced graphene oxide composite. So this is after a reflux process using hydrothermal route, where you can see there is an obvious change in color from yellow to black, which suggests there is a reduction of graphene. So this is just a demonstration I tried with sodium borohydride in the experiment, and where we can see the precipitates. So this is the beauty of using mild reducing agents. The first is that it does do reduction, and second, the most important is it stabilizes reduced graphene oxide in water. So as you can see here, that it's a very uniformly distributed reduced graphene oxide. Whereas if you use harsh chemicals, it instantly precipitates. So this is one of the advantages. So these are my 10 micrographs where we can see few layers graphene, and as we introduce silver nanoparticles in it, we see clusters of silver nanoparticles whose sizes are of the range between 28 and 32 nanometer. So as we further investigated the size, we saw some asymmetric growth, also prismatic shape, hexagonal shape. So this is usually assisted by graphene oxide, which says the asymmetric growth of the crystal during the reduction process. Excuse me. Another interesting thing that we found was that while we zoomed on the image, we found very, very small patches on the surface of the graphene. And well, this we thought, why this is a silver nanoparticle, and we tried to see whether we can get PL conversion with this, because we doubted that it could be graphene quantum dots as well, because their sizes range between 4 nanometer and 9 nanometer. So this is the size distribution pattern. And then we tried doing the upconversion experiment, where we excited the sample, which is silver AgRGO, with low energy wavelengths, and we got the emission in the high energy wavelength. So this suggested that the graphene quantum dots are definitely present in the sample. So this is as a result of reduction of silver nitrate and graphene oxide simultaneously during the hydrothermal process. So we have also come up with the tentative, proposal for the reaction mechanism, which I'll show up in the later slide. So as you can see, the dashed line, these are all the reduced graphene oxide samples. So we wanted to see whether RG also shows similar patterns. No, it doesn't show. So what it implies is that when you reduce AgNO3 ZO simultaneously, that results in formation of graphene quantum dots in the sample. So these are the Raman spectroscopic analysis. So as you can see from GO, and when you increase, introduce silver nanoparticles, we see that the intensity of the peak is proportionally enhanced. So here I have used 1 millimolar, 2 millimolar, 5 millimolar, and 10 millimolar of silver nitrate to form the AgRGO composites. So as we can see that there is an obvious surface enhancement effect also, surface enhanced Raman scattering. So this surface, what is doing, it's enhancing the D and G bands of graphene, as well as some of the new bands we could observe in between 300 and 600 centimeter inverse. And this is actually attributed to manganese derivatives, because when we synthesize graphene oxide, we use manganese, potassium permanganate. So some traces of manganese is always there in graphene oxide. So these are usually people detect this by using NMR techniques, because these are present in traces. But through our experiment, we proved that by using source spectra also, we can probe defects, structural defects in graphene, as well as if the contaminants are sensitive to vibrational spectroscopy, they can also be detected via source spectroscopy. So these are the manganese derivatives present in the graphene. All these new peaks that we see here at the edges of the D and the G band, they correspond to functional group related defects in graphene. So these are the signatures. So we have used the fit, the Lorentzian fit, and we have attributed each of these curves to the defects, sp2, sp3 defects, all this, and the functional groups, or even the functional groups like hydroxyl, carboxyl, carbonyl, which are only detected through FTIR spectra, can also be probed if source enhancement is substantially achieved in graphene. So as we have also seen this delta CAG-C vibration. So Raman spectroscopy also proved that some kind of a bonding is there between Ag and C carbon of the graphene. So this is the tentative mechanism. So when we reduce silver nitrate with graphene oxide, it results in the release of nitric acid in the solution, and this nitric acid in turn oxidizes again graphene, resulting in the formation of COC bonds. When these COC bonds, as we can see here with the red line, are present in excess, it induces structural strain in graphene, as a result of which they get detached from the parent structure, resulting in the formation of graphene quantum dots. So these are the scanning tunneling images. So this have been taken by indigenously built Quasar technologies, which is based in New Delhi. So this has been measured, used by the indigenously built characterization tool. So these are all done under where there was no vacuum condition and temperature at the normal room temperature. So as we can see on figure A, this is the HOPG, that means which is highly oriented pyrolytic graphite, over which we deposited reduced graphene oxide and we took their scans. So we can see that there is a distinct feature with the of the reduced graphene oxide and AgRGO, where we can see the flat HOPG background. So these are the 1 micron, 512 nanometer large area scans, and we also did the so these regions represent highly oxidized regions, and this is the atomic scale morphology. So on figure A, it is the image of HOPG, where the interlayers of the interatomic spacing was observed to be 2.46, which is for a perfectly periodic atomic lattice. So in case of RGO, because of surface roughness and also presence of the functional groups, we although saw the periodicity, but only for a small region. And here the interatomic spacing was found to be 2.34 angstrom. Similarly, we also did for AG1 RGO. So that means when 1 millimolar of silver nitrate is used to reduce graphene oxide to form AG1 RGO composite, this would be its impact on the atomic scale morphology. So here we can see there is a drastic shift. So here the interatomic spacing is 2.35 angstrom. Here we can see it's a drastic 4.2 angstrom. So all this indicated that there is certainly some structural strain induced in graphene, and also the breakage of the CC bonds might be present. In addition, we also saw the lattice defects such as the vacancies, as you can see here, and also the lattice mismatch. So all these defects and the properties of the graphene encouraged us to do some measurements using speed magnetometry. And here we found that the graphene oxide, whose MS value or the saturation magnetization is least, and reduced graphene oxide MS, the saturation magnetization increases in a very incrementally. So we see that when you reduce graphene oxide, there are generation of paramagnetic centers in them because of the reduction, because we are removing the functional groups. As soon as we introduce silver nanoparticles in it, we can see a sharp increase in the saturation magnetization of graphene. So this is for AG1 RGO. So AG 0.5 RGO, it is this, and AG1 RGO, there is a sharp magnetization. But this trend is not continuous, because as soon as we increase by 2 millimolar, which is AG2 RGO, it again decreases. There is a decreasing trend. So apart from enhancing the magnetization, the increase in AgNP concentration of a graphene is also somehow decreasing its MS value because of creation of carboxylic functional groups in the sample. So when COC bond is formed over the surface of the graphene, what it does is that it cancels the net magnetic moment of sublattices A and B. So when this COC bonds or the groups are present in excess, it reduces the saturation magnetization. And also we found, once we zoomed this image, we found that there is a hysteresis present in the sample, which are attributed to the long range magnetic ordering. And this is present because of the clusters of OH which are present in the graphene oxide, or sorry, AgRG. So we fitted the MH curve using the modified Brillouin function. Usually people fit by Brillouin function where paramagnetism is observed, but our fit were more accurate with modified Brillouin function, wherein here we introduce the H, we replace H by gamma H minus C. So this type of equations are used where long range magnetic ordering exists in the sample. So the chi-square fit was found to be best with this equation. So therefore, we can also conclude from this that there exists some kind of long range magnetic ordering in the sample. So fit converges for J value equal to 3. So this is the chi-T fit, where we found that the samples are GO and RGO samples are diamagnetic in nature, weakly diamagnetic in nature. And as soon as we dope with or introduce AgNP, they becomes paramagnetic. We can also see its paramagnetic nature by the.
Okay, 1 minute to conclude your
Okay,
talk.
thank you, ma'am. Thank you. Yeah. So this is the IV curve. So here we can see if as soon as we reduce GO from insulating, it becomes ohmic in nature. As soon as we introduce silver nanoparticles, we can see a sharp increase in the current value. So with the introduction of AgNP, the resistance decreases 400 times as compared to RGO. So whereas in papers it's reported only 15 to 174 times. So here we also, so this is for AG2 and AG10 RGO. So there is a competitive effect here. So with the increase in AgNP, we cannot see a proportional increase in the conductivity. Why? Because with AgNP, when you increase it, there is a drawback also, because you will be essentially creating defects. So these are my conclusion. So we concluded that simultaneous enhancement of both magnetization and electrical conductivity can be achieved in graphene. Okay, and this work can be further done by using different nanoparticles and checked with different concentrations. And it provides a feasibility to fabricate composites, which might find promising applications in spintronics and memory-based devices. So, and my acknowledgements. to my supervisor and to all the affiliations that I had in my past. Thank you.
Thank you so much for such an interesting talk. Now the floor is open for question and answers. If anyone has any questions, they can ask it now.
Sir, it was a wonderful presentation. So, can you explain the significance of preparation methods for the graphene using silver nanoparticles?
Can you please repeat? It is I'm not hearing properly. Yes.
Significance of preparation methods for the graphene using silver nanoparticles.
Okay, you're asking about the preparation steps.
Yes, yes, sir.
Oh, okay, okay. So it is just let me just go to the beginning. Yeah, here so we used so we use the geo solution and we make some concentration of silver nitrate with the distilled water, double distilled water, and then we add some amount to this geo solution. Over it, we usually use aqueous extract of plant leaves, which are of course rich in phytomolecules, and we put that extract all together, stir it for a while to make a homogeneity, and then we put it on a reflux bath. So here there's a boiling water and it gets heated, and after 3-4 hours, the color changes. So which suggests that it is reduced.
Thank you, sir.
Thank you.
Excuse me, sir. Thank you so much for the informative presentation. I am Somberanjan from Akita University, Japan. As you explained about this material, we can use this in spintronic application. So did you study about the anisotropy property of this material?
Sorry, for the further I did not do this study. This was my last
Okay.
work after my PhD. So maybe if I find labs in the days to come, I would be continuing.
Okay. So any comment on the coercivity? Did you find the coercivity of the material?
Yes, coercivity is very, very less, although not promising like the ferromagnetic materials. But yes, of course, long range. So we are not claiming this to be ferromagnetic also, to be on the safer side, because coercivity is less. But although yes, we do see hysteresis. So this is because of the coupling of the defects clusters in the graphene and magnetic anisotropy also. Yeah, magnetic anisotropy we have attributed, but we didn't do the detailed study.
Okay. Thank you so much, sir.
Yes.
Dr.
Thank you.
Chetri,
Ma'am.
could you please let us know what is the name of the STM instrument you have used for the imaging?
Yes, I would proudly say because it is made in Delhi and I'm very
Okay.
much closely associated with them. Maybe I will type it here, STM, and I will send the website address also.
Okay, thank you.
They are currently making atomic force microscope at all these high-end instruments which we usually import from outside countries. No? They are like trying to build it here in India. So I'll send the
Okay,
website details, gas
okay,
chromatography, everything. Yes.
okay, thank you.
Yeah.
So thank you so much, Prajwal. It was a really interesting talk. And now we'd like to invite the last talk of our technical session. Uh, Prathasarthi Srinivasan, Department of Electronics and Communication Engineering, Amrita School of Engineering, Chennai, Amrita Vishwa Vidyapeetham, India. And the topic of the talk is an insight into metal-free and ruthenium quantum dots, decorated 2D graphitic carbon nitrides towards sensing of ethanol and 3-methyl 1-butanol species.
Yeah, yeah. Very good morning to everyone present here, and thank you very much for the introduction, ma'am. So let me start the presentation of. Let me start the presentation in a while. Yes. So whether my screen is visible, ma'am?
Yeah, yes, your screen is
Yes,
visible and
yes.
you're audible.
Yes. Very good morning to everyone present here. Myself, Dr. Parthasarathi Srinivasan from Amrita School of Engineering, Amrita Vishwavidyapitham, Chennai campus. And I'm very happy to deliver a talk over this ICN 2022 conference, and I'm really happy to be a part of this conference. So before going to the today's talk, so let me introduce the works which we are carrying out in our laboratory, what we are working on in a brief way, and then let me go to the today's peculiar topic on metal-free and ruthenium quantum dots decorated 2D graphitic carbon nitrides for sensing of ethanol and 3-methyl-1-butanol species. So in general, what we are working on is that we are working on nanostructured sensors for environmental, healthcare, and food quality applications. So as far as the healthcare application is concerned, we are working on developing a nanostructure-based sensors, especially for detecting the what do you call the exhale breathe biomarkers. The trend nowadays for early diagnosis of diseases is through exhale breathe analysis. So we are we are developing a sensors for developing exhale breathe analysis. So that is a one part on the healthcare application. And similarly, for food quality applications, we are developing a series of sensors to capture the volatiles which is coming out from the food samples once it get deteriorated. And as far as the environmental monitoring application is concerned, we are developing again a sensors which could be able to detect the heavy metal ions and chemical residues in water samples. And of course, for an environmental application, we are developing some chemical sensors. So this is an overview of what we are doing. And for the next 2 to 3 slides, I just giving the deep insight of what we have developed so far, and then let me go to the today's talk. So as I said, we are working on healthcare application. So the first one here I have shown is the work which we have did for identifying the urinary tract infection, that is UTI. That is an early diagnosis of UTI using the photoluminescence based biosensor, right? So that is the major principle of the sensing is is based on the photoluminescence principle, where we targeted the quorum sensing signal called as acyl homoserine lactone that is actually present in the human body. So those who are infected with the UTI are prone to have this biosense, the quorum sensing signal. So our proposed work is that we could be able to probe these molecules even in a little concentration, so that according to the calibration in concentration, we could be able to tell that whether the patient is having this UTI or not. On the other side, for the healthcare application, we have developed also the different materials. We have tried with what you call the heterostructure based material for developing a breath sensor. Towards that, we have made UV activated ZNO and CDO based isotype heterostructure for sensing of breath volatiles, especially acetone sensor for the early detection of diabetic ketoacidosis. So this is a small insight where we are working on. And similarly for the food quality application, so from the materials to device fabrication. So we are focusing on materials to device fabrication. Now we are just making from the nanomaterials, how we are developing a sensor, and finally how we are making it as a complete model using a prototype, and how we are integrating the IoT into that, and all these things which we are working on. So the first one which we have developed is for electronic nose. So it is like an artificial nose which we have developed for smelling the biomarker which is being released once the seafood is being deteriorated. This work is particularly we have did it for seafood sample. So we have filed the patent also for this particular work, where we have developed a complete model and a prototype, and soon it will be commercialized also. And as far as the food quality application, another application is concerned, where we are working on electrochemical based biosensors for identifying the formalin levels in fishes. So in general, we know that in a real-time scenario, the formalin content in the formalin content has been used to preserve the seafood items. But the very pathetic situation is that they are not using it in the allowed level. So here we have proposed an electrochemical based formalin biosensor, and we observed an interesting observation that it is exhibiting a comparator effect. So this is a novel approach we have made for probing this formalin levels in seafood, especially for fisher samples. So as far as the environmental application is concerned, here I have highlighted only a few work, but I know we have done a series of works which we are working on now. And this one is on alpha MOO3 nanorods. Again, we have investigated the material based on the metal oxide to probe the volatile organic compound which is present in the real-time atmosphere. So this particular work we prone to we have selectively sensed the trimethylamine molecule, and we have extensively studied all the selectivity studies, the transient studies, and we have observed the sensor is just showing excellent sensing towards the TMA. And based upon the different profiles, say how the grain features of the nanostructured material and the activation energy, especially the intergranular activation energy, and the surface defects of the material, how it is tuning the sensing response. So all these things we have studied in the case of environmental pollution monitoring. And the right hand side I have shown you the electrochemical. Again, it's an electrochemical probing of hydrogen peroxide molecule which is there in the river water. So this work we have based with reference to our collaboration. So we did this work in Kaname river water, Japan, where we took the river water sample and we have tested for the hydrogen peroxide residues in the water bodies. Here the novel property of the the sensor which we are proposing is that we have used ternary nano interface. So this is for the first time we have introduced titanium oxide, zirconium oxide, and hafnium oxide based material for identifying the chemical residues which is present in the water bodies. So with this background, these are all the various works which we are working on in our as a team. So this is with this background now let me enter into the today's talk on peculiarly on investigation of carbon nitride based material for probing ethanol and 3-methyl 1-butanol molecules. So with all this work, we majoritarily uses metal oxide based material. But when you come for a real-time, sensing analysis, this metal oxide material will be, will have a certain drawback, which is the influence of relative humidity. So for that, the initial spark where we have developed the sensors for ammonia detection at room temperature using heptazine based microporous organic polymer. So that is the first point where we started exploring the 2D material, especially on porous organic polymers, where we this investigation was done in the year of 2018, where we observed an interesting observation that is, in general, as I told, the chemoresistive sensors, whatever we are developing at the room temperature, the major influencing parameter is the influence of relative humidity. I can say the relative humidity can suppress the overall sensing response of the system. So we should develop a sensor which should have the anti-humidity nature. So this is what in our mind, and when we are investigate this particular material, heptazine-based microporous polymer, to our surprise, the material not only possesses the anti-humidity nature, but also it possesses, humidity favorable sensing response, what you call it as animal chemoreceptor. So with reference to that, we have started exploring the mechanism how the material is exhibiting animal chemoreceptor, and we can found that it is because of solvation-assisted catalytic effect, the mechanism which I have projected over here. So this is what actually we have observed in that particular material. Actually, this is an initial point where we want to test many 2D materials, especially here the heptazine-based moiety. Since the material is having heptazine-based moiety, the interaction property has been extremely changed, so that is extremely favorable towards us. So we just want to explore many materials based on heptazine based moiety. So we are in the search of a different material where by the time we started searching for the material, those who are representing either heptazine or a triazine based functionality, so that it would be able to not only be able to make an anti-humidity nature, but also able to make animal chemoreceptor. So toward this research, we found that carbon nitride is being an suitable candidate for a chemoreceptive sensing owing to different properties as I have listed over here, that is on hybridization, stability, biocompatibility, and especially on exchangeable NH groups. And since I mentioned here already, it is representing heptazine and triazine functional bonds, we feel that this particular material could be an novel material for a next generation sensing elements. So toward this, we have started exploring different possibility of modifying its surface, and we want to explore the sensing property. So toward this, with this background only, now I'm going to deliver this talk on the initial two works which we have developed based on the carbon nitride and ruthenium modified carbon nitride. So initially we have taken a carbon nitride material, that is, we have directly made a thermal polymerization of cyanamide. With reference to the thermal polymerization of cyanamide, we have developed a carbon nitride nanosheets, and we found that it is actually a mesoporous in nature, and it shows large surface area. When compared to the literature, we found that this material shows a very large surface area, and to our surprise, it is showing excellent sensing characteristic to ethanol at room temperature. And as long as we observed this behavior, then we have moved to ruthenium quantum dots decorated graphitic carbon nitride. So we want to explore what happens if we surface modify the material with ruthenium, and we want to test what happens to the sensing property. So this is why we have tested with the ruthenium quantum dots also, and we have found an interesting observation here in the case of both the mesoporous as well as ruthenium quantum dots. As far as the mesoporous carbon nitride is concerned, we observed a self-protonation mechanism in sensing the ethanol species. On the other hand, the transition has happened. The conductivity has been changed from P-type to N-type when you just surface modify the ruthenium species onto the carbon nitride. So this is what actually we have observed, and of course the results which we are going to discuss in the next 2 to 3 slides, and then I'll be finishing the talk. So this is actually on the nano sheets. So this is a meso nano sheet where we have observed as the morphological studies projected here. You see it is displaying the 2D lamellar structure. So it is actually representing a 2D lamellar structure having surface exfoliated carbon nitride sheet, where we started testing this particular material towards the different target gases, and we found that it is highly selective towards ethanol, and this is because of the this is because of the active interaction of ethanol species and also higher inductive effect of the ethanol compared to the other alcoholic species. So we found that this material is highly selective towards ethanol. To cross-verify that, the selectivity factor has been calculated, that is with reference to the interferent environment, and we found that this particular sensor showed excellent sensing characteristics towards ethanol even in the interferent environment also. And here the noteworthy point is that we could say the largest surface area. So this is the first time we have observed this particular surface area with this particular material when compared to the literature, and this particularly in turn makes the ethanol molecules to penetrate into it's make a percolation path for the ethanol molecules to come and interact on the surface and which would have reflected in the better sensing characteristics as you observed in the graphs. And here the limit of detection was observed to be 500 ppb. Even we could able to detect the ethanol species at a lower concentration. Even we can say it is a sub ppb levels with the transient times of 34 and 30 seconds. That is less than a half a minute, right? So it is around it is approximately a half a minute we could able to detect the ethanol species which is there in the lower concentration concentration at even sub-ppm level. So this is what the observation. And as I mentioned here, we observed this mechanism. So here I have shown you, it's a self-protonation mechanism. So what happens? So this particular material is behaving like a p-type material or a p-type conductivity. Right, so we just exploring this material towards an normal atmosphere. It actually accepts the electron, it captures the electron acceptors, and it further make the surface to be more protonated.
You
Right?
got 1 minute to conclude your talk.
Yeah, fine. Yes. So it is more protonated. And of course, so when the target gases is interacting, you see there is a steep increase in the surface resistance. That means that, the targeted species and the type of interaction is happening because of the decrement in the p-type charge carriers which was presented in the atmosphere. And, because of this electron hole recombination, we could observe this trend. And when we include this ruthenium quantum dot, when you surface modify this ruthenium quantum dot, we could observe that the entire shifting of selectivity towards 3-methyl-1-butanol, which is all otherwise called as isoamide alcohol. So that is initially when the mesoporous carbon nitride showing greater sensing response to ethanol, and once the ruthenium quantum dots is being modified here with the surface, we could see the transition in the selectivity and all the other transient selectivity plots. It implies that the sensor showed good sensing figure of merits with the limit of detection of 1 ppm. And of course, here also the sensor response and recovery times falls within half a minute. So this, such a fast transient profile would be highly required if you want to develop a breath sensor, especially to identify the, identifying the diseases at the earlier stages. This would be, optimal material to fabricate the sensor. And the mechanism, again, just not more than 15 seconds, I will explain the same thing. So the mechanism, whatever I said in the case of meso GCN, there we observe the self-protonation mechanism since the material exhibit to be a p-type material. And once you once you surface modified it with ruthenium quantum dot, the surface is completely changed to p-type to n-type behavior. And this is a band diagram model. We know the concept. So under before the contact, it is isolated bands of both the material has been displayed, and after the making an electrical contact, there because of the transfer of electrons from the 3-methyl-1-butanol, the electrons are being accumulated at the conduction band of the material, and this overall progressing the surface adsorbed chemisorbed species, that is O2 minus, and because of this we could observe better sensing characteristics towards 3-methyl-1-butanol. So to conclude here, so generally this material, whatever the material we are investigating, it should expose the anti-humidity reaction, and for an especially for an healthcare application if you want to develop a sensor. And we found that this particular material is exhibiting all the characteristics, so it is a possibility of developing a complete model using this particular sensor. And I'm thanking you once again for the opportunity given. Thank you so much.
Thank you so much. Now I would now the floor is open for question and answers. If anyone has any questions, they can ask it now. Okay, so I think there are no questions. So as we come to the end of the first session of the day, I hope that the presentations and the deliberations by the invited speaker have given some points to the delegates and attendees to ponder upon and enhance their research interest, and also expand their research fields in the area of hybrid materials. Once again, I take this opportunity to thank all the speakers for their presentations and the delegates who attended this session. Thank you, one and all. Thank you so much.
I express my sincere gratitude to Dr. Shabnam Ban for chairing the session. Let's give a big applause to our chairperson for the excellent sharing. I extend my thanks to the speakers for the wonderful presentation. Dr. Shabnam Dan, can you please continue the sharing? Because the next chairs are not present.
Okay,
And
sure.
because
I do that, but the first presentation is mine. Like, do I invite myself and give the presentation? That is okay for me if I do that. Okay, so yeah, so
I think Dr.
yeah, you
Siko
can
George
invite me.
chairing the session.
Hello, am I audible?
Yes.
Thank you. Welcome to the second session. We are continuing session named as nanoparticles, and the first session is from Dr. Shabnam Dan. Dr. Shabnam, are you present?
Yes.
Yes, Professor Shabdan Nan is from Department of Chemistry from University of Agriculture Technology Science, Uttar Pradesh. So if you are ready with the presentation, you can load the presentation.
Yes, I am. Is my presentation visible and am I audible?
Yes.
Okay, thank you. So, good morning, everyone. I am Dr. Shabnam Dan, Assistant Professor, Department of Chemistry from Sam Higginbotham University of Agriculture, Technology and Science, Prayagraj, Uttar Pradesh, India. I am here to present a part of my research work entitled A Comparative Study on the Effect of Modifiers on Magnetic Properties of Manganese Ferrite Nanoparticles. So, as we all know, that nanoparticles are a wide class of materials that include the particulate substances which have one dimension less than 100 nanometer. Among nanoparticle, magnetic nanoparticles have gained enormous attention owing to its wide application in various fields such as medical application, therapeutics, targeted drug delivery as catalyst, magnetic data storage, and as nanoadsorbents. So therefore, the question arises that why there is a need to modify the surface of a nanoparticle. Because of the large surface to volume ratio, they exhibit high surface energy. Therefore, it is necessary to surface modify nanoparticles. So the method that was adopted to synthesize manganese ferrite nanoparticle was chemical co-precipitation method. This method was adopted because of the facileness and convenient approach. And the advantage of the method is the high yield and high product purity. So, for this purpose, we took for the synthesis of manganese ferrite nanoparticle, a mixture of manganese sulfate and ferrous sulfate was taken, and the solution was subjected to magnetic stirring, and uh, s- uh, sodium hydroxide was added dropwise until a pH of 14 was reached. The solution was stirred at 80 degrees Celsius for an hour, and then the solution was cooled and left for aging. The solution was washed with distilled water and ethanol and was later centrifuged and dried overnight in an oven. The similar for surface modification, six combination of modifiers were taken. The very first one was a zwitterionic surfactant, that is uh, N-dodecyl and N-dimethyl amino butyrate, that is DDMAP. The second coating was an acrylic polymer polymethyl methacrylate, that is PMMA. The third coating was polyethylene glycol, that is PEG 200. The fourth coating was a combination of the polymers PMMA and PEG 200, and the last coating was was the combination of the surfactant along with the block copolymers, that is GDMAB, PMMA, and PEG. The synthesis method is the same as we discussed for manganese ferrite nanoparticle. It's just that in the second step, the DD-MAP surfactant was added. Similarly, in the second step, the modifiers were added in all the processes. Then for characterizing, uh, in order to characterize and validate the modification of the nanoparticles, uh, different analytical techniques were used. The very first one being DLS and TEM for size distribution and morphology, FTIR for surface functionalization, XRD to determine the crystal structure, TGA and DTA for thermal to determine the thermal stability of the synthesized nanoparticles, SEM for surface morphology information, and VSM to determine the magnetic property. Moving on to the result and discussion, the very first thing that was done after the synthesis was to calculate the percentage yield. It was observed that the manganese ferrite nanoparticle showed the highest yield, that was 80.65%, followed amongst the modified nanoparticle. DD-MAP, PMMA, and PEG modified nanoparticles showed the highest yield of 75.86%, followed by DD-MAP modified manganese ferrite nanoparticle 0.82 nanoparticle, and the least yield was seen in PEG modified nanoparticle. Then coming on, in order to determine the size of the synthesized nanoparticle, DLS and TEM and techniques were used. DLS basically determines the hydrodynamic size, and TEM determines the particle size of a nanoparticle in the dry states. So it was observed that manganese ferrite nanoparticle, it exhibited a particle size of 66.13 nanometer, whereas DD-MAP modified manganese ferrite nanoparticles showed a narrow nano size range of 11.51 nanometer, followed by PMMA with 11.12 nanometer, followed by PEG that was 47.98, and followed by PMMA and PEG that was 70 nanometer and 20 nanometer for the last combination. These are the TEM images that we already discussed of the samples, and these are the size histogram of generated by PSA. Now moving on to elucidate the magnetic character of the synthesized magnetic nanoparticle, VSM studies were performed to determine the following, to determine the magnetic properties given as magnetic saturation, that is MS, remnant magnetization, that is MR, coercivity, that is OE, and HC, and magnetic moment, that is MUB. So here in this case, manganese ferrite nanoparticle would act as a reference, and the saturation magnetization that was observed for manganese ferrite nanoparticle, that was 23 EMU per gram, and the coercivity was 71.25, and its corresponding magnetic moment was calculated to be 0.229 Bohr magneton. So starting with the very first combination of modification, incorporation of a zwitterionic surfactant, DD-MAP, leads to a dramatic reduction in the value of MS, a decrease of 86% in the value of magnetic saturation, and an equal decrease of 86% in the value of coercivity can be ascribed to a magnetically dead layer of the surfactant on the surface of the manganese ferrite nanoparticle. The surfactant layer influences the interaction between core and surface spins of particle-particle association and constrains the magnetic moment alignment under the applied magnetic field. On the other hand, the second combination, the embodiment of PMMA on manganese ferrite nanoparticle leads to a moderate reduction in the value of magnetic saturation, a 37% decrease. A 37% decrease of MS value was observed, and an upsurge of 26% in the value of coercivity was observed. This could be comprehended in terms of the interchange with the non-magnetic layer of PMMA and the impact of the nano-sized character of the ferrite magnetic domains. Then again, moving on to the PEG modified nanoparticle, PEG on being used for surface modification of manganese ferrite nanoparticle caused a downturn in the value of magnetic saturation, connoting a 24% decrease and a drastic increase of 31% in the value of coercivity. This increase in coercivity could be due to the two reasons. The first being increase in the value of coercivity associated with the single domain size. The second being random orientation of the crystal structure. Then moving on to the next coating, that was PMMA and PEG. The effect of incorporating block copolymer PMMA and PEG on the manganese ferrite nanoparticle was evaluated, and a drastic decrease of 99% in the magnetic saturation value was observed. In a similar fashion, a drastic decrease of about 73% in the value of coercivity was also observed. This downturn is due to the increasing polymer chain length, which is attributed to the reduced effective weight fraction of the magnetic core. So the field therefore the last coating, that was the last modification that was seen, was of DD-MAP, PMMA, and PEG combination of the surfactant and the polymer. It was observed that there was no significant change in the MS value. This is attributed to the fact that, considering the shell volume and its density versus magnetic core, so it was observed that the shell volume and its density versus the magnetic coat, it can be inferred that the mass of the non-magnetic coating is near to about 2.57%. So this was about the magnetic properties that were evaluated. Now moving on to the next slide. I think it is not moving. Just a second. Just a sec. Yeah. So sorry for the interruption. Actually, the slides were not moving. I hope it is now moving. Okay. So these are the VSM MH curves for all the synthesized modified and unmodified nanoparticle. Moving on, the XRD analysis was used to determine the crystal structure of the synthesized nanoparticle. Since VSM slides showed the best magnetic properties of PEG modified nanoparticle, therefore this particular slide, the different diffraction pattern confirms the formation of single phase cubic spinel structure for both bare and for both bare and peg modified nanoparticle and as well as the other modified nanoparticles. The sharp and narrow peaks of the modified nanoparticle uh, are indicative of higher crystallinity of the modified nanoparticle. Uh, uh, according according to the Sherrod method, the crystallite size and lattice parameters were calculated, and as these the data were matched with the JCPDS cards, and accordingly their crystal structure and space groups were determined. It was found that the crystal structure of all the synthesized nanoparticle were cubic, and the space group of all the synthesized nanoparticle were the same. Only for the PMMA modified nanoparticle, it was FMCM.
Sorry to interrupt. You have to conclude within 2 more minutes.
1 minute?
No, 3 more minutes.
Okay. 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 So, moving on. So I'll just conclude soon, really fast. So the FTI spectra also validated the modification of manganese ferrite nanoparticle with all the modifiers, and these are the SEM images of the synthesized nanoparticle. It is evident from the SEM micrographs that the synthesized manganese ferrite nanoparticles are distinctly agglomerated. These images shows that the surface of the sphere is more moderately smooth with high degree of agglomeration. On comparing the micrographs of manganese ferrite nanoparticles and the modified nanoparticles, it is evident that the interaction between the surface of the metal ion and the prevalent groups in the modifiers on the surface of the manganese ferrite. The micrographs also illustrate the formation of images as spheres embedded on it. Then TGA analysis was used to determine the thermal stability of the synthesized nanoparticle. All the thermograms obtained in the study validate the formation of manganese ferrite nanoparticle and also verified the surface modification by the respective modifiers on the manganese ferrite. The percentage loss was also very much obvious on studying the curve, and it also demonstrated the volatile matter present in the samples. And on observing the DTA curves, it was evident that the transition was exothermic. So with this, I would like to conclude. In the present, in the work presented, the synthesis and characterization of the composite nanoparticles composed of magnetic core, which were further modified with polymeric and surfactant coating, was evaluated. The synthesized nanoparticles were suitable for various magnetic applications, which will be discussed in the future prospect section. The effect of modifiers by by DD-MAP, PMA, and PEG on the magnetic property was evaluated. It was concluded that a mild decrease was observed in all the coatings except for the combination like DD-MAP, PMMA, and PEG. It was observed that there was no decrease in the magnetic properties was found. Only in the case of PMMA and PEG modified nanoparticle, the magnetic behavior changed from ferromagnetic to paramagnetic due to increasing polymer chain length, which is attributed to the reduced effective weight fraction of the magnetic core. Then in future prospects, the synthesized nanoparticle can be used as nanoadsorbents, which I have already performed in my elaborate research work. It was successfully, the PEG modified nanoparticles were successfully used as nanoadsorbent for the removal of chromium 6 from wastewater. Then it can also be used as electrochemical biosensors and antimicrobial and antifungal agents, catalyst, contrast agents. Their application can also be explored in the biomedical therapeutics and drug delivery due to their ability to hold the poorly soluble drugs in its hydrophobic cavity, resulting in the targeted drug release. Thank you so much.
Dr. Shabnam Dan, excellent presentation. Thank you very much. And I would like some queries from the audience.
Hello, ma'am. Hello.
Yes, yes.
Yes, ma'am. I'm myself, Dr. Mofia Ghosh, ma'am. Ma'am, excellent presentation, first of all. Ma'am, I have one question. If the polymer like polyethylene glycol are coated onto the surface of the magnetic nanocomposite, and then we want to conjugate the drug onto the, or intercalate the drug onto the polymer surface, then can it be possible for the, in this case,
Yes.
for
Yes, actually, I am currently writing a paper which talks about the same thing, that PMMA, because of its hydrophobic nature, it can, hold the drug in its cavity, and really it can be used in the targeted drug delivery. So therefore, the PMMA and PEG modified nanoparticles, since it is paramagnetic, so it can be successfully used in this targeted drug delivery.
Okay, ma'am. Thank you, ma'am. Thank you.
Yes, thank you so much for your question.
Thank you, Dr. Dan.
Thank
We
you.
are moving to the next presenter. Next presenter is Dr. Sujay Sarkar from Chemistry School of Advanced Science, Laboratories. Dr. Sujay, are you there?
Yes, sir. Yes, sir. I'm here.
Thank you. You can start presentation, and you are having 20 minutes time, 18 for presentation and 2 minutes for discussion. Thank you.
Sure, sir. Is it visible?
Yeah, it's coming. Can you put in the slideshow mode?
Yeah, is it? Is it okay?
Right. Yes, please go.
Okay. Yeah. Good morning and thank you. Thank you for your introduction. Yes. Today I'm going to present that the investigation of the single nanoparticle photocatalyst using this scanning photoelectrochemical microscope. Okay, it's a new it's a term, it's a new thing that this electrochemical microscopy using this the scanning mode, and of course in presence of this photo, and we are starting the single nanoparticle. So now actually we'll just give a brief introduction that why do we need the single particle single nanoparticle investigate using this method. So just I hope that everybody remember that just this climate change conference in UK 2021 actually that made clear that the world is ready for the green hydrogen, because our fossil fuel is now going to over within this maybe within 100 years or something like that. So we have to look for another alternative, and that is the green hydrogen. And we know that in our nature already that sunlight using the photosynthesis method, already we are doing this water splitting and getting this oxygen and hydrogen. That hydrogen can be used with this carbon dioxide and nitrogen and get the liquid fuels and this one. But our aim is to use this hydrogen and oxygen and to make the fuel cell. Why that fuel cell? Because the fuel cell is only device which is the environmental benign, because the byproduct is the water, and if you use that in the proper catalyst, that hydrogen and oxygen that bind and make the water, and you will get the electricity, and the efficiency of this the 40 to 60% efficiency. Okay, so that's why this is a high demand on this one to the alternative energy source or as a form of the fuel cell. Yeah, here I'll show you that what's actually going on. Previously the industrial gas and special application was there and based on there's a fossil fuels are using, but currently we are slowly moving to the fuel cell, because the fuel cell in this home or the fuel cell devices actually launched in the market in the 2014. Of course, it's not that spread out as actually we expected, but it's not. But actually, future is going to this the fuel cell device. And what's the problem? Why is actually not going that spread like this fossil fuel? Because of the catalyst. Because here the most favorable catalyst is the platinum, and all we know that platinum is one of the costly and this low abundance. So that's why people actually, scientists are trying to replace the platinum with this some cost-effective material. And this 2005, that theoretically that Jeans Norskov first time reported that the few layers of this the molybdenum disulfide catalyst can replace with the platinum with this with this the free energy versus this coordinate. They showed that this thermoneutrality of this MOH2 is close to the platinum. And of course, they have actually studied this one. And after this long, after this one, there's the 2011, that one of the group, that is the Hong Jing Dai, he first time used that this MOH2 nanoparticle with the graphene and showed that it's the active hydrogen evolution catalyst. But one thing here, they are actually using as a bulk material, because they are coating that material, they're mixing that and coat on a classic carbon electrode, and they have studied that one. So don't know that which part of the MOH2 is active, because if you see the MOH2, this crystal structure, whether it's the edges are active or in the basal plane is active. So for that, one study was there around the 2007, it's published in the Science. So they actually used this MOH2 nanoparticle on the gold 111, and they have studied with the STM studies, and from there they showed the edges of the MOH2 are more active than the basal plane. Okay, so it's not only that after that also people are still keeping on working, and then one of this method, that the AFM SCCM method, they have actually shown also the same thing, that the basal compared to the basal plane, edges are more active than this one. But of course, when you take this the STM and this the AFM, and they are actually the high cost, and there's this little bit the complicated instrument to understand that one. So in this direction, one of the instrument was actually one of the device was came at the same time of the time this STM was evolving. That 1989, Professor Alan J. Bard actually introduced a new technique using this electrochemistry, that is called the scanning electrochemical microscopy. It's a simple thing, like the 3-electrode system as we are using in our this daily electrochemistry, but the two thing is different. One is the size of the electrode. So size of the electrode is that it's a micron size of electrode, not the what we are using generally, the glassy carbon 3 mm or the 5 mm diameter. No, here the diameter is the in micron level, 25 micron or 10 micron or less than that. And one more thing, that is the piezo element or the stepper method that can move. So that's why the scanning, so that we can do the electrochemistry as well as we can scan the whole surface. Okay, so this is this beauty of this instrument. So yeah, here actually we can show that, okay, this is the one of this electrode, that the micron level electrode, and difference between this micron level electrode and our big electrode, that the 3 mm dielectrode, the difference is the diffusion. Here the diffusion is the hemispherical diffusion, so that's why current is actually saturated here. Okay, that we are actually not getting the peak as we are seeing in the planar diffusion. And what is the advantage of this one? See, when the electrode is approaching to the surface, because you have the g-axis, you can actually bring it up and down. So advantage that you can bring it close to the surface. When it's a conducting surface, current will actually increase. Okay, tip current will increase. Because why? Because your reduced species is oxidized, and oxidized species can further reduced, and so this cycle is continuous. So this actually production of more and more oxidized species on the surface, and that will reduce, so that your current will increase. And this is called the approach curve, and based on this approach curve you can control your electrode and to bring to close to the surface. On the other hand, interesting thing, that you can do the electrochemistry on the insulator also, because in case of the insulator it is showing the negative, because there is no chance of generation of the opposite species, the oxidized or the reduced species. So that's why we can actually use the electrochemistry on the this insulator also. So based on this approach curve, actually we can bring our electrode close to the surface, and we can study that in the interface what is actually happening. One of the example I can actually show you here. Yeah, this is actually happening in my previous lab. So here they have actually shown this the palladium nanocubes. And you see that when they have done the AFM, you cannot find exactly the nanocube size because of the deflection of the tips. Okay, this is the limitation of the AFM, that you cannot find the edges very clearly when it is in the nano regime. But when you use the nanometer size electrode, you can see that nicely that the sharp peak of the cube, the palladium nanocube they have used, and they have used here I think 14 nanometer diameter that platinum tip. And using the same phenomena, using this the ferrocene to ferrocenium, ferrocenium to ferrocene, and using these methods, they bring the electrode close to, and they have actually get the image also. So this is the advantage of this, and using this advantage, actually, we are going to study that single entity of that. Yeah, so as I mentioned that they are actually using the 14 nanometer electrode. So this is our 2 to 3 nanometer diameter normal glassy carbon, but this is the 25 to nanometer size that diameter electrodes. Okay, this is the FM of the top view of this. This is the APM images. This is the top view of the electrode, and this showed that okay, diameter is close to that 20 nanometer. And yeah, one more example I show you with this one, that all of you know that working on this the molybdenum sulfide, and the metallic phase of that is a 1T. That is 1T phase is the metallic phase, and that 2H phase is the semiconductor phase. So when we actually approach on the these 1T phases, this is the metallic phase, that means the conductive surface, that means the current is increasing. So it is the current is actually increasing in the approach curve. But when is the 2H phase is semiconducting, so it's a not conducting, so that's why current is actually decreasing. So based on these phenomena, we can actually, this is this 1T and MOS to that, why that 1T is the conducting, why 2H is not conducting. This is some theoretical prediction, and this is the high resolution TM actually showing that, okay, we can find out that. So if we want to know that whether you have this 1T phase or the 2T phase, you have to go to the TM, and then high resolution TM only can tell you that, okay, this is 1T. But without this one, you can use the simple SCCM technique, and based on this approach curve, you can tell that you have that 1T, you have that 2S phase. And you see that one of the example where the one sample was prepared in such a way that the 1T MOS2 and the 2H MOS2 are there in the together. And now you scan with this 55 nanometer the platinum radius platinum tip, and you can scan that and can clearly see that this is the 2H MOS2, this is the 1T MOS2. Current is high here current is increasing, this is the line scan, and here current is actually decreasing. Okay, so so this is that the electrocatalytic phenomena, but this this the Daniel Nacera that from this Harvard University, he actually working on the artificial leaf. So artificial leaf means you take you just prepare coating a material and put it under the sunlight, and they actually produce the hydrogen and oxygen. So whether we can use this technique, means the light as well as the electrochemistry under the photoelectrochemistry with this the SCCM technique. So in this direction, actually this 1995, one of the group actually started, they used the microelectrode and they tried to put optical fiber and try to study that one on the TI2 phase, but it was not gone to the next level. Professor Bard also tried, but Professor Bard how tried that he signed the light from the outside and try to scan the electrode. That recently 2017, that Professor Schumann from the Germany, he actually take a kind of little bit micron electrode and put optical fiber here and then try to go this one. But in these all cases, they are using kind of the micron size electrode. But our aim was to that we can do the same thing with a nano size electrode. So yes, we actually prepare a nano size electrode and put an optical fiber here. In the top of this is the optical fiber, and this is the tip in the glass tip. And when we pass the UV light, we can see that UV visible light, we can see that. So this is the light through the tube, and this is the reflection. So based on that, we can actually, using this optics, we can actually find out where is our tip. So whether we want to study this particle or this particle, well, we can actually move this one. But of course, when you have the many particle, it will be difficult to distinguish. So this is actually one of the study that using this 50 nanometer electrode, we have actually scanned that this niobium dope, that TiO2 using this platinum tip, and you can see that the current is increasing. Okay, and we can scan the surfaces, and then we can find that there is not much that any other that impurity is there except some the niobium dope. So that's some current increases because of the doping of this niobium. Okay, so this is actually tried with the side illumination, means what actually Professor Bard was actually trying, and this is actually trying the through tip. That you can see that when it's a through tip, the current is actually more, or enhanced the current is more compared to the side illumination. So we found that the through tip illumination is the more effective than the side illumination. So that in this direction, we actually try to this image, and this is the correlative, this is the photocatalytic activity. So what we did now in this one, we take this the TiO2 and deposit a single platinum nanoparticle. Okay, we have actually deposited more, but we have actually distinguished one of them, and then we try to find out. So this is the AFM image of that. Maybe some 3 or 4 nanoparticles are there, and we actually try to scan using this one. So that our acidic solution producing hydrogen, and hydrogen is reducing on the platinum tip, and based on the current, actually we are try to scan this one. Okay, so one case is actually use the 50 nanometer platinum electrode, other case we use 18 nanometer electrode, and we can actually distinguish one. But here actually one of the problems, so whether we are using this, whether we are exactly locating this one or not, this one actually we are not much actually sure in this one, because it is on the surface. Okay, so if we want to study particular this one, and if you want to see the morphology of that, you need to look for some alternate methods, okay, to understand the same particle, whatever you are doing electrochemistry and you are doing this microscopy of the same particle or not. So for that, actually we have actually studied one more thing, that is called this TM tomography. That is the 3-dimensional, that the transmission electrons microscopy image. So in this the 3D tomography, you can easily understand and you can actually analyze that one, that which part is more active, which part is not more less active. That study you can do. So in order to do this one, you need your substrate on the TM grid. Else, suppose you are suppose you have studied this particle and using this SEM, but you cannot take this particle to the TM and understand the TM tomography and understand the whole high resolution scanning or the 3D scanning. You cannot do that. So in order to do that, instead of that surface, you need a surface which you can take it to the TM. So for that, what we did, we use the TM grid itself as a substrate. So this is one of this TM grid. Actually, this is the optical image of the TM grid. So this is the carbon film, and this is this copper or maybe the gold grid. And we went to the AFM. And actually, why we went to the AFM? Because we want to see that whether the surface is a surface of this grid or carbon is the entirely smooth or not. And here we have see the line scanning, and it is in the picometer range. That means it's it's smoother than this in the nanometer, more than actually what we expected that one. So you can then one more thing, say suppose we want to locate a particular particle. Now how we will locate in the TM? Because in TM also with 300 means the 300 boxes are there. So which, sorry?
Can you please conclude within 2 minutes?
Okay. Okay. I thought that I have another 5 minutes. Okay, fine. I am concluding now. So we have used the finder grids. Finder grids is the numbers. That's based on this number we can locate and we can bring our T particular. Let's say this is 26. We have seen in the optical microscopy that a 26 is there. So we bring our close to this one and we actually shine light. And then what we did, we actually take a single that the TiO2 nanorod. This is optical image of that one nanorod on the TiO2 nanorod on the TM grid. And now we went to the SCCM and then we actually find that exactly that the TM scan, and then we take this one, wash it very gently, and then go to the TM, and we found exactly that in that TM that's images of that it's actually correlating that the TM and the SCCM insert. You see that here the current is more and here the current is more, but the limitation of the TM we could not find, we could not go to this the high resolution TM and to understand that why it is actually. So if we have that's such TM, and then we can go to the high resolution TM and or even the TM tomography, we can understand that the why current is more increase and why current is less here. So the structural information also we can get it from this correlation. Of course, I have tried also in this the AFM, and this is the correlation between this AFM and this the SCCM studies, and of course that we can find out using this approach curve and bring this electrode there, and we have studied this. And one more thing also we did, that is that we have studied this the photocatalytic, means that through the light we are lighting the UV light, right? Because sorry, so yeah, through this one we are actually shining this the UV light. So using this the UV light, we actually try to do this water oxidation and oxygen, and then oxygen is further reduced in the tip, and then this is the one of the rods. Actually we have get it that, so somewhere we get more current, somewhere less current, and some cases we got a huge current actually some places. So this is our actually one of the preliminary studies we have done to correlated microscopy with the photocatalytic activity. Now the next step was there actually, okay, that time I actually came back from there. So next step actually they are carrying on, that is they are doing this one. this TM tomography and try to understand that why current is more and why the current is less. So with this, I actually concluded that, this developed methodology nanoscale SEM and the photosystem on the TM grid, and this setup enabled to the multi-technique, that SEM TM or SEM AFM, and this the STEM images can actually understand the more insight of the photocatalytic or this photocatalytic activity using this technication. And with this one, yes, thank you. Okay, before that, concluding this one, so this is actually my field. I am actually basically from the material electrochemistry, but I have worked on the electrodeposition, electrocatalysis, in situ electrochemistry, devices, sensor, photoelectronics, and more interested in the nano electrochemistry. So this is my actually the range of the electrochemistry that things actually I have worked out. So if anybody is interested to this collaborated or something, you can please contact me in my mail ID. Thank you. Thank you for this. And thank you all for your attention. And thank you for the organizer. Thank you. If you have any question, yeah, I am happy to answer.
Vijay, nice presentation. I think your energy level is also very high. Fine. Any questions?
Yeah, you can, if you have, okay, I know that you're running out of time. So if you have any question, you can certainly write me in my mail ID and we can,
okay,
discuss. Yes.
There is one question.
Yes, sure.
Sir, it was a wonderful presentation. Thank you. And can you please explain the significant role of nanotechnology in photocatalysis?
In the photocatalysis?
Yes.
See, in the photocatalysis, we are using, so what we are doing, we are actually taking, maybe sometimes we are splitting the water, hydrogen and oxygen. Now, the nanotechnology or the particular, this technique will help you that, okay, what are the active sites? Now, all the sites are not active. As I showed in the MOS2, only the edges are the active, not the basal plate. So like that, all the photocatalysts are active because we are using in a bulk, we are drop coating in a, or making in a film on some electrode. So to understand that which is the active site, so if I find out using this nanotechnology, what are the active sites? So we actually synthesize the material, only such active sites are present more in the surface. And then we can use it so that our activity or efficiency will increase. So that is the advantage of this nanotechnology in the understanding the photocatalytic activity.
Thank you.
Thank you, sir.
Thank you, Dr. Sujay Sarkar, for your excellent presentation. And I am calling our next presenter, Anjana K. Wala, Department of Life Science from Bhubaneswar University, Gujarat. Dr. Anjana, can you start presentation?
Sure. Thank you so much, Chairman. Good morning, everyone. First of all, I would like to thank Professor Sabu Thomas and his team for inviting me to deliver a talk. And I would like to apologize due to I had mailed also regarding that my laptop had gone through a lot of issues. So my presentation, as per me, is not up to the mark as it is supposed to be. But I have tried to make it as far as comprehensible. So I would like to start with my talk. Is my slide seen, ma'am? Can you see my slide?
Yes, we can.
Okay. Thank you so much. Should I go back then? Okay. Thank you so much. So my topic is marine-derived fungi, biofactories of metal nanoparticles. I'm a bit, what should I say, different from the talks going on in a way that I'm basically a microbiologist. So actually speaking, in a frank way, I'm canvassing my microorganism to be harnessed as a biofactory for nanomaterials. And as we are moving on to the 75th anniversary of our independence, I would like to say here that I come from the place and my university is in the name of Maharaja Krishna Kumar Singh Ji, His Highness Maharaja Krishna Kumar Singh Ji, who was the first to donate his princely state for the sovereign India. So we can see the picture with Sardar Vallabhbhai Patel as well, Maharaja Sahab and Sardar Vallabhbhai Patel. So with this tribute to him, I would like to continue with my topic. As we all are aware, The metal nanoparticles are always unique in their properties from their bulk counterparts, and there are a number of requirements these days due to the various applications being developed. We require to have the controlled properties, the fine-tuned properties of the nanoparticles, and because of that we need to always have some tailor-made materials which can be used for better applications. And traditionally, as we know, metal nanoparticles are being synthesized through physicochemical routes, but they have got certain limitations in terms of either they could be cost intensive, sometimes due to the use of chemicals, they could be sometimes not environment friendly, and even it happens that there are certain chemicals, if they are used during the preparation protocol, they limit their application in the clinical and pharmaceutical applications. So these are the restrictions which calls for the development of cleaner protocols, development of safer protocols which can be used for better applications, and including the microorganisms as well as plants. They have been examined for synthesizing various nanoparticles. If we see the demarcations of the habitats, many of you are not biologists and ecologists, so I just would like to make it refresh. Everybody knows, but just to recollect that the entire habitat we can broadly categorize into terrestrial, which is pertaining to land, and the aquatic, which is pertaining to water. So the microorganisms which are present on land are known as the terrestrial microorganisms, and those which reside in the marine environment, they are known as the marine microbes. So if we see the applications of microorganisms in the field of nanobiotechnology compared to their terrestrial counterparts, the marine microbes have been, we can say, they have been slightly overlooked. People have not paid much attention to them as they are supposed to be given. So there is a lot of buzz and a number of scientists involved. They have proposed that initiatives should be taken for exploiting these important marine resources for nanobiotechnological research, and they would come up with some better potentials. And if we harness fungi, it would be even more beneficial due to their unique traits. So fungi, I should make clear again that fungi are a group of microorganisms which belong to the eukaryotic category. Microorganisms are basically prokaryotic, but some of them are eukaryotic, means they are having well-developed cellular architecture. So we, the mammals, and the fungi both have the eukaryotic cellular architecture. So why fungi should be more advantageous? If we, they are more advantageous when we use for nanotechnological applications. First of all, they have ease in handling the culture. When we nurture them in the lab, when we grow them in the lab, they are easy to handle. Their wall binding capacity is also very high, as well as they can take in the material. They can take up any metal uptake intracellularly, as well as they can even have the adsorption many a times on their cell wall surface. They can resist the high agitation rate or flow pressure if they are used in a bioreactor, because if we apply it on a larger scale, we are going to definitely grow them in a bioreactor. So fungi can be grown easily using bioreactors as well, and they can secrete a large number of amount of enzymes extracellularly. And when we have some chemicals extracellularly produced, it is easier for the downstream processing. Downstream processing means once the product is formed, its separation from the reactor is easier, And of course, because of that, economic viability also would be the advantageous part when we harness the fungal cultures for nanoparticle synthesis. So when we talk about biological systems for their application on in nanoparticle synthesis and its application in the biomedical field, people may say that when we use something for biomedical purpose in the medicinal field, immune response due to the capping proteins which are present on the nanomaterials could lead to a problem. Person may develop allergy to that particular material, so that also is an issue. Now, if the molecule of protein is glycosylated, if it is sugar encoded, in that case, the immune response can be suppressed or at least it can be reduced. So if we talk about fungi, they have better glycosylation abilities than the bacterial counterparts. And because of that, their capping and stabilization is better for their biomedical applications than in the case of materials which are synthesized through other biological routes. And because of this reason, we can say that fungus mediated nanoparticles can prove better from the biomedical application point of view. So actually during my fast track young scientist DST sponsored project, I could identify a marine fungus which was having tremendous tolerance and removal efficiency towards arsenic. We know that arsenic is one of the most potent carcinogen. So this fungus, it could tolerate even 2000 ppm of arsenic, which was very, very remarkable. And by that time, I could come to know through some publication in Nature, which had published, I think it was some from NCL or so. Yeah, it is from the group of scientists, NCL. So they have rather inspired me to take up this kind of work. And then I started thinking of putting up a project where I can harness these marine fungi for the nanotechnological applications. So during my CSIR Pull Scientist project, I worked on biosynthesis of these nanoparticles using marine fungi. So in general, if we see, fungi can be identified, they can be isolated from any of the natural sources. As we can see, even from food, we know that at home also the food gets spoiled if we leave it for some time, and especially during the moist conditions, it gets very easily rotten due to the development of fungus. But this fungi can be very useful if we take it in another way, if we harness its potentials in a scientific way. So even wood can be the source of some fungus, food materials or fruits, even from soil, or other dead biomass or some other materials, and of course the marine environment also. We can always isolate and identify fungus. So if the fungus is in a filamentous structure, we generally call it fungi, which is a mold. And if it is having a unicellular structure, we call it a yeast. So yeast and mold, but we in general say fungi and mold. So fungi and yeast. So we can culture them in the laboratory, in the flask. We can grow them on the petri dishes. We can grow them, and we can. Fungi are the kind of organisms that they are easily tamed in the laboratory. They can easily tackle any of the adverse conditions, right? So if you supply with any of the metal salt, and if you optimize the parameters, cultural parameters, the fungi can develop the nanoparticles in a green mode. So we can say that in an environmental friendly mode, and they can be isolated, and then we can go for a number of biomedical applications as well as environmental and agricultural applications also. This diagram I have taken from somebody else's publication, but I can add it to, they can also be utilized for agricultural as well as environmental benefit also. So why actually fungi they are doing this? Why they should synthesize easily for us the nanoparticles from the any metal salt they are given? Because nature has endowed with some strategy to them to tackle the adverse conditions. So even if they are given any heavy metal, they will be using any of this strategy to get rid of the stress of the heavy metal which is imposed on them, right? So they can either chelate the material intracellularly using their metalloprotein or rather metallothionein or any of the peptides which they produce, which have the metal chelating ability. They can produce certain enzymes which can detoxify the stress of the material. They can precipitate the the metal intracellularly. Sometimes they volatilize the compound of the metal, or they can complex the metal by producing certain metabolites extracellularly. So they do not let the metal in, but they complex it outside the cell in the surroundings, or even they can precipitate or bind with the cell wall also. Sometimes mere adsorption can also work. It will not let the metal in. Sorry. Sorry. So redox transformation, biomineralization, a number of strategies fungi have developed which help them in growing as a biofactories for synthesizing nanomaterials. So this is one of my publications in the marine microbial metal for heavy metal marine ecology. And this diagram I have made inspired from the publication from Professor Gutt, who is a very renowned biologist, having a tremendous work on fungal metal interactions. So if we come again with the marine environment, so the marine fungal strains, so far what we have seen about the fungal traits, they are in general. But when we talk about the marine fungal strains, they have been found in any of the marine habitat, including the inorganic matter, marine plants, marine vertebrate as well as invertebrate animals, marine microbial communities. They can reside on other microbes as well. Then they can be found in water as well as in sediments. And utilization of marine derived fungi is a less explored area, but compared to their terrestrial counterparts, marine fungi always have more adversity which they require to be tackled, and because of that they have developed with more and more potentials, and because of that they have more advantages than the terrestrial fungi. But till 2009 these promising resources have not been given attention as a synthesis. I mean, in harnessing for synthesis of biomaterials. Professor Kathiresan in 2009 and his colleagues first reported the marine fungus, which synthesized marine fungus Penicillium falutinum, which synthesized the silver nanoparticles, and with that started the what should I say, the studies on the marine resources for their application in bio-nanotechnological field. So in one of my publications, I had prepared a timeline which can give us idea about how the marine derived fungal nanotechnology evolved. So in general, there was a research on fungal mediated synthesis started in somewhere around 2001. As I said, the people from NCL and some other lab, I'm forgetting, they had started working in this line. And then in 2009, Professor Kathiresan's group reported the first marine fungus to produce nanoparticles. Then, as I said, by that time, even I got inspired to take this work further. and even I started working in my lab regarding this, and it was assigned me as a CSIR pool scientist project. So but during that time, I was working with physics department. So my colleagues from physics, they helped me a lot during this project, and we started working in collaboration, and we observed laser speckles by the nanoparticles which were synthesized from a marine derived fungus, Aspergillus niger. Then one more important noteworthy feature I could achieve during my work, it was that some marine fungus known as Rhizopus oryzae, it could synthesize the gold nanoparticles extracellularly as well as intracellularly. So, and that too under static condition. So that is even more economic, because if you, and whenever we think in terms of the industrial microbiologists, they always think in terms of money. They have nothing to do with what R&D you are putting in. They just think in terms of how much money I can save or how much profit I can gain. So if the fungus is doing it under static condition, you do not need to apply the what should I say, the cost in terms of providing the shaking condition. So this was the first report which we could make. It was about the intra and extracellular biosynthesis of gold nanoparticles by some marine fungus. And by that time, two more things we could achieve. That we isolated the secondary metabolite from a marine derived fungus, which is known as the siderophore, which has the tendency to chelate iron, and using that purified peptide we could synthesize the silver nanoparticles. And during that time only, in collaboration with my physics group, I could work on the weak localization of light using the gold nanoparticles synthesized by a marine derived Aspergillus niger. So as I said,
Anjana,
marine,
sorry for the
yes,
interruption.
ma'am.
Can you please conclude within 2 minutes?
Okay, sure, ma'am. Oh, so anyway, so in this slide we can see that we are at Maharaja Krishna Kumar Singh Ji are in one of the 3 pioneering working groups in India, which have the privilege of starting starting work on application of fungi in the field of nanotechnology. And at MKBU we have the success rate of 100% whenever we have applied any marine fungi for its application for nanoparticle synthesis. So this is the strategy what the fungus develops when it is applied, when it is supplied with the metal salt. So it can synthesize the nanoparticle this way. To be more precise, the silver and gold nanoparticles. So these are the pictures of the fungi which I have used. So this is the before production of nanoparticles. This is the after. Okay, I'm skipping this slide as well. Yeah, this is the characterization of the particles. Yeah, and this is the laser speckle what I was telling. It has been published in Micro and Nano Letters in 2014. We could also develop the protocol where within 3 minutes we can synthesize extracellularly silver nanoparticles. Just within 3 minutes you mix the fungus and it is going to produce. It is one of the very remarkable properties which we could have. And this Rhizopus oryzae, as I was telling, it is published in this journal, and it is, as I told, it is the first ever report. This particular fungus, Rhizopus oryzae, it is showing the synthesis of gold nanoparticles. So this particular picture is after 48 hours. So we can see that the synthesis has already taken place. and it is very remarkable. It has got very remarkable property that the project is over and it is nearly 8 years, and still I have got one sample. It is still stable. It is very remarkable feature of this particular nanoparticle, that the sample I have in a small vial, it is still stable. The particles are in their dispersed state, they have not settled yet. And it could be, what I think is, it could be due to the electrostatic repulsions which is arising due to the negative charges which are developing on the conjugate proteins, which is making the particles suspended in the suspension. And these are the various ranges of particles which I could produce by changing the pH of the medium. This is the IR diagram. We can see this is the weak localization, as I was telling, which was published in RSC Advances. So this is the Aspergillus pseudovi, one more fungus which could synthesize the gold nanoparticles. So I had a chance of writing a chapter for this particular book. These are the applications of these marine fungi developed nanoparticles. We can see this slide shows the strategy of silver nanoparticles for getting for developing the antibacterial mechanism. How do they do it? They either hamper the DNA synthesis, or they can break the cell wall, or they can hamper the phosphate metabolism, and a number of strategies are there which help them in exerting the antimicrobial activities. So when I talk about mold, I should say about something about yeast also, but I have not worked with yeast. But there are people who are working on yeast as well. So these are the work from some other people who have done the production of nanoparticles using marine yeast as well. But this is not my work. These two slides are somebody else's work. So this is one of the recent works, one of the recent publications, where in this particular book we have got two chapters, chapter 14 as well as chapter 17 are from my group, which is basically working on, telling something about the marine derived nanoparticles. This is very recent chapter where we have something to contribute in the field of nanotechnology through fungi. So I would like to acknowledge a number of institutions as well as the number of people who have helped me a lot, and of course CSIR, who given me the opportunity to work on my project. Then Department of Science and Technology for some other project as well. I acknowledge my institute, Maharaja Krishna Kumar Singh Ji, Bhavnagar University, where all my 3 projects I have carried out. I would like to thank Professor R.V. Mehta, my PhD mentor, Professor H.C. Dubey, Professor S.P. Bhatnagar, Professor R.V. Upadhyay. I have forgot, I skipped to mention one name, late Dr. Rajesh Patel, with whom I have published the RSC Advances paper. He is no more with us now. I thank my current head of the department. I thank all the colleagues and students who have contributed during my work. And of course, I thank again the organizers for giving me an opportunity to interact on this international platform. Thank you so much.
Thank you, Dr. Anshana,
Thank you,
for
ma'am.
your wonderful presentation. And if somebody is having some clarifications or queries, you may please.
Hi, ma'am. It was a wonderful presentation. So
Thank you
I
so
have
much.
a question. What
Yeah,
is the
please.
advantage of using marine fungi over yeast for obtaining the nanoparticles?
Yeah, ma'am. See, the fungi, you mean mold, right? They have
Yes,
got
yes.
the filamentous structure. So if you use yeast, you need to centrifuge to separate the biomass. So again, you are putting in some cost, right? If you use the filamentous fungus, by simply filtration, you can remove because they have got the filamentous structure. They have more this thing surface area to work on, so they can snatch more metal nanoparticles from the surrounding because of their more access to the surface, right? So these are the common things which we can have as the advantages of using them. And always it is if we think in terms of industries, the easy downstream processing is, because many a times it happens, ma'am, that 70% of the cost of production goes to downstream processing. So if we use this kind of materials, it's very easy, their growth rate is very high. If they get contaminated, you can easily make out. So all these things make them more advantageous than their unicellular counterpart in my point of view. I hope I have satisfied your query, ma'am.
Yes, ma'am. You made it clear. Thank you so much.
Thank you. Thank you so much. Can I have a small question to Professor Sabu, sir, if the chairperson permits? Regarding the evening presentation it is. So if the chairperson permits, can I ask a question to sir? Because I had mailed, but I think he might have not sent due to busy schedule. Sir,
Yes,
can I ask you regarding, thank you so much, ma'am. Sir, based on my presentation, would you suggest me to prepare a slide for the evening presentation regarding the collaborative work? Sabu, sir?
Sure.
Can you hear me, sir?
Yeah. Dr. Sabu Thomas is in the another hall.
Okay, sorry.
You may please prepare the presentation. No problem.
Okay, thank you. Thank you so much, ma'am.
You're welcome.
Okay, thank you.
So thank you, Dr. Anjana. We
so
are
much,
moving
ma'am.
to the next presenter. Next presenter is Dr. Sanu Surendran from KMCT Polytechnic College. Dr. Sanu, are you present? I think Dr. Sanu is not present. So let's conclude the session here. I thank Dr. Dan, Dr. Sujay, Dr. Anjana for your excellent presentation. And in fact, the session, nanoparticles, was really interesting. And I also thank the organizers and also the audience. Thank you very much.
Thank you. Thank you so much. So we conclude the session here, ma'am? Yeah.
Yes.
Okay. So is it a lunch break, I think? Or no?
We are
No.
moving to the next session.
Okay,
in fact, I would like to hand over to the organizers. Thank you.
Okay, fine. So we should be there in the meet, I think, right?
Yes.
Okay. Thank you.
Ma'am, now welcome to the third session.
Yeah, just 1 minute, Dr. Shiva.
Minu POC. Are you ready?
I express my sincere gratitude to Dr. Sikojo for chairing the session. Let's give a big applause to our chairperson for excellent chairing. I express thanks to the speakers for the wonderful presentation. Now we are moving to our next session, and I cordially invite Dr. Shivakami
Yes, ma'am.
for chairing the session.
Okay, thank you, ma'am. Welcome to the third session. First of all, I thank organizers for giving me a chance to share the session on nanocomposites. We have two speakers on this session. They will be given the talk about nanocomposites. I would like to request the speakers, please keep the time level, and if any questions on the delegates, you can ask them at the end of the session. Thank you. With this, I would like to invite the first speaker of this technical session, Minu Pius from St. Teresa's College, Ernakulam, India. And the topic of the talk is tailoring the synthesis routes of zinc ferrites nanocomposite for diverse applications. I welcome you, ma'am.
Okay.
Please start.
Thank you, ma'am. I hope my screen is visible for you. Is it visible?
No.
No.
No, ma'am.
Just a second. How about now?
Yes.
Okay. So good morning, everyone, and I'm very extremely thankful for giving me this chance to present my topic. I'm Minu Pais from St. Teresa's College, and I'll be presenting on tailoring the synthesis routes of zinc ferrite nanocomposites for diverse applications. So zinc ferrite has spinel ferrite structures, and the synthesis approach, reaction temperature, and stoichiometry can decide the kind of structure as well as the features and properties shown by the zinc ferrite. So in the nanocomposite form, we can enhance the surface reaction sites through corners, edges, and defects. And it has got optoelectronic tunability, chemical stability, and super paramagnetic nature. We can design hybrid designs and heterostructures, which can increase the absorption capacity and making it finding application in photocatalytic realm, as well as in targeted delivery, drug delivery, and magnetic hyperthermia effects. So many kind of materials have been made nanocomposite with zinc ferrite. We can actually make we can increase the efficiency of zinc ferrite as such by making in the nanocomposite form. So the objective of the talk is to present the optimizing of the calcination temperature involved in the synthesis of zinc ferrite nanoparticles, and using that optimized calcination temperature, the further synthesis of nanocomposite is employed via different synthesis routes, and we have explored the photocatalytic and photothermal utility of the nanocomposites. So in the first topic, that is, we tried to synthesize the zinc ferrite nanoparticles using the co-precipitation method, and after using the chloride precursors. And once a precipitate is formed, we have subjected the sample to different range of calcination temperature, and the samples are named after the temperature that is used as for calcination. And the further characterization of the synthesized samples were done structurally using the XRD and FTIR, as well as thermal analysis was also done like TG and DSC to ensure the thermal stability under different temperature. So from the X-ray diffraction studies, we could see that there is a evolution or emergence of emergence of peaks from the 400 temperature onwards, and the crystallinity has increased with temperature, and all the sample from 400 onwards, the diffraction peaks of zinc ferrite has been emerging. And another feature that is noticed is that the size, because the crystallinity is increasing, the size has been of the crystallite size also has increased, which is calculated using the Debye-Scherrer formula. And further thermal stability can be ensured by analyzing the thermogravimetric analysis, where we'll check the weight in loss, the loss in weight due to the heating of the sample, and the uncalcined sample has been used, and you can see that there is a steady decrease in weight, and almost 23% of weight degrees has been noticed, and further for 650 beyond 600 and all, there is a stability in the weight loss. So this can be attributed to the evaporation of the volatile components and the thermal decomposition, which lead to the steady weight loss before getting the stabilized form. So it also we have done the differential scanning calorimetric studies to measure the enthalpy change, and from the plot you can see that there are endothermic peaks and exothermic peaks corresponding to the evaporation of the volatile compounds and the crystallization of the sample. And so these two studies the confirmed that beyond the 600 degrees Celsius or will be giving a much thermally stable sample. And FTR studies have been also being done in order to know whether the structural formation has been complete, and it also confirms that from beyond 400 calcination temperature onwards, the characteristic peaks of zinc ferrite has evolved, which corresponds to the iron oxygen vibration in the octahedral site and the zinc and oxygen vibration in the tetrahedral site. So another peculiarity that is also noted is that with the emergence of calcination temperature, the characteristic peaks have formed, as well as there is a decrease in hydroxyl vibration due to the hydroxyl groups for the samples which are subjected to 700 and 800 degrees Celsius for calcination. So from our first work, we could conclude that the crystallinity and the structure formation as well as the thermal stability can be ensured for an optimum temperature of 700 or more, and correspondingly that temperature was used in the synthesis of nanocomposites. So the nanocomposites were synthesized in a similar manner, except that after the precipitate is formed, it was drop by drop added to the silver nitrate and trisodium citrate solution to get, and the calcination was done in 700 degrees Celsius, and the sample was named as CS0. While in the second way, we tried to add it in a quick manner, and the sample was named as CS1. And while in the third case, only after digestion of the reaction and centrifugation, the precipitate was mixed with the precursors for silver formation, and correspondingly the sample was named as CS2. So we will be comparing the characterizations of these samples compared with the zinc ferrite nanoparticles. So in all, by doing the X-ray diffraction studies, we could see that there is a steady increase in, all the samples have shown zinc ferrite, the diffraction peaks corresponding to the zinc ferrite lattice, as well as silver chloride has been noticed in CS0 and CS1 samples, and silver has been completely formed, reduced in the CS2 sample. So this could be attributed because only after the zinc ferrite formation, the silver precursor was added. So we could see there is the crystallite size was noticed, was calculated using the Debye-Scherrer formula, and the lattice parameter was also seen to decrease with the nanocomposite nature. And further, using FTR analysis, there is a presence of the characteristic peaks of spinel ferrite in CS0 and CS1 samples as well as in the CS2, but there is a shift of peaks to the octahedral vibration noticed in the CS2 sample, which indicates a possibility for an inversion of the structure. And further, since it is a magnetic sample, we try to study the magnetic effect using the vibration sample magnetometer analysis, and it showed that the composite sample CS2 has got higher magnetization, saturation magnetization compared to the bare sample or other nanocomposite. It's only because it also confirms the possibility for inversion, because the ion which occupies the octahedral site will be exchanged to the tetrahedral site as well, and which can increase the exchange interaction and hence enhance the saturation magnetization of the composite. So this could be very much helpful in making it used as a retrievable sample for further applications. And diffusive reflectance spectrum was analyzed, and we could see in the top plot a red shift and band gap, which could be attributed to the increase in crystallinity that is noticed in the case of nanocomposite as well. So the samples were nanocomposite sample were further investigated for its photocatalytic ability. So the methylene blue is considered as a dye which is often used in paper industry and textile industry, and even toning silk cloths and even in medical field also. But in high dosage, and after it is used, it is discharged from especially from the textile industry. It is discharged into the water bodies, so which can increase the chemical oxygen demand, and hence the carcinogenic and mutagenic effects have been caused to the human beings as well as to the aquatic life. So several treatment has been used to filtrate this, remediate this water. And one of the method is photocatalytic degradation is found to be a good method because it doesn't constitute any secondary pollutants in the process. And one of the problem identified in the photocatalytic degradation is the separation of the photocatalyst after using it for wastewater remediation. So in that aspect, the magnetic photocatalyst could be a very good candidate. So in that, with that aim, we try to use this zinc ferrite, the nano composites of zinc ferrite, which have been shown better magnetic behavior, is used for the degradation of methylene blue, which is taken in the 10 ppm, which is the minimum concentration that is available in the wastewater. And the sample dosage used was 1 gram per liter. And this solution was stirred in 30 minutes in darkness. And after that it is exposed to the direct sunlight, and we could see a steady decrease in comparing the samples, and also it is compared with the silver also. So CS2 sample has shown similar behavior as that of the silver nanoparticle as well, and we could see there is an exponential increase in the degradation efficiency for the CS2 sample, and all the samples, nano composite sample, has shown better performance in the photocatalytic. It could be attributed to the better performance, a better band gap it has obtained in the nano composite form. And using the pseudo first order kinetics, the reaction rate constant was also found out. And I could see that the degradation has happened even in 90 minutes of exposure. The CS2 sample has given 97% of degradation of the dye, and the maximum was obtained as 99 point, almost complete degradation has happened in 3 hours. So, and also comparing the rate degradation among the nano composite, the CS2 sample has shown a better, very good reaction constant compared with the silver as well. So in comparison with the literature reports, we could see that zinc ferrite has normally used in photocatalytic activity, but in the presence of strong oxidizing agents like hydrogen peroxide. And if it is in nano composite form, more dosage has been used and more time is taken for degradation and for beyond or above 90% degradation of dye. And in our case, our sample has shown 97% of degradation within 90 minutes and almost 99.5% degradation in 3 hours also. And further, so this could show that it could be act as a magnetically retrievable photocatalyst, very good photocatalyst. And further, we try to investigate the thermal diffusivity of these samples. For that, we performed a dual beam thermal lens technique, where we'll be exciting the sample using a laser beam which corresponds to the absorbance of the sample, and that is 480 nanometer. And there would be a change in, because the laser is a Gaussian beam, you'll be getting the maximum heating in the center of the sample, or the axis of the beam, and there is a refractive index change about that axis, and correspondingly as the liquid will expand on heating, you'll be getting a diverging lens which is called a thermal lens. And we'll be probing the thermal lens using another laser beam which is called probe beam, and and we'll be seeing a thermal blooming effect, and this could be measured in the time dependent intensity variation in the probe beam during the blooming. So this was analyzed using the this theory of expression using for the intensity, and we could obtain the time constant, time response of the thermal lens, from which we can find out the thermal diffusivity of the sample. So employing this, we took zinc ferrite and the nano composite in nanofluid form with water, and using the theoretical fit, we could find out the thermal diffusivity of zinc ferrite as 2.61, and which is on comparison with water, which is having 1.4, almost 86% higher thermal diffusivity is noted. And while all the nano composite, especially CS1 sample, which consists of silver chloride and zinc ferrite as a constituent in the composite, has shown a remarkable thermal diffusivity property. So so we can see that by tailoring the property, we can tailor the property and suitability of the sample for various application, either by changing the calcination temperature and tuning the synthesis route. We can increase the crystallinity, modify the structure, which can enhance the saturation magnetization and hence bring in the super paramagnetic behavior, which make it useful as a retrievable sample. And increased absorbance has led to the increased performance in the photocatalytic ability as well as enhance the thermal diffusivity. So we could see that the nano composite prepared in the form of zinc, ferrite and silver could act as a magnetically retrievable photocatalyst, which shows 7% degradation of methylene blue dye within 90 minutes of direct sunlight exposure, while the zinc, ferrite and silver chloride nanocomposite can act as a very good thermal conductor and which could be used in the further for biomedical treatments like magnetic hypothermia and even photodynamic therapy. So we look forward to such applications in future also. So I thank my guide as well as my team for enabling me to do my work. Thank you.
Thank you, ma'am. Audience have any questions? Please ask. Any questions?
Hello, madam. Madam,
yes, sir.
Have you seen the XRDs of zinc ferrite at various temperatures and the comparison of these XRDs and peaks? Zinc ferrite at various temperatures, have you taken the XRDs, X-ray diffraction patterns, and you have compared?
Yes, sir. Yes, sir. I have already shown that. We have compared it, and from
so
that,
what is the observation? Can you?
Observation that is with temperature, the crystallinity is increasing with temperature.
What about the stability?
Yes, stability was noted. Stability was compared with the TG analysis and using DSA method as well as FTR analysis, which showed good thermal stability as well as the mechanical stability also.
Okay. Okay. Thank you.
Thank you, sir. Thank you, sir, for the question.
Anybody? Any questions? Okay. Thank you, ma'am, for your nice presentation. Thank you.
Thank you, sir.
The second talk of this technical session is Toja Lisa Sagu, Department of Chemistry, School of Applied Sciences, Centurion University of Technology and Management, Bhubaneswar, India. And the topic of the talk is investigations on the photocatalytic and antibacterial properties of samarium doped zinc oxide and tin oxide nanocomposites. Toja Lisa Sahu. Who? No. Nobody is there. Okay. Now I wind up the session.
I express my sincere gratitude to Dr. Shivakami for sharing the session. Let's give a big applause to our chairperson for the excellent sharing. I extend my thanks to the speakers for the wonderful presentation.
Thank you, ma'am.
Hello. Hello, may I audible? Hello.
And now I cordially invite Dr. Sujoy Sarkar for presenting, for chairing the session. Is Sujoy Sarkar present for chairing the session?
Okay. Since Dr. Sujoy Sarkar is not there, I invite Dr. Vishnu Prasad Sahu, School of Applied Science, KIIT, deemed University, Bhubaneswar, for the presentation. Dr.
Okay.
Sahu, are you there?
Yes, 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 I am here. Am I audible to everyone?
Yeah, yeah.
Okay,
You
thank
can
you.
just share your screen and start presentation.
Okay, thank you, the team ICN 2022 for accepting our topic and selecting our topic for the invited talk. Okay, I would like to convey my happiest thanks to the team. Okay, my screen is visible, right?
Yes,
Hello?
your screen is visible.
Okay, thank you, ma'am. Actually, I'm working as a associate professor here, and this presentation is completely made by my PhD scholar, Miss Swati Acharya, and that's why her name is in the top. So basically, we are working on the dielectric properties of conducting polymer based nanocomposites. Okay, so this is our broad research area. So today we are going to present the topic entitled an effective strategy to enhance the dielectric and electromagnetic radiation shielding of thermoplastic polyurethane polypyrrole graphene oxide based polymer nanocomposites. Okay, so here the things we will be discussing, the contents are introduction, objectives, experimental techniques we have used, what are the results, what are the analysis or characterization we have done, that we will discuss in the result and discussion headings, and followed by conclusions and references. So as you know, introduction needs to be presented in every presentation, the very short introduction that polymer nanocomposites has tremendous application nowadays. So and here we are first of all in our lab we are synthesizing the conducting polymers like polyaniline we have synthesized in the oxidative polymerization method. Now we are focusing on polypyrrole, that also we are synthesizing by same oxidizing polymerization methods, and we are getting the polymers in variety structures like nanolayers, nanorods, globules, all are in the nano to micro, you can say, so 100 to 200 300 nanometer dimensions we are getting. Okay, so then what are the major drawbacks of the conducting polymers? The conducting polymers advantages are first that they are highly conductive, and they are having good dielectric property as well as dielectric loss, both they are exhibiting. So our aim to explore the use of the conducting polymers. So but they are exhibiting both epsilon dash and epsilon double dash, that means storage behavior as well as lossy behavior equally. So how we cannot store charge, we cannot use them. So then how to reduce the lossy behavior, how to when we are reducing the lossy behavior, that time also we are reducing the epsilon dash, that is in the permittivity. Okay, so we are trying our level best to reduce the lossy behavior some extent or more, but the epsilon dash should be in the range so that the epsilon dash suppress. So epsilon dash should more than the epsilon double dash. Okay, so that this is our motto to develop, and these materials are very suitable to be used as a capacitor, as to observe the electromagnetic radiations, and some sensors, piezo sensitivity, like that. So many applications are there, but we are focusing on electromagnetic radiations. So again for the electromagnetic radiation shielding or microwave shielding, more number of interfaces are required. Okay, so more number of interfaces means the composite should be a hybrid one. So first of all, we are taking a insulating polymers, that is here PPU, thermoplastic polyurethane. Also we are taking PDMS in another work. Also we are taking PVDF, it is assigned to another student. Okay, so then we are taking conducting polymer, that is PPY, polypyrrole. And then we are also incorporating very minimal quantity of graphene or graphene oxide or carbon-based nanofillers, so that we are developing some interfaces. Okay, so that interfaces, when the interfaces are more, when the radiation enters to the material, so that the radiation will follow multiple reflection in the bulk. So finally, the intensity of the radiation, the energy of the radiation getting decreased, so it will be observed. Okay, this is our motto. So these are the conducting polymers are very famous, and in earlier also it is synthesized. They are synthesized and reported in literature, and we are focusing in our lab polyaniline, emeraldine salt form, and polypyrrole, that is also doped form. Okay, so PTSA we are using as doping agent. Okay, so that PTSA increases the polar characteristics, which is very important for dielectric applications. We are focusing here polypyrrole. Then coming nanocomposites. As we know, the composite means if one composite means the mixture of two materials. If one of the material dimension, one of its dimension is less than 100 nanometer, then the composite is called as nanocomposites. And these nanocomposites are having a very suitability to different applications. That's why it creates very large interfaces. Who creates the nanofiller creates? Okay, the highest surface area, also we can functionalize the graphene, functionalize the CNT, but here we are not used any functionalized graphene, but it can be. Okay, so that's why it creates very large interfaces between the nano-sized building blocks and polymer matrix. It allows to design and so many it allows the polymer nanocomposites can be used where the conventional nanocomposites cannot be used. Okay, then these are the graphene oxides and reduced graphene oxide. These are the structures. Coming to the EMI shielding, that is the main application of our work. So there are two types of particularly electromagnetic shielding material. One is absorption dominant, other one is the reflection dominant. If a material exhibiting, if the surface of the material is conductive in nature, conductive, that means the conductivity is almost equal to the conductivity of a semiconductor. So what will happen? The radiation, electromagnetic radiation or microwave will come and reflect. Okay, reflection also contribute the EMI shielding. Okay, or then if the material is dielectric one means the conductivity is somehow moderate, but the epsilon dash permittivity is good or adequate, then the material, the radiation will enter, and it, due to presence of so many interfaces, it undergo multiple reflections and finally it will absorb, just like your Ferris black body. We can take the example of Ferris black body. Okay, that's why we have categorized absorption dominant and reflection dominant EMI shielding materials. Then our objective to fabricate TPU, thermoplastic polyurethane, PPY, and geo-based nanocomposites through solvent casting. Very simplified solvent casting. We have taken DMF with ultra low amount of geo, characterize the manufactured blend nanocomposite structure and morphological analysis. That means we have characterized the synthesized or the fabricated nanocomposites by FESM and by Raman, as well as we have gone for dielectric test, and then finally we have tested their efficiency of microwave shielding. Then experimental technique, these three materials are used. Okay, thermoplastic polyurethane is based, it is having both elastic and plastic characteristics, so it is very compatible, at least physically compatible with polypyrrole and geo. That's why we have chosen that one. Okay, that means it has no objection to take PPY. Okay, we have done the PVDA with PPY. We are getting so many problems during synthesis, during fabrication of the film, but in case of thermoplastic polyurethane, it is very user friendly. Then polypyrrole, we are getting very high yield, and its conductivity is very adequate enough, and it can be tuned also by varying the doping percentage, doping amount. It can also be, the conductivity can also be tuned. Okay, that is the major advantages of PPY. Then geo, obviously geo, we are taking very minimum quantity, and that is compatible with polypyrrole as well as thermoplastics, polyurethane, and we are getting so many interfaces for the incorporation of geo. These are the schematic representation of our fabrication of the polymer nanocomposites. Okay, first we are taking the sonicating the geo, then we are making the solution of what in PPY and geo in DMF. Then we are another container, we are making the solution of TPU, then we are adding, then followed by sonication, then we are pouring on the battery disk, then we are putting in the film, sorry, in the oven for at 80 degrees Celsius, then we are getting the film, and then we are going for some characterizations. So these are the formulation techniques we have used are going to present today. So that is 95:5, 90:10, 95:15, 80:20. These are the what the PPY and TPU blend ratios, and we have added only 0.2 php, means parts per polymer of graphene oxide in 95:5 blend. Okay, so we have means this work need to be explored again, but we have just started this work. So resultant discussion. This is the Raman. The first one is the black one, the Raman of Geo, and the red one is the Raman of PO PPY. Then the Raman of TPU and PPY. And TPU PPY Geo Raman yet to be done. Okay. So here the D band and G band, that the characteristics bands which represents the the D band represents the digital graphite structure in graphene. So due to interaction with PPY and TPU, sorry, the interaction of a PPY and TPU, particularly from the blue color graph, it gives us the significant idea that, or the idea which substantially ensure us that yes, there is interaction between PPY and TPY. That's why the D band is shifting from 1365 to 1395. So this is the first one, the FESM image of PPY. That is this type of structure we are getting. In the very initially, I told you that whatever synthesis method we are using, they are almost nano, some 150, 200 nanometer to 300 nanometer, like that. Here we are getting this type of particles of PPY. So PPY is a polymer, but we are getting the nano form. Then when it is incorporated in TPU, so this type of interfaces, so many interfaces we are getting, these interfaces are very required for the multiple reflection of the electromagnetic radiations. So then coming to the dielectric properties. So here the dielectric epsilon dash, that is nothing but the dielectric permittivity. So the black color, the PPY, no doubt a conducting material will exhibit high dielectric permittivity, but equally also it exhibits high dielectric loss. That's why we are at the top of the graph, we are getting only the PPY present, that is it exhibits high dielectric permittivity because it is polar in nature and it can easily polarize along the direction of electric field. And even the decrease of epsilon dash with frequency also moderate. That means the dipoles are very fashionably present in PPY, so they can elongate in the field direction very nicely. Okay, so because listen, we can in the literature also, in our earlier work, we have noticed the sharp fall of epsilon dash with frequency, but here we are not getting sharp fall, moderate fall. That means the dipoles are properly oriented and relax along the direction of applied field even at higher frequency. Okay, so then at the bottom TPU, it is very insulating. That's why the last we are getting TPU, that epsilon dash. Then in between them we are getting the blends. Okay, so 95:5, in the blend ratio, it exhibits the 95:5, 80:10, 85:15, 90:10, all are coming in between the PPY and TPU. Okay, but from the figure, it is 85:15 exhibits high permittivity, and 80:20 in the next graph I will show you. Yes, 80:20 exhibits high conductivity. Okay, so actually on the if we consider the epsilon dash as the measuring factor or optimization factor, so you can see that 85:15 is the best polymer, best ratio of the polymer blend. Okay, but every ratio we will explore the effect of graphene oxide. So we have started only at 95:5. Okay, so then after addition of 0.2 php of graphene oxide, so we have noticed significant some marginal improvement in epsilon dash. Okay, as well as the fall is very means what the means the for dielectric permittivity, the fall with frequency is also nominal, or you can say, or we can conclude that it is considerable, that is no drastic fall. Again, coming to the tan delta value. So tan delta always it is the ratio of epsilon double dash by epsilon dash. Okay, so epsilon double dash obviously here predominates. That means the within 10 to 1 to 10 to the power 1 frequency, the value of tan delta is more than 1. But after this, we are getting the value of tan delta is less than 1. That means after this frequency, the epsilon dash predominates over epsilon double dash. That's why tan delta value is getting 1, less than 1. That is the means good findings, or one of the important findings of our work. We can suppress epsilon double dash, and we can increase the epsilon dash, or we have it is we got it at least after 10 to the power 2 frequency hertz. Then coming to the epsilon sigma SC, here the sigma SC is also increasing with PPI exhibits high what electrical conductivity, the AC conductivity, that is quite obvious. And again, we can say that the conductivity increases with frequency, but almost it is parallel with the frequency axis. That means again we can say that the PPI is synthesized very nicely, so that there is no noise in the graph. Okay. So again, the blends are also exhibiting the sigma SE in between them. Coming to the EMI shielding. So EMI shielding, we are from the Agilent technology instrument, we are conducting the EMI shielding in the 8 to 12 gigahertz frequency range. And there are we are getting S11, S12. S11 is the reflectance, S12 is the observance. But from the S11 we can calculate ACR, and S12 you can calculate SCA. That is, SCA means absorption, extent of absorption of electromagnetic radiation, and SCR means extent of reflection. Okay, by this formula we can calculate. So coming to the, this is the schematic representation, how the incident radiation enters inside the multi-phase composite system, and how the immediate, the green color, that is the reflection of immediate reflection. Then some of the part will enter to the composite system, how it undergo multiple reflections, and finally absorption. Then there is the purple color, that is also transmission. Obviously there will be transmission, there is reflection, and some sort of absorption. Our aim is to dominate absorption over reflection as well as transmission. So here the again another schematic representation here, how the red, blue, and green color arrow, they are undergoing multiple reflection in the bulk of the material due to more number of interfaces. Coming to the our result here, total EMI shielding. Total EMI shielding is the sum of ACR plus ACA. So here the 9010 with increasing the here the 9010 is this one 15 decibel, and the red one is the 8020, that is almost 20 to 25 decibel, and 85 is to 15, that we are getting 32 decibel, and 95 with 95 is to 5 with 0.2 php of graphene oxide, we are getting 35, more than 35 decibel. That means we are expecting that by uploading more, that is 0.4, 0.5, 0.7, like that, the geo loading. So we are expecting that more EMISC we will be getting. So coming to the conclusion, the TPU PPI geo blend nanocomposites have been fabricated by simplified solvent casting methods, and we have gone for FESM analysis, and we noticed, or we recorded some development of interfaces, so which is our aim. Then 95 is to, we have explored the effect of geo on 95 is to 5 blend ratio, and we noticed the marginal improvement in permittivity, but significant improvement in dielectric, that is EMI shielding value. So these are the references, and thank you the team ICN 2022 for considering our topic for presentation. Thank you. So I would like to have some discussion. At least
Sir, I have
some.
a doubt.
Yes.
Sir, I like to know how we can reduce the radiations which is coming out from this mobile phones and all. What we can do about it.
Actually, that is our main aim. Today also I am writing a patent on this. So actually, this is the mobile. Like every chances of coming this is the 5G era, and every chances of coming what microwaves from the radius in the server room as well as from the mobile phone. So actually, our plan is to develop the film. Okay, film by uh, conducting polymer using conducting polymer, so that it can be placed inside the mobile cabin or cabinet, because it is very lightweight, anti-corroding, so it can observe. So but we have not gone that much of in depth, but this is our aim. We are working on
Okay,
it.
no problem. You can call the next person directly. Okay, okay, sir. Thank you.
Thank you, ma'am. Thank you, sir. May I stop my presentation?
Thank you for your nice presentation. And we are going to the next presenter. Next presenter is Dr. Mahabole Megha.
Yes.
Are you present? Yes.
Yeah.
Okay.
Okay.
So can we directly go to the presentation?
Yeah. Thank you, sir. Thank you.
Yes. You please share your slides.
Okay. Thank you, sir. Share Monica. Today? Thank you. Hello? Hello?
Yes, you
Yeah,
are audible.
am I audible to you? Am I
Yeah, you
audible?
are audible.
Okay.
Can you
Thank
make it full screen?
Okay. Yeah, I'm here full screen only. Okay.
But it is not visible. The slides are not in full screen mode.
Okay.
Madam, you please share your full screen.
1 minute, please. So I have shared actually. Whether it is, can you see? Can you see the slides now? Hello. Hello.
Now it's coming. It's coming. You can start.
Okay.
Can you put it in slideshow mode?
Yeah.
Full screen.
Okay. Very good morning to all of you. I'm Dr. Mahabole from School of Physical Sciences, SRTM University, Nanded. Am I audible to you? Yes?
Yes, ma'am. You're audible.
Okay. The topic of my presentation is development of hydroxyapatite-based nanocomposites for dielectric applications. Actually, hydroxyapatite belongs to a category which is called as apatite, and generally they are given by the formula M10XO46Z2, where M is a metal divalent cation such as strontium, calcium, etc. X is a trivalent species, usually phosphate. Z is an anion such as hydroxyl group or fluorine or chlorine. This is the crystal structure of hydroxyapatite, which shows you the PO4 tetrahedral structure, and the hydroxyl groups, they are arranged along the C axis of the crystal
Excuse
structure.
me, ma'am.
Yeah.
Ma'am, your slides are not moving.
Not moving?
Yeah, it's just the introduction, like the topic part is like that is visible right now.
Okay, I don't know. I have done everything. I don't know. Can you see now?
No, we can see the slides, but only the first slide we can see.
Okay.
Can
Now?
you start it again? Maybe then it will.
Now? It's okay?
No, ma'am. Only first slide we can see.
Okay. I don't know what to do now. Can you see all the slides now?
No, no, ma'am. Ma'am, can you just start it again, the presentation?
Okay, okay. Okay. 1 minute, please. Now, can you see now? Whether this is changing now? Hello?
Ma'am,
Hello?
right now nothing is visible, like no slides.
Okay. Mm-hmm. Oh, what should be done now? I don't know whether this is what should I
Ma'am,
do now?
have you shared your presentation again? Because there is nothing visible in the screen.
Okay. I'll say entire window.
You have clicked the share button. Dr. Megha, you have clicked
Yeah?
the share button. You have clicked the share button.
Yeah.
And then
Now,
what you see?
yeah, this is the window that we have where all the participants are there and also my presentation.
Okay.
So I'm
You
sharing
just
that.
open your PowerPoint.
Yeah.
You,
I
yeah.
have opened. Huh.
Yeah. Now you go to full screen.
Where is full screen? I don't know.
Yeah.
Now,
Click
can
there.
you see? Can you see?
I think it is still now in the not in the full screen. So
Okay.
can you just stop sharing? Then please please do as I inform. Okay. Now you go to share, but click share button.
There is no share button now.
No, the arrow one next to the raised hand.
No.
On the bottom part of your screen.
Yeah.
Yeah, you just click on that. Now you see entire screen.
Screen.
Yeah, click on that. Now you can see a white a window. You just click and then click share.
Can you see? Can you see now?
No, you just click your share. You click share.
Yeah, I have already done that.
No, you click the screen and then you see a window. Then you again have to share. Click on the share.
Yeah, I have. Window.
No, it is not shared.
Share. Now?
Yes, it is coming. It is coming. Now you just open your PowerPoint. You make it full screen.
Yeah. It's full screen only. Okay.
Okay, fine, no problem, madam. You just try to move the slides.
Okay.
Can you just?
Can I speak now?
Madam, can you just move the slides? I just would like to confirm whether slides are moving.
Okay. Now see. Yes.
No, slides are not moving. We are in the second slide. So I will do one thing, madam.
You have sent the presentation to us.
Okay, 1 minute. Will you please
Maybe
give
you
me
can
2
try
minutes,
once
please?
more.
Sure.
Will you please give me 2 minutes, please?
Oh, okay, fine.
Okay, thank you, ma'am.
And by that time, can you please mail your presentation also?
Okay.
And if the next speaker is available, can we?
Sorry, madam. I'll just do that. Hello?
Yes, please.
Yeah. 1 minute, please. हे प्रेझेंट नाही होत आहे तिथे त्यांना स्लाइड्स दिसत नाहीयेत.
You can just send the slides if you want.
Window.
Can I instruct her what to do?
Can you see now? Can you see
yes, it is coming. Now go to full screen.
Full screen कुठे? Full screenचं काय? नाही दिसत आहे त्यांना. Can you see now, madam?
Yes, we can see. But
You try to keep it in the slideshow mode. I mean,
yeah, it's a slide slow.
maybe, maybe you
Hello?
can select again, share presentation, select entire screen. When you share, initially when you share, select entire screen. Madam, yeah. Now you again share, click on entire screen. Yes. Dr. Mega, can you hear me? You are muted. Dr. Mega, you are muted. Dr. Mega, can you hear me?
Yeah, 1 minute, please.
Yes.
Can you see now? Hello?
Yes, it is coming. It is coming.
Huh?
Yeah.
Can you see?
Yes, we can see that. Not in full screen, but maybe you can. Can you please change the slides? Move the slides, please.
Can you see now?
It's your second slide only. It is not moving.
okay, madam, you please send it by mail. Do you have our email ID?
Yes, yes.
You please send your slides. We will operate from here. Okay.
Okay. हे करू का वाईट एक्झिट म्हणून प्रेझेंटेशन सॉरी आता काय
You are sending the slides?
Yeah. Just a minute, please.
Yeah.
माझा स्लाइडच दिसत नाही ना येत नाही येतो Stop sharing as wanted. Can you see now?
Yes, it is fine now. It is fine now. Yes. Please move the slides, please. Yes, it is okay. It is okay.
Okay. Thank you.
Okay, please start your presentation. Thank you.
Okay, very good morning to all of you. I am Dr. Mahabole. Very sorry for the disturbance or the trouble that has incurred meanwhile. I am from School of Physical Sciences, SRTM University, Nanded. The topic of my presentation is development of hydroxyapatite-based nanocomposites for dielectric applications. Am I audible, madam, now? Hello?
Yes, ma'am, you are audible, ma'am.
Okay. Generally, hydroxyapatite, it belongs to apatite family, and that family is generally represented by the formula M10XO46Z2, where M is a metal divalent cation, X is a trivalent species, and Z is an anion. Okay. This slide shows the crystal structure of hydroxyapatite, which contains the phosphate tetrahedral structure and the OH group, which is aligned along the C axis of C-axis. This hydroxyapatite is widely used in biomedical applications, and it has specific properties like biocompatibility, bioactivity, non-toxicity, non-immunogenic, non-inflammatory, osteoconductivity, and stability in the physiological environment. This hydroxyapatite finds wide applications in biomedical field, particularly orthopedic and dental applications. It is also being used for chromatography, It is also used in drug delivery system as well as in catalysis, fuel cells, chemical gas sensors. And now we have already worked on this hydroxyapatite material for biomedical applications. We have studied the bioactivity of the pure HAP as well as the ion exchange HAP materials. If we have correlated that with the dielectric material, dielectric constant of that material as a function of its time. Okay, incubation in a simulated body fluid. We have also worked on chemical gas sensors, and we have successfully used this material for sensing the gases like CO, CO2, like that. And now in this particular paper, we just want to discuss its dielectric properties and how it can be used for as a dielectric material. There are variety of techniques which are generally used for the preparation of hydroxyapatite. Sol gel, hydrothermal processing, microwave irradiation route, ultrasonic spray pyrolysis, emulsion system, sonochemical synthesis, and wet chemical process. So in this particular synthesis, we have used the wet chemical process because it is being the simplest of all and very cost-effective method. So during synthesis, we have used calcium nitrate and diammonium hydrogen phosphate as the main precursors. We have prepared the 1 molar solution of calcium nitrate and 0.6 molar solution of diammonium hydrogen phosphate. We have mixed it and we got the milky precipitate. So the pH of that milky precipitate was adjusted with the help of liquid ammonia, and it was kept for stirring for 24 hours. After that, the material, whatever material we are getting, that is dried at 100 degrees centigrade and it is sintered at 1000 degrees centigrade for 2 hours. And this material, what we have obtained after sintering, is the hydroxyapatite. It is also called as bioceramic material, and ceramics are the generally materials which are generally prepared after sintering. Only a particular phase which is of our interest is developed. So that material is then characterized by XRD, FTIR, SAME, and AFM. We have used hydroxyapatite that we have prepared via this chemical route as the main matrix material, and we have selected alumina as the other ceramic material as a filler material. So alumina is one of the representative electric insulating material. It has high thermal conductivity and high chemical stability at high temperature compared to the other electronic electro-insulating materials, and it also works as a catalyst, and it exhibits excellent dielectric performance, and that's why we have selected alumina as the filler material. So this is this crystal structure of alumina. Then after that, we have prepared the composite of that. We have considered HAP as the main matrix and Al2O3 as the filler material. And the approach that we have used is the mechanical mixing process. And we have prepared number of compositions here. We have 100% HAP, 100% Al2O3, and then we have different compositions, 90-10, like that. So we have prepared approximately 10 to 12 samples, and we have prepared the composites. This whatever material that we have prepared, pure HAP, pure Al2O3, and the composites, all these materials, they are converted into the pellet form using the hydraulic press, and the diameter of that every pellet was generally 13 mm and the thickness is of 2 mm. The dielectric studies has been carried out with the help of Cortec 7600 LCR meter, and various parameters are measured with a parallel plate capacitor arrangement. The frequency range was varied from 10 Hz to 2 megahertz, and the temperature, we have carried out these dielectric measurements at room temperature. So using this LCR meter, we have measured the capacitance, dissipation factor, real and imaginary parts for our study. The dielectric properties of HAP are very important as far as the biomaterial applications are concerned. it has been observed that the application of electric field can accelerate the healing fracture in bones. Also, the electrical stimulation enhances the rate of growth of bone growth whenever we are using the bone grafts. And the electrical pooling of hydroxyapatite enhances its bioactivity. And therefore, actually, if you just consider the bone is a composite material, natural composite material, wherein we have fluid, collagen, and the hydroxyapatite material. So that's why here, and in addition to that, the films, the hydroxyapatite films have been widely used as a dielectric or insulating coating for various implants also. So wherever necessary, and that's why the dielectric properties of hydroxyapatite and its composite are very, very important. So the results now. This typical slide shows you the XRD pattern of hydroxyapatite that is synthesized in the lab. It gives you typical peaks corresponding to hydroxyapatite, and the XRD confirms the growth of a hexagonal phase of HAP, and the crystallite size was calculated just by using Divisor formula, and it is observed to be 36 nanometer. Then we have FTIR, which shows the presence of phosphate as well as the hydroxyl groups which are present, and these functional groups confirms or assures the growth of hydroxyapatite. This is the same and IDAX of the hydroxyapatite that we have synthesized. It shows the elements like carbon, oxygen, phosphorus, calcium, and it tells you that all these elements, they are there in the hydroxyapatite structure. So the next diagram is related to the AFM, atomic force microscopy, and this atomic force microscopy tells you something about the nano size of the hydroxyapatite. So this nano is roughly of 20 nanometer. So the elements confirms the formation of HAP, and AFM indicates the synthesized material is of nano size. These are the X-ray diffraction pattern of HAP alumina composites. For comparison, we have introduced the XRD pattern of HAP as well as pure L2O3 for comparison, and it shows the presence of typical alumina peaks at 37.3, 39.4, and 42.4 and 45.5, and that can be assigned to particular planes, and all these peaks, they correspond to alumina. If you just see the XRD pattern of composites, these are the typical composite XRD patterns of typical composite materials. So this shows the typical structural characteristic corresponding to aluminum oxide as well as the host, that is hydroxyapatite. In other words, the crystal structures of HAP and L2O3, they are retained in the composite as well. So this indicates the successful blending of oxide filler with the HAP ceramic matrix, and the composites are just the physical mixture of the two. These are the FTIR graphs for the composites, and the presence of at the bottom we have FTIR for HAP, and it is also compared with L2O3 and typical one of the FTIR for one of the composite materials. So it shows the presence of functional groups for HAP as well as L2O3, and it also indicates the blending of the L2O3 with HAP. So these are the this is the dielectric this is the dielectric constant graph, that is the frequency versus the dielectric constant of the material, and all the samples, they exhibit high dielectric constant values in the low frequency region. The dielectric constant decreases with increase in frequency and exhibits the frequency independent behavior in the higher frequency range. The dielectric constant of pristine HAP and Al2O3 are found to be roughly 44 and 880 respectively, but when the L2O3 is incorporated or blended with the HAP, the dielectric constant increases. So the highest dielectric constant is observed for 20% HAP and 80% L2O3 composition. And the dielectric constant for composites are found to be the functions of the composition. So you will find that as the percentage of HAP and L2O3 changes, then the dielectric constant also changes. So this graph shows you that for 20% HAP and 80% L2O3, we have maximum dielectric constant. This is the graph compare for dielectric loss, and it is observed that the dielectric loss shows the hump actually in the low frequency region, and for certain materials as the percentage changes, it converts into hump. At the hump is slowly shifting from low frequency region to somewhat high frequency region. So the dissipation factor also decreases with increase in frequency, and there are two humps. Small hump is observed in the low frequency region, and in addition to that we have another hump in the somewhat near about say 10 to the power 3 hertz. And if you just see the values of loss, the loss is found to be somewhat very much smaller. This is the AC conductivity of HAP as well as the HAP based composites, and from the graph you can just see that up to 10 to the power 5 the AC conductivity remains somewhat constant, and it increases for higher frequencies. So it shows the frequency independent behavior in the low frequency region, and in high frequency it increases. So this is all about my presentation. Thank you very much. I would like to thank the organizers for giving me opportunity to present my work. Thank you. Thank you.
Thank you, Dr. Megha. It was a wonderful presentation. Now the session is open for discussion.
Yes. Hello.
Hello.
Yes.
Session is now open for discussion.
Okay. Hello. Hello.
Ma'am, there is no question from the audience. So thank you for the presentation.
Thank you. Thank you very much. Thank you very much.
Now for the next presentation, I would like to invite Pinaki Laha, Department of Physics, LND College, B.R. Ambedkar, Bihar. And the topic is the effect of defects on magnonic spectra of alloy antidot arrays. Hello. Dr. Pinaki Laha.
Yes, yes, good afternoon.
Yes, sir, you can
Just sharing my slides.
Yes.
Okay. Am I audible and visible now?
Yes, sir, you are audible and slides are start your
Yeah.
presentation.
Okay, thank you. Myself, Dr. Pinaki Laha. I am from LND College, Motihari, which is in Bihar University, Muzaffarpur. Now I am going to start my topic, that is the effects of defects on magnonic spectra of Fermi antidote arrays. So first of all, I have to describe what is basically magnonic devices. I think it is quite new and something interesting for few peoples because it is less research topic at present. So my topic is on magnonic crystals, which is an potential to use spin waves to carry and process information, and also in building nanoscale microwave components such as filters, attenuators, and phase shifters. There are several applications in biomedical field also. So basically, magnetic nanostructures form the basis of many present and future technologies, including pattern magnetic media, magnetic random access memory, magnetic logic devices, and magnetic resonance imaging. Nanomagnets may be used to propagate high-frequency magnetic excitations in the form of collective long-wavelength spin waves as information carriers in magnonic crystals. When the magnetic elements are strongly magnetostatically coupled, antidote lattice is a strong candidate for magnonic crystal, as this is an exchange coupled periodic media with large propagation velocities for magnons. So what is magnonic crystal? The periodic arrays of nanomagnets may be considered as an artificial crystals where spin waves or magnons are the carriers. They are known as magnonic crystals. There are several types of magnonic crystal is showing in my slide. First of all, that is a stripe, which is in one-dimensional magnonic crystal. And secondly, the second slide, that is the 2D magnonic crystals. There are two types of magnonic crystal is showing in the slide. First one, that is the dot structure, quantum dot structure, and second one, that is the called anti-dot structure. Okay. So my research topic is focused on the search for magnonic band gap and tunability of the gap with various physical and material parameters of magnonic crystals are the key aspects of research in magnonics. We are basically focused on the magnonic band gap, which is different from the electronic band gap of a material. And we are trying to tune the band gap of magnonic band gap of a magnetic structures. So why magnonic crystal is so important for study? The study of magnetic excitations in densely packed arrays of nanomagnets provides a test bed for investigating the static and dynamic dipolar coupling between the elements in an array and the occurrence of a vast range of magnetic ground states and the resulting magnetic spectra. Magnetic nanohole or antidot arrays are well-known candidates for the magnetophotonic crystals due to the influence of magnetic field on the light coupling to surface plasmons in such system. Static and dynamic magnetic properties of magnetic nanohole arrays are a relatively new topic of interest, and the magnetic ground states of such systems depend strongly on the shape and size of the magnetic materials between the nanoholes. Magnetic nanohole arrays do not suffer from the superparamagnetic effect even at the deep nanoscale dimension due to the absence of any isolated small magnetic entity. Why magnonic crystal? The holes introduce locally distributed shape anisotropy and act as spinning centers for the hole displacements and spin waves. The hole pattern modifies the magnetic behavior of the thin films and gives rise to an increase in the coercive field of the in-plane magnetization with increasing hole diameter and to the appearance of out-of-plane magnetization components. Consequently, the periodicity of these structures has a strong influence on their magnetization process, which is a very much important factor. One of the most important recent applications of magnetic nanhole arrays is magnetic crystals, a microwave analog of the so-called photonic and sonic crystals. Magnetic crystals deal with the opportunity to modify the short wavelength magnetic excitation spectra in spatially modulated magnetic materials, which leads to the area of artificial structures, aiming to the design of novel materials with powerful functionalities. To reach the goal, it is important to investigate various possible periodic and non-periodic artificial structures and their effects on the magnetic spectra in terms of the various physical parameters. Basically, the magnetization dynamics depends on what factor? One is the mechanism with the time scale, because that in time scale the magnetization dynamics is changing. Above 1 nanosecond to 10 nanosecond, basically domain wall dynamics is pronounced, which is used in DRAM devices, magnetic media devices, read-write head, MRAM devices. And above 1 picosecond to 100 picosecond, or that is in the range of 10 to 100 gigahertz, the magnetization precision, which is my research area, is very much pronounced. Here we use LLG equation, which is Landau-Lipschitz-Gilbert equation. This is the governing equation to describe the magnetization process systematically and qualitatively, even quantitatively, using this equation. The equation is dm by dt. M is magnetization and H is the magnetic field. Dm by dt is equal to minus gamma naught. Gamma naught is the gyromagnetic ratio. M cross H plus alpha by ms into M cross dm by dt. There are two terms here. First is the precision and second one is damping. Alpha is a damping quantity. So first of all, we have studied the car rotation using magneto-optical car effect. What is happening with the very varying time scale? We can see that the first is demagnetization initially, and secondly that the first remagnetization and remagnetization with precision occurs. Basically, and the third one is the laser induced demagnetization, which is also my research area. So less than 1 picosecond, that is ultra fast demagnetization, and 1 to 10 picosecond, that is the remagnetization. We are solving LLG equation using macrospin model and the micromagnetic simulation. So what is spin waves? So spin waves are the very much important factor here to carry the information in the magnetic crystals. So there are three type of interaction. One is exchange interaction, second one is dipole exchange interaction, and third one is the dipolar interaction. And the three pronounced mode are occurring. First one is the magnetostatic surface mode, which is known as MSSW mode. Magnetization, and Q is the wave vector, M is the magnetization, which are perpendicular to each other. And second one, that is the magnetostatic forward volume mode, that is the MSMVM. And here the M and Q are perpendicular to each other and perpendicular to the plane of the wave vector. And third one is the magnetostatic backward volume mode, which is known as MSBVM mode. Here magnetization and the wave vector are in same plane and in same direction. There are three dispersion relations are there. First one for magnetostatic surface mode, second one is the magnetostatic forward volume mode, and third one is the magnetostatic backward volume mode. So first of all, I have to discuss about some experimental evidence what is happening here. First of all, we experimentally we can prepare the permalloy thin film by the sputtering unit or electron beam evaporation technique. There are several techniques by which we can prepare magnetic thin films, and we have studied the VSM measurement about their magnetic property. Then we have studied the surface morphology by atomic force microscopy, and we have studied that the roughness is 0.154 nanometer and the grain size is 5 to 10 nanometer, which is very much important to fabricate a magnetic device because the roughness should be very less and the grain size is also less. So after that, after preparing the thin films, we have go for the focused ion beam lithographic system. Basically, this is a very much important to develop magnetic devices, because this process can prepare a good quality of magnetic devices. Here we have prepared different type of permalloy and antidote with different diameter. Basically, here we have used the Helios Nanolab 600 dual beam FIB, which is iron milling is done by the liquid gallium plus iron beam lithography on blanket permalloy flame to create array of holes or antidotes on the permalloy thin film. An optimized beam current of 28 picoampere limits the beam spot size around 8 nanometer to get a sufficient etch rate. Initial milling of holes is done at 30 kV voltage in single pass. The redepositions are removed at 2 kilo-electron-volt milling voltage in multipass mode, which ensure the holes with much cleaner and uniform edges. The spot size is a function of a beam current. But the problem is that it is not an easy process to prepare or fabricate a good quality of magnetic devices, because there are several disadvantages and there are several defects arises. So what is the motivation of my research topic? Here we present a systematic micromagnetic simulation study of magnetic modes in permalloy antidot arrays. Specifically, we investigate the effects of the areal density and symmetry of the array and defects introduced in the array. The magnetic modes are mostly dependent on the density and the symmetry of the array, but are weakly dependent on the defects. We have further investigated the modes in a tailored array consisting of equally spaced lattice structure with varying density using micromagnetic simulation. Micromagnetic simulations offer us with a virtual experimental route to understanding the fundamental physics involved and guiding principles towards the design of an advanced structure before getting into the expensive nanofabrication and characterizing techniques. These results will open up the possibility of tuning the magnetic bands in magnetic antidot arrays by careful design of the structure of the array. What is the simulation technique used here? We have used OOMF, object-oriented micromagnetic framework, which is a micromagnetic simulation tool, which is a free open source software. In the simulation, we solved the LLG equation, Landau-Lipsch-Gilbert equation, to calculate the stable magnetic configuration after the energy minimization process. The input material parameters used for permalloy are 4 pi ms. Ms is the saturation magnetization, which is 860 Oersted. Exchange stiffness constant A is equal to 13 into 10 to the power minus 12 joule per meter. Magnetocrystalline anisotropy constant is 0. Damping constant alpha is equal to 0.008, and the LLG gyromagnetic ratio gamma is equal to 17.6 megahertz per Oersted. OOMF software discretize the input sample geometry into rectangular prism-like cells and solves the LLG equation at each node. We have studied arrays of 10 by 10 elements with cell size dimension 3 by 3 by 20 nanometer for the simulation. So, effect of defects in permalloy antidot lattice. We have investigated the effect of introducing defects in the arrays on the magnetic spectra. We have selected the square array with W by S is equal to 1. We have introduced two types of defect. The first one is one circular in shape, while the second one is square in shape. The pattern region is rotated with different angle. So, and the third one is the resulting time resolved traces and the effective spectra, first Fourier transform spectra, are shown in figure. The introduction of defects does not affect the magnetic spectra significantly. So these are the permalloy antidot arrays. First one is the perfect arrays. Second one is introducing 10% defect. Third one is the 25% defect, and fourth one is the 50% defect. Diameter of the antidot arrays is 200 nanometer, and the separation between the two antidot arrays is 200 nanometer. So these are the effective spectra, and first one is the result of the magnetization process. The creation of a new mode inside the regular pattern region due to the alternate blocking of folds is responsible for the suitable change in the frequency spectra. Introducing more defects, less peaks are observed at higher frequency. After that, we have studied that the angular dependency of the structure. So we have used here 25% defect because the results are much more interesting. So we are just rotating the antidote arrays with different angle, that is the 0 degree, 15 degree, 30 degree, 45 degree according to the magnetic field. So the first one is the for the perfect square lattice, and the second one is the 25% defect square lattice. So with the angular changes, when the angular dependency study is happening, there are several changes. There are splitting of the peaks. There are so many things are happening here, so which is much more interesting, and we are working on that. And the second one is the square lattice, square antidote lattice, permalloy antidote lattice. We have seen that the 25% defect is very much gives us very much interesting result. So we go for that directly, and there are with the changing the rotation, we are getting different type of peaks, which is in the peak splitting, and there in the lower frequency ranges we get peaks. So these are the peaks and their results. The periodicity of the magnonic structures has a strong influence on their magnetization process. Modifications of the morphological properties of the pattern film have a direct impact on the static behavior and the magnetization reversal mechanism in permalloy antidote arrays with engineered defect. They can influence the dynamic behavior, leading to a variation in the strongly localized mode arising at the hole edges. In a preliminary modeling study about the role of defects, it was concluded that they do not affect the magnonic spectra in a significant way. The angular dependence of the magnonic spectra does exhibit the expected changes. However, their effects on the magnonic modes and their implications or device applications are still to be understood. So thank you. I want to acknowledge my mentor, Professor Anjan Burman, and Alphas Nano Magnetism Group, SN Bose National Center for Basic Science, Kolkata, Department of Information Technology, Government of India, and my college, LND College, Motihari. Thank you. Thank you all. Sir, I am not getting your voice. Thomas, sir, I am not getting your voice.
Excuse me, sir. Sir, your mic is in mute mode, so you can unmute yourself. And then
Can I unmute my mic?
Actually, it's full of comedy, right? What to take. Continue. So what should I do? You just comment. Now what should I do? Thank you, Nagilatha, for your presentation. Next we call Dr. Kaniga Dulta, Faculty of Applied Science and Biotechnology, Shulini University, Ceylon, India. And the topic is anti-cancer potential of green synthesized syncoxane nanoparticles using aqueous extract of rhizome of Bergenia filata. Dr. Kanika, are you there? Dr. Kanika? Dr. Kanika, are you there?
Yeah, hello, madam. Hello.
Dr. Kanika, yes, yes. What you can do is you just yes. So for the next session on biomedical application, I would like to invite Professor Gautam Singh, Department of Applied Physics, Amity University, Uttar Pradesh. Dr. Gautam, are you there?
Yes, ma'am, I am here.
Yes.
Uh,
You can invite the speakers, Professor Gautam. Thank you.
yeah, okay, ma'am. Thank you. Yeah, so let me invite Dr. Kanika Dulta for her presentation. She is working as research associate from the Soloni University, Solon. So, Dr. Kanika, please go ahead and do a presentation.
Dr. Kanika, you are mute. You can unmute yourself. Dr. Kanika Datta, can you unmute yourself? Your microphone is blocked. We can't hear you.
Yes, Dr. Kanika, please unmute yourself. Yeah, Dr. Kanika, please go ahead and.
Dr. Kanika, is there any problem? Is there any problem? If so, maybe I request Dr. Gautam, can you call the next presenter and then we can continue with Dr. Kanika by the time she will make the microphone ready?
Yes, ma'am. I can do that. Yeah.
Yeah.
So the next speaker is Dr.
Dr. Lakshmi
Lakshmi.
Vinayar, she has informed that she has an urgent meeting today,
Okay.
and she won't be taking today. She will be taking tomorrow. So
Okay.
can you please call Dr. Preeti Jain?
Yes, ma'am. Okay, so Dr. Preeti Jain from Sarda University. Are you there, ma'am? Dr. Preeti Jain, ma'am.
Dr. Kanika? Dr. Kanika, if you have the problem with the mic, can you please stop presenting now and we can give you a chance later?
Am I
Because
audible? Am I audible?
Yes, you are
yes,
audible.
you are audible. Yes,
Sorry for
yes, now audible.
yes,
Thank you.
I'm
Thank
so
you.
sorry.
Okay.
So here
Please share your
this
slides.
so screen is visible to everyone.
Yes.
Yes, yes.
Okay, yes.
Good afternoon,
Please.
everyone. Good afternoon, everyone. I am Dr. Kanika, working as a research associate, Faculty of Applied Sciences, Solon. So today I'm here to present my work, the anti-cancer potential of the green synthesized zinc oxide nanoparticle using aqueous extract of rhizomes of Virginia ciliata. So first of all, introduction. So as we know that the nanotechnology was presented by the F. Fammer in 1959 lecture. As we know that nanotechnologies deals with the particle size that ranges from 1 to 100 nanometer. Meta nanoparticles with unique optical and electrical properties have widely investigated during the past decade. Metal and metal oxide nanoparticles are various types like zinc oxide, magnesium oxide, copper oxide, silicon, so on. So these are used in the biomedical application. Depend upon the size and the shape, the nanoparticles can be also classified 0, 1 dimension, 2 dimension, and 3 dimension. So in this study, we have focused on the zinc oxide nanoparticles. So here comes the zinc oxide nanoparticle. Zinc oxide nanoparticles are the second most abundant metal oxide after iron. It is very cheap and safe, and it can be easily prepared. And zinc oxide nanoparticles have the high energy band, so it has excellent chemical, electrical, and thermal stability. So according to the Food and Drug Administration, it has proved as the zinc is the safe material for use, and also we can use for the edible coating. So here the figure is showing the different property of the zinc oxide nanoparticle. In the previous literature, many people work on the anti-tumor, anti-inflammatory, antifungal, and wound healing. So nowadays many people are working on the edible coating, so we can preserve a food for the we can preserve food and also increase the shelf life. So here comes a method. How we can synthesize the nanoparticles. So nanoparticle synthesis methods are of three types: physical, chemical, and biological. If we talk about the physical method is also called as the top bottom method, in which the larger particles decompose into the smaller particles and then inform the nanoparticle formation. And the physical method consists of the mechanical method, vapor method. Mechanical method consists of the milling, and the vapor method consists of the vapor decomposition, and it also divided into the three parts like sputtering, laser abulsion, and laser pyrolysis. If we, then we come to the chemical method. Chemical method is called as the bottom up method. In this, it is the opposite of the physical method. You can say the reverse of the physical method. First, it form the atom, then atom into the cluster and the formation of the nanoparticle. So it is done by the sol gel, chemical vapor deposition, colloidal method, and spray pyrolysis. Then comes to the biological method. It's the very cheap method, and the most of the people are working on this method. This is called the green synthesis. Green synthesis means the use of the plant like the stem, flower, root, seed, etc. And also we can use micro, bacteria, fungi, and yeast. So in this study, we use the green synthesis. Green synthesis means the cost-effective, eco-friendly, use less temperature and non-toxic material. If we compare with the chemical method, chemical need high temperature, high pressure, and use of the chemical. So in the study, we have taken the plant Virginia ciliata. It is an evergreen herb belonging to the family Sagiforaceae. It found throughout the Himalayan region, and this plant is found very useful in the dissolving of kidney stone, and also it can be used for the antibacterial and anti-tussive properties. So here come the material and method. So first of all, we have collected the sample from the Himachal Pradesh district Shimla. So you can see the arrow is the collection site, and if figure figure B is showing the rhizome of the Virginia ciliata, and figure C is the powder form of the Virginia ciliata. So further, we have done the preparation of the extract, and the figure 2 is showing the flow chart of the green synthesis of nanoparticle. Here's the journal flow chart of the green synthesis of nanoparticle. For this study, we need a biological extract. It could be anything like stem, root, flower, and then the metal solution. In this study, we have taken the zinc acetate dihydrate for the formation. After which, we have the mixing of these both plant extract and the solution, and then after the main thing is come to the point is pH, temperature, and pressure. So it's the main optimizing condition we need for the synthesis of nanoparticles. So after this, the capping and reducing take place, and the synthesis of nanoparticle done. So here the flow chart, what we have done. First, we have taken the zinc acetate, that is the metal precursor, and plant extract is the Virginia ciliata rhizome. So we have done the mixing of these, then the color changes take place. Now after we have adjusted the pH by using the NOH 1 molar. After we kept the solution on the stirrer for 60 degrees Celsius for 2 hours, and after stirring, we kept the solution for 2 days in the dark, and then after we have done the centrifugation process and the removal of impurities by washing with ethanol, by washing water, then we have done the hot dry the pallet. Then after we kept the sample in the muffle furnace to 3 to 4 hours at 350 degrees Celsius, and here comes the zinc oxide nanoparticle in the whitish form. So here's the whole process how the nanoparticle formation take place. After the result comes. So in result class, we have done the firstly we have done the characterization by UV visible, FTIR, XRD, DLS, SEM, and EDX. But if we talk about the first, the visible observation, as you can see, the figure 4.8 is the zinc acetate solution. Second one is the plant extract, and then is the final color changes. So we can say it depends upon the surface plasma resonance, which help in the bioreduction of zinc oxide nanoparticle and changes the color from yellow to lightish brown. After we have done the UV visible analysis, as you can see in the figure 5, it shows the peak around 340 nanometer, which confirm the formation of a nanoparticle. And we know that in UV visible spectrophotometer depend upon the Beard-Lambert law. In what happen in UV visible spectrophotometer, it observe it depend upon the matter absorb the light, and the electron excited from the lower state to higher state. So after we have done the FTIR analysis, and we know that the FTIR stands for the Fourier transfer infrared spectroscopy. It takes place in the range of 400 to 4,000 meter. As you can see, there are so many peaks. The peaks take place in the region of 3,000. It confirms the formation of OH bond, and the peak in the region of 2,000. It confirmed the formation of alkenes, but the peak around in the IR region from 4,000 to 6,000, it confirmed the formation of metal oxide nanoparticles. So we can say that particularly we can say that the FTR confirm the presence of functional group, that the metal attached to the biological part. So after we have done the XRD, which is the main part. XRD means the X-ray diffraction analysis, which confirm the whether the structure is crystalline or amorphous. But in this study, the structure is crystallized. As you can see, the peaks the XRD analysis we have done at the 2 theta from 20 to 80 degree. As you can see, there are so many peaks, and we also calculate the particle size. The particle size is about 14 is around approx one peak particle size is around 40 nanometer. But we have done by using the Debye-Scarrow equation, that is the beta, that is V is equal to the k lambda upon b cos theta. So we can calculate the particle size. So in this study is a 40 nanometer. After we go for a DLS analysis, this is a dynamic light scattering analysis. Dynamic light scattering is depend upon the Brownian movement. So in this study, the particle size ranges from the 30 to 70 nanometer. So all these studies important for the characterization of nanoparticles. So after we have done the SAM analysis, that is a scanning electron microscopy, which predict the morphological structure of the particles. So in this study, the particles are somewhat aggregated, but if we focused on the one particle size, it's showing the flower-like structures. So after we have done the EDX analysis, that is energy dispersive X-ray analysis, which confirm the element composition present in the sample. So in this study, the zinc is found to be 73% and oxygen in 26%. So after we have done the last study, that is the stability study for stability study of the nanoparticle, which we confirmed by the UV visible spectroscopy. But we have done the study for the 1 month in the interval of 7 days. So 0 days is that day when we have prepared the sample. So we have taken the reading the interval of 1 week. So you can see there is a peak formation at 340 nanometers. So we can say that the nanoparticle is stable up to 1 month. So here's the characterization study. So last we have done the biological activity, that is called the anti-cancer activity. So in this study we have taken the 2 cell line, HT cell lines and HeLa cell line. HT cell line is the human colon cell line, and HeLa cell line is the cervical cell line. Cervical cell line is also called as the immortal cell line because it will divide, it will not die, it will divide continue. So what we have done, we have cultured the cell in DME media. DMEM stand for the Dublusco modified eagle medium, and supplement with the 10% fetal FBS, fetal bovine serum. This is the supplement to grow for the cells, and then we also added the antibiotic. FBS is necessary because it help in cell dividing. So after we kept the cell in 5% CO2 incubator, 37-degree temperature, so cell can divide, so cell can grow. Sorry. So after we have done the assay, that is called the MTT assay. MTT is the most common assay used for the anti-cancers, or we can say cell viability test. So in this we have done the 6-step cell seedling, MTT reagent, incubation, reaction, and the reading. So cell seedling means we have taken the 96 well plate, and then when seeded the cells in this plate. Then after we added MTT reagent, then we have done the incubation for 3 to 4 hours. After the incubation of 3 to 4 hours, what we have, there is a reaction, that is the MTT reagent is converted into the former zinc blue in the presence of mitochondrial dehydrogenase enzyme. So after that we have taken a reading around 590 nanometers. So here is the percentage. So how we calculated the OD of sample minus OD of control divided by OD of control into 100. So what happened in the 96 well plate? If the purple color, the purple color show the viability of the cell, and the color in pink color it show the non-viability. That means the cell death. So as you can see in the figure 12, first is the HT29 anti-cancer potential of the HT29. So as you can see, we have taken the different concentration from 25 to 200 microgram per ml. So with increase in concentration, there is a cell death take place. If we talk about the HT29 colon cell lines at the concentration of 200 microgram per ml, there is a 57.6% of inhibition, or we can say the cell death. If we talk about the HeLa cell lines, in this there is a same thing happen. Within increase in concentration, there is the cell death take place. But in case of this, there is a 65.6 cell death take place. So here is we have done the in vitro study. So here is the overall conclusion. So overall, what we concluded, the green synthesis is better as compared to the chemical method, and so after that we have done the characterization studies whether the sample is good, is in the nanoparticle form or not. So after that we have done the biological study for the cancer cell line. So overall we can say that the green synthesis is good as compared to the chemical method. So in further we can go for the in vivo study also. Thank you.
Yeah, thank you so much, Dr. Kanika. You have made a good presentation.
Thank you,
So
sir.
let us have some questions on this talk. The audience, please. Any question from the audience? Okay, so if there is no question, then let's move on to the next speaker.
Okay, thank you, sir.
Dr. Preeti Jain from Department of Chemistry and Biochemistry, School of Basic Sciences and Research, Sarda University, Kochi, Kerala. Madam, are you there? Yes, Dr. Preeti Jain.
Yes, sir. Good afternoon to all. Yes, sir.
Just
My
share our,
student is sharing this screen. Medu,
yeah,
Medu,
please.
can you kindly unmute her?
Yes, my name is Madeline, you can say, and I've worked under Dr. Preeti Jain, and the topic of my presentation is fabrication of metallic nanocomposites and their versatile application. So this is my contents, that is introduction, green synthesis of nanoparticles, application of nanocomposites, methodology, and the conclusion. So in the introduction, silver nanoparticles which was embedded on the nanocomposites, they have been reported to have a substantial antibacterial capabilities because they can be used repeatedly for more stable materials, and dyes they have also been used to reduce the environmental impact of synthetic dyes because they pollute as they pollute the water. And titanium dioxide they have been researched by as a heterogeneous catalyst for the restoration of damaged environments. Since it is a traditional method, it is sensitive and selective, but it also necessitates the use of complex tools and it takes time. Since because of their simplicity, they are also a good alternative. Green synthesis of nanoparticles. Green synthesis of nanoparticles, they are ozone-friendly and less detrimental reagents. Nanoparticles can be made in a number of ways in biological, physical, chemical, and combined methods. Ball milling is also one of the example of physical methods, whereas sol gel is also another example of chemical methods. Whereas the biological approach of making nanoparticles is a one-step bioreduction, which uses fewer energy and is environmentally beneficial. Green synthesis, which is natural, it is used to treat cancer and is also used in hospital, homes, water treatment, and many other fields because of the unique physiochemical property. Application of nanocomposites. Nanocomposites, they have a wide range of applications in which some of them are like they can be used in thin film capacitors for computer chips. They are also used in biomedical and in energy storage. They are also used in food packaging, oxygen and gas barriers, and also in the use of wastewater treatment, etc. Synthesis of silver nanoparticle by bark extract. The bark that I've used was from the tree of Acli marmelos. So firstly, we have prepared the bark extract by using double distilled water, and we have made the extract basic by adding 0.1 normal of sodium hydroxide. And then we took 10 ml of silver nitrate and 3 ml of extract and added a small piece of cotton and heat it in the magnetic stirrer for at 70 degrees Celsius for 15 minutes. And after it was done, we separated the solution and the cotton was kept in the hot air oven for drying. So after it was done, the cotton was ready to use for antibacterial activity. Characterization of silver nanocomposite on cotton fiber service. SEM was used to visualize the series of its biosynthesized nanocomposites. The same picture indicated a spherical surface morphology and an even shape. In EDX scanning, it indicated the existence of silver and other components covering the clusters of silver. So the surface images of cotton zinc synthesized was better than XC2 synthesized cotton silver. Results of antibacterial activity. The Dix diffusion technique was used to analyze the antimicrobial activity. So the fabricated cotton silver and cotton zinc were tested against gram-negative Pseudomonas aeruginosa and gram-positive SRS using an agar well diffusion method. So the organism was subcultured in nutrient broth at 37 degrees Celsius and was incubated overnight. So after the incubation period, the antibacterial activity was detected by measuring the zone of inhibition, in which C, which is the zinc silver nanocomposites, showed better zone of inhibition as compared to the XC2 silver nanocomposite and in situ silver nanocomposite. Zinc is natural, low toxicity material and is also environmentally friendly. Synthesis of titanium dioxide nanocomposite. So for this, we have prepared the titanium dioxide by using distilled water. We took 40 ml of titanium dioxide and 10 ml of silver nitrate and 10 ml of extract and sonicated at 70 degrees Celsius for 30 minutes. So after slowly, there was a brown color suspension started appearing in the mixtures, which revealed the formation of nanocomposite. So the resulting solution was centrifuged at 10,000 RPM for 45 minutes. The supernatant was discarded and the nanoparticles were tried in the oven for semi-analysis. And later the TiO2 nanocomposites are produced. The same studies of TiO2. The morphological structure of TiO2 nanoparticles were irregular morphology, had an irregular morphology and was spherical in shape. Optimization of reaction parameters. UV visible spectra of the optimization studies. First one is the pH. So we took different pH, and the original pH of the extract was 8. So the dye from a different pH showed that at higher pH value, the reduction of dye showed good result as compared to the lower pH value. So 11 pH showed a better result. Number B, that is concentration of catalyst, different concentration of catalyst. So the prepared solution was placed in the shaker and kept in the visible light for 3 hours. So the rate of breakdown decreased as the catalyst concentration was increased. So 200 microliter showed the most prominent result. C, that is concentration of dye. The concentration of methylene blue was systematically changed, which was used to evaluate the effect of concentration of dye by using titanium dioxide, silver nanoparticle as catalyst. So in different dye amount, the concentration of dye can be altered so as to check that the photocatalytic activity we have used 1 ppm, 5 ppm, 7 ppm, and 10 ppm. So for 1 ppm of dye solution, the catalyst degraded by 95%, and 5 ppm by 75%, and 7 ppm by 49%, and 10 ppm by 30%. By using 200 microliter of catalyst in the visible light. In conclusion, the silver nanoparticles, which were synthesized by using bark of the Ackley marmelos tree, were characterized, and zinc sulfate showed good antibacterial activity on the silver nanocomposite on cotton fiber surface, and titanium dioxide nanocomposites were synthesized and characterized, and the photocatalysts of dye degradation, they showed good result, excellent result, which was also used in the treatment of polluted water. Thank you.
Okay, thank you so much, Ms. Medulno Kenesi, for your talk. If there is any question from the audience. Yes, please, any question?
Yeah, yes, sir.
Yeah, please.
Can I ask one question, sir?
Yes, please, go ahead.
Actually, madam, about this titanium dioxide composite with zinc, silver, is it actually, did you take any XRD on that sample?
Yes, sir. Can you please repeat the question?
For this titanium dioxide composite with silver, did you take any XRD? Is it direct crystalline?
No, sir,
it is not crystalline.
Taken the XRD. Sir, it was not exactly crystalline.
Yeah, because from your same image, I think it is not easy to identify.
Yes.
And why
yes,
there is antibacterial activities on this compound? Is it because of silver or is it because of titanium?
Sir, for the antibacterial activity, I didn't use titanium. I have used silver and zinc. So.
Okay. Okay. Anyway, thank you, sir.
Okay, so thank you so much again, Ms. Kenesi, for your talk.
Thank you.
Let's move on to the next speaker, Dr. Pushpalatha C. From Ramaiah University of Applied Sciences, Bangalore. Yes, ma'am. Dr. Pushpalatha, ma'am, are you there?
Good afternoon. Yes, sir. Can
yes,
you hear
ma'am.
me?
Can you please share your? Yeah, I can hear. Yes, please share your screen.
Actually, I'm sharing, sir. 1 second.
Yeah.
You can see the PPT, sir.
Yes, ma'am. Can you please make it? Oh, yes, yes.
You can
Yes,
see my
coming up.
PPT, sir.
Yes, it's there, ma'am. Yes. Yeah, please go ahead and make your presentation.
Okay, and I start. Okay. Good afternoon, everyone. I am Dr. Pushpalata, Associate Professor from Faculty of Dental Sciences, Ramaya University of Applied Sciences. I thank the organizing committee of International Online Conference on Nanomaterials 2022 for presenting a paper titled Application of Nanoparticles in Management of Oral Diseases. So in the field of dentistry, there are various compounds that are used to protect the teeth. The quality of the dental biomaterials are improved because of recent innovations in biomaterials and their application in dentistry. Thus, it is improving the health care of dental patients. There are wide applications of nanoparticles in dentistry in the form of nanocomposites, nano light curable glass ionomer cements, nano impression materials, nanoparticles coating on dental implants, nano based bone replacement cements, nano encapsulation, nano needles, nano diagnosis, etc. But recently, it is found that natural products are also used in the prevention of dental caries because of the presence of some bioactive phytochemicals and which exhibits antibacterial property and which are effective in remineralizing the tooth structure. The coca bean, which is a natural product, is a rich source of arginine, glutamine, leucine, flavonols, proanthocyanins, and certain minerals and methylxanthines like theobromine, caffeine, theophylline. The coca bean extract possesses certain caries inhibitory substances like theobromine, which exhibits anti-glucosyl transferase activity, which is necessary for inhibition of dental caries. And it also reduces the rate of acid production, biofilm formation, and also promotes enamel regeneration. So, we selected the coca bean in the present study because there is a myth saying that the chocolate which contains the coca, it's a cariogenic, means it is the main culprit for the formation of caries. Actually, the studies reports that the coca, it is karyostatic. Actually, it is not cariogenic. But this showed that the sugar which is added into the coca makes the chocolate cariogenic, leading to dental caries formation. So, based on this background, we developed a study with the aim to assess the effect of novel theobromine nanoparticles based dental varnish on remineralization of early enamel caries lesions. With the objectives: isolation of theobromine from coca beans and its characterization, in silico identification of molecular targets of isolated theobromine against selected cariogenic microorganism, and formulation of dental varnish using theobromine nanoparticles, and assessment of antibacterial activity and remineralization potential of developed varnish. In order to fulfill the objective, the methodology was like this. First, the coca was collected from Puttur, Mangalore district, and this was ground to a coca powder, and it was subjected for defatting to remove lipids, waxes, sterols, and non-phenolic compounds. After defatting, the coca was subjected for extraction using Soxhlet extraction procedure. The residue obtained after Soxhlet extraction procedure was further concentrated to obtain a coca mass extract. So In order to confirm that this coca mass, whether it contains theobromine or not, we did HPLC analysis. The HPLC analysis confirmed that the coca mass extract contained theobromine on comparison with the peak of the theobromine standard. After confirming that the coca mass contains theobromine, then we proceeded with isolation of this theobromine from this coca mass using preparatory HPLC. After isolating the theobromine compound, which is shown in the diagram, which was a white crystalline powder, then we wanted to confirm whether the isolated compound was theobromine or not. So we did UV spectra, FTIR, mass spectra, and NMR. The peaks of the theobromine, the isolated compound, correlated with the peak of the standard theobromine and confirmed that the theobromine, which was the isolated compound, was theobromine. After that, in silico approach was carried out in order to identify the molecular targets of isolated theobromine against Streptococcus mutans, which is considered as a main organism for the for dental caries formation. So the study reported that there was a binding affinity against superoxide dismutase and against glucan sucrase enzyme. And even it had a surface binding interaction against Streptococcus mutans sortase A enzyme and streptococcal surface adhesin enzyme. So all this suggested that the theobromine had an antibacterial activity. After confirming that it had an antibacterial activity, we proceeded with the formulation of dental varnish. First, we prepared the theobromine nanoparticles using probe sonication method. The particle size of the theobromine was confirmed using HCM analysis, where the particle size was ranging from 60 to 80 nanometer. And later, the dental varnish was developed using theobromine nanoparticles, agarose, benzoin, and ethanol. So the developed varnish is shown here, which was white in color. After development, we characterize the developed varnish for physical property, mechanical, rheological, and chemical properties. The macroscopic evaluation was done for color, smoothness, and homogeneity. The studies showed that it was white in color, smooth, and homogeneous. Macroscopic evaluation using optical microscopy, scanning electron microscopy, and atomic microscopy showed that the formulation has a uniform spread on the surface of the tooth with uniform distribution of the particles. The developed formulation was alkaline in nature. The drying time under natural and compressed air showed that the drying time was 2 to 3 minutes. It had a satisfactory spreadability, extrudability, water resistant, gel time, gel temperature, and sufficient mucoadhesive force to the tooth structure. The viscosity test using viscometer showed that the developed varnish was neither too thick or neither too thin. The in vitro study showed that there was a sustained drug release of theobromine from the formulation. This is a microscopic evaluation of the formulation under dark field and contrast microscope, where you can see there is a uniform distribution of the particles on the surface of the tooth structure. This is a SEM analysis and AFM, where you can see there is a uniform distribution on the tooth structure. The biocompatibility of the developed varnish was also assessed at different dilution, and at a dilution of 20%, we can see there was a cell viability of 96%. At a dilution of 2.5%, the cell viability was 82%, suggesting that it is biocompatible and can be used for oral application. Next, the antibacterial activity of the developed varnish was assessed using agar well diffusion method against Streptococcus mutans and Lactobacillus. So the developed varnish showed an antibacterial activity against these two organisms, but slightly compared to that of the standard what was used. Coming to the remineralization potential of the developed varnish, to assess the remineralization potential, first enamel blocks were prepared using a extracted tooth. And they were divided into 3 groups. One is control, standard, and developed varnish group. And the mineral loss, micro hardness, and calcium and phosphorus level of the sample was determined at baseline, after demineralization, and after remineralization. The baseline reading means before subjecting to any treatment, the normal tooth values were taken for mineral loss, micro hardness, using Vickers micro hardness tester and using nano indented tester, and calcium and phosphorus level using SEM. After baseline recording, then the tooth samples were subjected for demineralization for 7 days. That is creating an artificial enamel lesion on the samples. After demineralization, again the samples reading were recorded for mineral loss, micro hardness, and calcium and phosphorus level. After demineralization, the tooth samples were subjected for remineralization, means treating the tooth with the selected groups. After remineralization, the tooth showed that the mineral gain using diagonodent reading showed that there was an increase in the mineral gain after remineralization. Here you can see the blue bar suggests the baseline reading, the red color suggests the demineralization reading, green one suggests the remineralization reading. If a lesser value indicates that there is a mineral gain. So you can see that at the red line, the value is more, suggesting that there is a mineral loss. But the green one, after remineralization, the value is reduced, means there is a gain in the mineral. Similarly, the surface micro hardness was assessed using depth sensing indentation. Here, you can see that after remineralization, the value of the hardness was increased compared to the demineralization. Even the elasticity of the tooth also was increased after remineralization. Coming to the mineral profile, that is the calcium and phosphorus level after remineralization, using developed varnish showed that there was an increase in the calcium and phosphorus level after remineralization. Coming to the assessment of the surface morphology of the tooth after remineralization, you can see at the baseline the surface of the tooth was normal without any microporosity. After demineralization, you can see that there is a small microporosity created on the surface of the tooth. After remineralization, that is after treating with the developed varnish and with the standard and control, there was a lot of change in the standard and the developed group. In the control, there was not much change in the surface morphology. You can see that there is a microporosity was present like that only. But in the standard, you can see that the porosity was reduced and the surface has become slightly smooth. Whereas in case of a standard, which is mentioned as F1 group, you can see that the microporosity was completely removed and there was a slightly shallow depression. This suggests that there is a remineralization of the tooth structure using the developed varnish. So, coming to the conclusion, I conclude saying that the developed novel theobromine nanoparticle-based dental varnish has remineralization potential and can be recommended for the management of early enamel caries lesion. However, further clinical trials are needed for long-term effects. Thank you.
Thank you so much, madam, for nice presentation. Now we can have a few questions on this talk. Any question from the audience, please? Okay, so if there is no question, so let's move on to the next speaker, Dr. Susmita Das. Are you there, ma'am?
Yes, I'm here.
Okay.
Am I audible?
Yes, ma'am, you are audible. Please share your slides.
Yes.
So, Dr. Susmita Das, ma'am, is from Department of Chemistry, MIT University, West Bengal, and her topic is on ionic liquid nanoplastics future pharmaceuticals.
Is my presentation visible, sir?
Yes, ma'am. Please make it on full screen. Yes, please go ahead.
Okay, thank you. Um, Good afternoon, one and all present. Today, the topic of my presentation is ionic liquid nanotheranostics, future pharmaceuticals. I am Dr. Shushmita Das from Department of Chemistry, Amity Institute of Applied Sciences, Amity University, Kolkata. So, at first, I would like to talk about ionic liquids, what ionic liquids are. Ionic liquids are basically organic salts which are comprised of some inappropriately sized cations and anions, which are within a compound through ionic interactions. So due to the inappropriate size of the cation and the anion, they undergo frustrated packing, and as a result, these are low melting organic salts. The first ionic liquid that was discovered was by Paul Walden, and the ionic liquid was ethyl ammonium nitrate. This ionic liquid was found to possess a melting point of 12 degrees Celsius. Hence, it was a liquid at room temperature. Later on, for certain number of years, the ionic liquid research remained stagnant, and after that, in 80s and 90s, the ionic liquid research once again had gained attention, and then people came up with some more other kinds of ionic liquids like imidazolium, pyridinium, pyrrolidinium, and different other ionic liquids, which were generally referred to as the second generation ionic liquids. These ionic liquids, some of them were found to be room temperature liquids and some of them were room temperature solids but had low melting point. Their melting point generally lied below 100 degrees Celsius. So ionic liquids are generally defined as organic salts that have melting point below 100 degrees Celsius. And they are categorized into two different categories. One is the room temperature ionic liquid. Room temperature ionic liquid is the one which are liquids at below 25 degrees Celsius, and frozen ionic liquids which have melting point between 25 and 100 degrees Celsius. So why are we interested in ionic liquids? What is the purpose of knowing about ionic liquids? These are some of the common cations and anions that have been used to design different kinds of ionic liquids, although ionic liquid research is no longer restricted to these particular cations and anions. And now we are interested in knowing what are the specific properties of ionic liquids that make them so interesting. So ionic liquids, as I mentioned, that some of them are room temperature liquids, and they have both non-polar and polar interactions within them. So they can solubilize wide variety of solutes ranging from very hydrophilic, very polar solutes to very non-polar solutes. Hence, ionic liquids can serve as good solvents and they can replace organic solvents. Why do we want ionic liquids to replace organic solvents? Organic solvents are generally volatile in nature and they cause environmental pollution. Some of them are also carcinogenic. So ionic liquids, these are viscous liquids. They have very low vapor pressure and hence they are almost non-volatile in nature. Hence, ionic liquids, if they replace organic solvents, they can serve as green solvents. Other than this solubility, ionic liquids also exhibit medium to low conductivity and a wide electrochemical window. And this makes ionic liquids as good electrolytes. Ionic liquids also serve as catalysts in various reactions. But apart from these properties, one of the very important property of ionic liquid is that they are highly designable. We can design them as per our needs. And due to the designability of the ionic liquids have found applications in various areas, such as they are used as active pharmaceutical ingredients, they are used in drug delivery, as nano carriers, in biosensing, as catalysts, as electrolytes, and different various other applications. Now, here in this talk, I am actually interested in the pharmaceutical properties of ionic liquids. And from the point of view of pharmaceutical properties of ionic liquids have been used as potential drugs and as drug delivery vehicles. So, in this particular talk, we are going to focus on the use of ionic liquids as potential drugs. Now, ionic liquids have been reported to exhibit antibacterial, antiviral, anti-inflammatory, antifungal, anti-cancer, antipyretic properties. For example, there is another advantage of designing drugs using ionic liquids is that we can combine two or more therapeutic properties within a given molecule by designing an appropriate ionic liquid. For example, if we look at this particular drug, benzalkonium, which is an antibacterial molecule, this ion, when combined with ibuprofenate, which is an anti-inflammatory molecule, then benzalkonium ibuprofenate can serve as an antibacterial, anti-inflammatory drug. Similarly, if you look at this benzalkonium, which is antibacterial, and sulfacetamide, which is anti-acne drug, when we form benzalkonium sulfacetamide, this may serve as an antibacterial, anti-acne drug. So in this way, we can combine multiple therapeutic properties into one molecule by forming appropriate ionic liquid. But it is not necessary that every time we combine two ions, we get the properties of the two ions. Sometimes the properties may deteriorate upon combination. So it is important to synthesize, to develop, design new ionic liquids, to develop them, and to study their properties to understand which combinations are working. So in this particular work, we have focused on the development of some phosphonium-based antibacterial ionic liquids and understanding their mechanism of action as well as other associated properties. Now, why are we interested in this phosphonium-based antibacterial ionic liquids? First of all, there is a continuous search for the development of new antibiotics. And that is because of the threat that the entire world is facing from the drug-resistant or the multi-drug resistant strains. And phosphonium-based ionic liquids, these are highly thermally stable. And if we design them in a proper way, they can be very non-toxic. So this kind of phosphonium ionic liquid based antibacterial drugs have been, some of the antibacterial molecules have been researched in this particular work. So here there are some of the phosphonium cations, among which we have taken the trihexyl tetradecyl phosphonium chloride. This is a commercially available phosphonium cation. And we have synthesized these ionic liquids, these 4 ionic liquids, using this phosphonium cation and the different anions. In the top 2 ionic liquid designs, you can see that we have a fluorescent anion, which is a dianion in the middle, and we have 2 phosphonium cations attached to this fluorescent anion. And then in the second design, we see that there is this is a monoanionic form of the fluorosinate, and to this the one phosphonium cation is attached. And in the third and the fourth designs, we see that in the third one we have the the phosphonium cation linked to an ampicillin anion, and in the fourth one we have a phosphonium cation linked to a dodecyl sulfate anion. So now when we examined their antibacterial properties, first of all, when we synthesize them, we found that there are certain differences in physical properties such as physical state, color, when we in comparison to the starting material. For example, the TTP2FL, this was a jelly-like orange-red liquid, orange-red substance, whereas TTPCl was a colorless liquid. And similarly, sodium ampicillin is a solid and TTPCl is a liquid. TTP ampicillin is a jelly-like colorless substance. Similarly, if we look at the solubility, the TTPCl was water insoluble, but TTPHFL was sparingly soluble. TTP2FL was poorly soluble in water. So the solubility, the other properties, physical properties, and their biological activity changes upon forming different combination of ionic liquids. As you can see here, we have kept the cation the same, and we have only altered the anion. Now, in our antibacterial assay studies, we have found that the TTPCl, which was one of our starting materials, and Na2FL was our second starting material, the TTPCl showed an antibacterial activity at a higher concentration with both E. coli and S. aureus, while Na2FL did not exhibit any antibacterial activity. But TTPHFL and TTP2FL both demonstrated very prominent antibacterial activity at much lower concentrations. And we also find that TTPHFL was more selective towards E. coli, while TTP2FL was more selective towards S. aureus. So in this case, we find a synergistic effect. While in case of TTP ampicillin, the concentration at which antibacterial activity was observed was higher in comparison to sodium ampicillin or TTPCl. So, and same was the case of TTP-SDS. So we find that in this case there is an antagonistic effect. So as I mentioned, that it is always not necessary that the properties are retained in the ionic liquids. The properties may deteriorate. So it is important to design and develop these ionic liquids and examine their activity. Now, this was a scanning electron microscopic image of the action of TTP2FL on S. aureus. In the right, the figure A shows an untreated S. aureus, and in the left, in the figure B, we see the drug treated S. aureus, that is TTP2FL treated S. aureus. So as we can see from the image, that in A, where the cells were untreated, the cells were intact and they had a spherical morphology. But when they were treated, the cells lost their integrity, and the cell wall seems to be ruptured, and their morphology had also changed. So this shows that the cell wall is getting ruptured, probably by the action of the drug TTP2FL. So we wanted to know we wanted to understand the mechanism of action of these drugs on these bacteria. That is, how do they kill the bacteria? For that, we had performed certain docking studies. These studies were actually performed by my collaborator my students had worked under her supervision to do these studies. In this docking studies, we had actually docked the various RNAs and the cell wall of the bacteria with the different drugs. And the reason why we had done this docking studies, because in some of the cases, the drugs may act by binding to the RNA DNA and thereby inhibiting the protein synthesis, or they may bind to the cell wall and they may inhibit the cell wall maturation. So this might be some of the probable mechanisms of antibacterial activity of the drugs. And when we did the docking study, we found that the design drugs TTP-HFL and TTP-2FL, they demonstrated highest docking score with the bacterial RNA 1xxt. 1xxt is the RCSB code for the bacterial E. coli RNA. And here we see that the docking score for TTPCL and Na2FL was much less in comparison to these ionic liquids, which implies that the binding was much stronger for TTP-HFL and TTP-2FL in comparison to TTPCL and Na2FL. We also had the docked with the bacterial cell wall, and from the bacterial cell wall docking results, we find that we had actually fragmented the cell wall into two parts because it was difficult to dock it with the entire cell wall. And with both the fragments, we find that the TTP HFL and TTP2FL had much higher docking score, with TTP2FL having the highest docking score, and TTPCL and Na2FL, which were the starting materials, had much lower docking score. So we can estimate from here that these drugs are actually binding to the cell wall and thus exhibiting its antibacterial activity. There is a probability that they may also bind to the RNAs, and they may exhibit their antibacterial activity in that pathway as well. But the more chances are their binding to the cell wall, as the trend matches our result. The trend of docking score matches our experimental results. So this is another study where we have seen this TTP2FL are actually nanoparticles. They actually form nanoparticles in dispersion, and these are pH sensitive fluorescent nanoparticles with pH dependent color change. So when we actually decrease the pH from the physiological pH to pH 2, we see the particle size increases from 28 or 30 nanometer to microns. So these kind of nanoparticles pH sensitive nanoparticles can also be used as pH dependent drug delivery and also in detection purposes, that is diagnosis purposes. Their fluorescence properties can be used for the diagnosis purposes, or their variable absorption with variable pH property can also be used for the diagnosis purposes. And hence we can say that these TTP2 nanoparticle, which has inherent antibacterial activity, can also be used as a drug delivery agent, drug delivery vehicle, as well as can also be used as a diagnostic tool. So they can be used as nanotheranostics. They can be termed as nanotheranostics. So from our studies, in conclusion, we can say that the phosphonium ionic liquids demonstrate varied extent of bactericidal effect, and the bactericidal effect depended upon the type of anion as well as on the number of phosphonium cations attached to the anion. And we also see that the number of phosphonium cations actually decides the selectivity of the resulting ionic liquid towards a specific kind of bacteria, such as E. coli or S. aureus, that have been studied here. And we have also tried to understand the mechanism of action of these antibiotics or these antibacterial agents. So I would like to acknowledge Amity University Kolkata for all the infrastructural support. I would like to acknowledge my students, Anindita Paul, Abira De, and Avitagni Roy, who were a part of these studies, and my collaborator, Dr. Devavani Ganguly, who has done the docking studies, who had actually supervised these docking studies, and ICN 2022 for giving me the opportunity to speak here. Thank you. I would appreciate any questions.
Okay, thank you, ma'am, for very nice presentation. And we can have now a few questions on this talk from the audience, please. Any question from the audience? Okay, so yes, sir, please.
Can I ask a question?
Yes, sir, please go ahead.
Hello.
Yes, sir, please.
Please go ahead. No problem. I have a question. Using ionic liquid, can you also improve upon the drug solubility? You know, ionic liquid has been quite a lot used for drug delivery system. So drug solubility, can you increase using ionic liquid? Because some of the
as these ionic liquids, you are saying ionic liquids to be used as drug carriers to solubilize the drugs. Yes, ionic liquids, they have been found to be possessing very good solubilizing properties for various kinds of molecules, and because they are amphiphilic in nature.
Yeah, exactly. And my other question, my concern is, does it affect the sustained release pattern?
Does it affect?
Release pattern. Does it affect the sustained release pattern of the drug, ionic liquid?
Ionic liquids are to some extent self-assembled systems.
Will they affect the release pattern of the drug?
Yeah, so in that case, if they are forming some sort of self-assemblies, they may affect, although I have not studied that myself.
Thank you. Very good. Thank you.
Thank you.
Okay, thank you, ma'am. Again.
Thank you.
Okay, so now this session is come to end, and I thank to all the speakers for their nice presentations, and I also thank to the organizer for giving me an opportunity to chair this session. With these words, I would like to hand over the session to the next chair.
Thank you, Dr. Gautam sir, for
you,
excellent chairing of the session. It was a great sharing. Thank you so much. Now I would like to invite Mahabole Megha and K. Rukmani for chairing the next session for carbon nanostructures.
Hello, madam.
Yes.
Hello.
Yes, ma'am. You are audible.
Okay. So in this session, we first speaker is Asmita Datta.
Yeah. Hello everyone.
Okay.
Hello, ma'am.
Okay. Please continue. Please share your slides. Hello.
Yeah, I'm doing. Yeah, this one. Can you see it?
Not yet. Yeah.
Now?
Yes.
It's okay?
Yes.
So I can start, right?
Yes, you can start.
Thank you. Hello everyone. My name is Ashmita Datta. I am a PhD student in Ariel University, Israel, in the Department of Chemistry, working under the supervisions of Dr. Arya Bodenstein. Today, I like to present my work on laser-induced incorporation of CNDs in graphene electrode to improve its flexibility and conductivity. The novelty behind this work is the incorporation of CND and uses this CND for the laser conversion, for the laser reduction. This work has been published in Flatchem journal recently in May. So you can read this paper in this following link. So basically, what are carbon composites? So carbon composite, when two or material not only mixed, but also the synergistic interaction between them leads to some unique and superior behavior. The advantage of forming the carbon-carbon composite materials are the most of the carbon materials have high mechanical strength and high thermal conductivity. So forming the carbon-carbon composite, it leads to enhance the mechanical strength, thermal and electrical conductivity. As most as the CNTs, the long the tube kind of nanostructure and its exceptional mechanical strength and thermal and electrical conductivity behavior leads to a superior and extremely high application in different field of the chemistry. As the most of the carbon material has porous structure, so it can be also used as gas sensor, gas storage and charge storage, and which can be improvised later as a double layer capacitor EDLC. So basically, the making the composite material leads to increase the performance of the material. The traditional method of RGO-CNT composite preparation requires a long time and high energy, which decrease the product yielding rate and manufacturing efficiency. As you can see in this paper, the Chen group in 2020 reported this work. They mixed the GO and CNT to evenly mixing solution, and they directly reduced it to RGO-CND by Joule heating. Fabricated material used as the current collector, as you can see, for the flexible aluminum ion battery with superior cyclic stability and rate capability. But the traditional method usually involves the heating process, as you can see here. But in our case, we use the laser as a graphitization method. So what is the main advantages of the laser? Laser fabrication in nowadays investigated as the fast energy saving low cost material manufacturing techniques in science. As the laser assisted synthesis methods differs from the traditional method because the heat transfer in laser graphitization happens in micro and millisecond, whereas the traditional method, it takes hours. Laser-assisted carbonization depends on several parameters such as laser wavelength, speed, energy density, absorptivity, and the thermal conductivity. The main advantages of laser, it's the penetration depth due to the long wavelength as compared to the short wavelength laser, but the disadvantage also the poor pinching accuracy and resolution for the long wavelength. So careful considerations of all the parameters is needed when we use laser for the application. So here I put one small video to show that how the laser works. So after the laser conversion, as you can see.
Hello, Asmita madam. Your
Yes.
slides are not changing actually. We
Slides
are
are
not able to see the changes in the slides. They are not moving.
Why? Now you can see.
No change.
How to come to the main page? I can share again.
Yeah, you can share once again.
Yes. Now you can see.
No, we are not able to see the slides. Okay. Now.
Now.
Just change the slide.
Now.
No, you can change the slide actually.
Actually, I'm changing it.
No. We are not able to see that.
I don't know why I stopped presenting. Maybe another.
Can anybody from MGU University can help her? Hello.
Yes. Dr. Yes. Okay.
I'm actually changing it. I don't know why.
It's changing, but can you do the sharing once more? Can you stop sharing now and then?
Okay.
Now you click on.
Now I'm doing it again. Okay.
Yes. Then you have to click on entire screen.
Okay. Wait, entire screen.
Yes.
Yeah, but
then share. You click on that and share. Click share.
No, for me like if I'm doing the entire screen, the share is inactive.
Now you just have to click on that. Your window is. You can see your window over there, right?
Yeah. I can see.
You just click on that. Then click. You activate that. You just click. Give a single click on that, and then share.
Yeah. Okay.
When you see the entire screen, you can see your window, right? Yeah. Now it's coming. Now you go to your PowerPoint, your presentation, you go.
Yeah. Yes.
Yeah. Click on that, you go to full screen. Full screen.
No.
Yes, it's full screen now. And you can, hide that, you can see the hide. There is a bar over there.
Yeah. That is okay.
Yeah,
Now the slide is changing.
Yes, it's changing.
Okay. Thank you so much. So from where I will start actually. Hello. Hi, hello.
You start from where you are showing a video, right? So you can start from there.
Okay. So as I told the laser graphitization, I put one small video to understand how laser works. So you can see the color change of the material before and after laser. Before laser, it was brown in color, and after laser, it becomes black. So we prepared the RGO-CNT composite by laser fabrication. The GO, it's prepared in our lab by Hammer's method. As the CNT is the sp2 hybridized rolled up sheet, so it is actually inert upon the laser irradiation. So one-step modifications of the CNTs is needed. For that, we put the CNTs inside the acid solution of H2SO4 and H2O2 to build the surface functional groups such as CWH group, OH, and C double bond O group inside the CNTs as a functional group. The formations of GO-CNT materials is done. We mix the GO and CNT, and after sonication, we dop cast it on the PET film and dry it. And after laser conversion, as you can see, it becomes brown to black after the laser irradiation. So what is the main thing of this illustrative procedure is that CNTs, it's not usually used for the laser application. It is not laser reductive, but in the first time, 1 or 2 paper you can see for this. But in our group, it is we tried the laser reduction of the CNTs with the GEO. After laser reduction, the GEO becomes RGO, and the CNTs, it's with it, so it is also energized inside the GEO. So the structural analysis of the composite is done by the same and the stem images. As you can see in the same image, the CNTs are on the surface of the graphene sheet. Is the well into and also in the stem images also you can see these CNTs are on the graphene sheet. It's well integrated. The structural integration, as you can see, the CNTs are totally bind with the surfaces of the graphene sheet. Therefore, there is a structural integration made with the graphene and with the CNTs. The characterizations can be done by the Raman spectrum. The 3 peaks usually come for the graphene material, the D band, the G band, and this band at the 2600 semi-inverse region. So the D band is mainly come for the sp3 hybridized carbon atom. The G band is come from the G band is come due to the sp2 hybridized carbon atom. As you can see, as we increase the as we start addition of the CNTs and increase the concentrations of the CNTs inside the RGO, inside the GEO, the ID by IG ratio also started increases, which means the sp2 carbons are decreases. As I said earlier, that the CNTs are very much thermally stable, so it really hinder the conversions of the GEO to RGO. So when the concentration of the CNTs inside the sample increases, it hinders or reduces the conversions of the GEO to RGO. So that's why the ID by IG ratio is also increases with additions of the CNTs inside the sample. So different types of orientations we studied when we come to the application stage. So we take the electrode and take the conductivities and conductivities in the rest state. Also in negative bending and in positive bending. In negative bending, the electrodes of the graphene layer comes closer. It reducing the gaps inside, ease the mobility of the electrons, and thus the conduction happens easily. So the conductivity increases in negative bending. However, in positive bending, the electrodes are pulled apart, expand the gaps, defects which may cause the defects in the carbonaceous lattice, which also lowers the contact points and hinders the electron mobility. So it indirectly reduces the conductivity of the electrode in positive bending. So we tried for the conductivity measurement, we tried in the rest state the RGO without the additions of CNT, and after that we increases the concentrations of CNTs inside the sample. As you can see, the only RGO without the additions of CNTs, the conductivity came 1.8 into 10 to the power 3 Siemens per meter, which significantly increases up to 7.5 fold increase in RGO CNT3, which is 13.51 into 10 to the power 3 Siemens per meter. So after the additions of CNT, conductivity increases upon rest state. For the negative and positive bending also, the relative change we calculating upon bend compared to rest. As you can see, XX divided by S0 is in rest state for the positive bending and negative bending also. At any bending, the conductivity of the composite is higher than the bare RGO electrode. Not only in absolute values, but also relative to the conductivity in rest. Positive band conductivity retention compared to the rest is 0.073 in the positive bending, which is for the bare RGO electrode at 0.82. It 0.82. You can also see the black line which indicate the additions of CNT, the difference in the conductivities between positive and negative bending also decreases. So it means the stability upon the mechanical stress is also increases with the additions of CNTs inside the sample. So I put one video to see the stability upon the mechanical stress with the RGO CNT electrode. As you can see that upon the bending, this is actually the ohm meter. It gives the resistance. So resistance increases means conductivity decreases. So here the resistance increases means conductivity decreases. And when I open the finger, it started decreases the resistance, which means the increase in the conductivity. So after additions of the CNTs inside the sample, the flexibility of these things increases. So flexibility improvement of the RGO-CNT increases. We can check by the cyclic voltammetry data also. This is the only RGO electrode which is upon bending. This becomes like, which is upon bending at 90 degree, which becomes like this. So there is 63.88% retentions in the capacitance. After additions of CNT, this is the RGO CNT electrode, which shows 98.45% retentions of the specific capacitance after the additions of CNT. So we can say after the additions of CNT, the mechanical stress and it's become more flexible and stable upon the mechanical strength. So if you put the stress also, it can maintain the structural integrity, structural integrations of the shape due to the additions of the CNT. So long-term stability of the RGO-CNT electrodes is also done. So RGO-CNT electrode, we take the data in bending state and we kept the bending state for 1 week. And after that, we take the same, for the same electrode, we take another cyclic voltammetry the measurement, which shows 88% retentions in cyclic voltammetry after 1 week of bending. So we can say the RGO-CNT electrode, it's a RGO-CNT electrode is stable enough as it maintains the structures and almost the same. Almost is the same for 1 week. The cyclic voltammetry shows 88% retention in specific capacitance. So from the above study, we can conclude that the novelty of this work, the leisure induced incorporations of CNTs in graphene, which is barely known. Also, we studied our electron by different analysis by STEM, SAME, Raman, XRD, and XPS. As CNT is widely known for highly conductive, it helps the charge transfer through the long network. Thermal stability of CNTs is also known. Due to the strong pi-pi interaction inside the sp2 hybridized structure, the CNT gives high tensile strength and other mechanical properties. Composite preparations with 2D graphene shield also having similar structural arrangement, which improves the flexibility of the graphene sheet. The flexibility is also improved by the high retention in specific capacitance value in composite. Long-term stability of the electrode is also done after 500 times, also shows the retentions of 88%. So at the last, I would like to thank Dr. Arya Borenstein for his constant support and my lab members who are always with me, and ICN 2022 to give me an opportunity to present my work here. Thank you so much.
Thank you, Asmita. It was a great presentation. And session is now open for the discussion. From the audience, if anyone is having any discussion, they can.
Yeah, Asmita, I have one question, a small question.
Yes.
What is the need to prepare the this hybrid material? Why we are adding RGU and CNT? Because CNT already have good electrical conductivity, and we can control the conductivity by adding some group on the surface. So, what is the need?
Thank you for the question. Actually, CNT we can modify that. That's not an issue. The main concept of our work, the RGO, it's a porous material. So with additions of CNT, it increases like that conductivity, because as we have the carbon support, so it increases the conductivity. For the RGO, we just add CNT in very small amount. It's not the total work based on CNT. It's based on RGO. We add CNTs to increase the activity or the properties of the RGO. RGO is the porous material, and RGO has a lot of application as supercapacitor. We can try these materials also for the EDLC or as supercaps. So the main concept is, yes.
But the van der Waals force between the
Mhm.
CNTs will affect the conductivity again if you are adding in RGU. So.
We saw after adding the CNTs inside the material, the conductivity also increases. Like because of the CNT only, it increases.
Yes.
So,
Thank you. Yes. Very good.
Thank you.
Thank you.
Thank you so much.
Thank you, Asmita, for the presentation.
Thank you so much.
I would call Dr. Gautam Singh, Department of Applied Physics, AIAS, MIT University, Uttar Pradesh, Noida. His presentation is on carbon dot induced homeotropic alignment in homogeneously anchored pneumatic liquid crystal sample cells. So you can present.
Thank you, ma'am. Okay, are the slides are visible, ma'am?
So they are visible, but can you make it in a slide share mode?
Yeah, I have done that.
But it is not in slide share.
Okay, let me share again then.
Yeah, share it again with the entire screen if you will select it.
Okay, yes, I did that. And then?
You click on entire screen and then you go to your presentation. Now you can click on your presentation where it.
Okay, is it there, ma'am?
So make it full screen.
Now?
Yes. Now you can present.
Is it moving now, ma'am? Slides are
Yes.
Okay, all right.
You can start, sir.
Okay, thank you so much, ma'am, for this opportunity to present my work on this great meeting which is going on and in the upcoming 3 days. So I am Gautam Singh and currently working as an associate professor at Department of Applied Physics at MIT Institute of Applied Sciences, MIT University, Uttar Pradesh, Noida. The title of my talk is Carbon Dots Induced Homeotropic Alignment in Homogeneously Anchored Nematic Liquid Crystal Sample Cell. So the outline of my talk includes the brief introduction on the nematic liquid crystals, the alignment of nematic liquid crystals, and of course the carbon dots. And then we have the recipe how to prepare these carbon dots doped nematic composites. And then we have results and discussion on these composites, and then conclusion. So as the name suggests that we are talking about the nematic liquid crystals. So once we listen the word nematic liquid crystal, so it's a very important in the sense that all the display devices which are based on liquid crystals are till today are especially made with the help of the nematic liquid crystal only, and these are the simplest liquid crystal ever discovered so far. So how to understand them actually about these liquid crystals? So the liquid crystals are basically highly anisotropic in nature, meaning that the structure of the molecule must be highly anisotropic. And once we have that, then this will induce the anisotropy in all the properties of these materials. So once we come back to this, so when we arrange all these molecules in a certain way, in a, let's say in a space, so due to their structure that they have, they will try to orient along a certain direction. So you can see on this schematic diagram I have shown here that there are a bunch of molecules lined up here, and they have this is the long axis of the molecule. So we can see that the long axis of the molecules, all the molecules are trying to orient along common direction that is called director N, and we can link this as a sort of like saying optical axis in lens that we used to do in 10+2 optics. So it's very important direction, and that tells that we have to measure all the properties with respect to this particular direction. These are basically organic compounds especially, and so here at the bottom I have given one example of the organic compound name as a MBBA. This is 4-methoxybenzyladine 4-butylidene, and this compound actually shows the room temperature nematic phase. So it's a phase sequence right over here. Now, once we understand what are nematic liquid crystals, as I said in the very beginning, that till today, whatever we see, the display devices based on the liquid crystal, they are mainly made of nematic liquid crystals. So what are those applications? So let's have a look on that. So the application started from the display devices, starting from the wristwatch, pocket calculator, mobile phone, desktop monitor, laptop screen. And apart from, we always used to have a feeling that the liquid crystals are only meant for making display devices, but it's not true. Nowadays, the focus is totally gone towards making the devices which are basically non-display, such as a special light modulator, photonic crystal fibers. You can make tunable filters, we can make lenses, grating, and we can also make the lasers, which are actually, we don't need to have the mirrors also. So these are the couple of applications which is actually based on the nematic liquid crystals. Now the question comes, if we already have these sort of applications in the market, then why do we need to actually fuse these kind of nanomaterials in these liquid crystals? So the question comes when we look at all these display devices so far which are available in the market, and they are based on liquid crystals. So they always have some problems, some sort of like saying their switching speed and their optical contrast and many more things there. So to address those things, actually one has to find out the ways. So people have done that. People are trying to use many kind of electronic circuitry and so on and so forth. But on that road, actually, in the last around 10 to 15 years, people come across that this nanotechnology, and they thought, why not to use those nanomaterials in our this very highly rich display industry of liquid crystals. So people have done that job. So in that category, people started doping nanomaterials and seeing that what they can do. And people really found that this very interesting nanomaterials can modify. They can tune the properties of liquid crystal materials, and hence they can also modify the display properties of these materials, and so on and so forth. So I'm not going to go in detail that. One more thing, that before, whenever we talk about the display devices or any device based on liquid crystals, we have to actually think about for the firstly that what is the alignment, because without alignment we cannot do anything with these materials. So alignment is the key point to go ahead with their applications. So especially in this particular field, we actually come across two types of alignment. The first one that I have showed on the left panel of the slide, this is called homogeneous, or we can say planar, and then we have homeotropic, or we can say vertical. So how do we actually understand these two different types of alignment? So this is in the schematic. We can see that we have this. This is called glass substrate or glass plate. And then we have to have this indium tin oxide coated layer, because we really need to make it highly conducting and of course transparent. And then we also coat some sort of polyimide layer. This is the layer which actually is going to align those molecules. So now I have given only, I mean, you can have, there are many polyimides available in the market, then we can use to align the liquid crystals, depending on the material what you have, and of course the structure of the material. So we can see that these are all the molecules of pneumatic liquid crystals. And then if you really if you have a polyimide layer coated on these two glass substrate, and this polyimide layer has a tendency to align these molecules in the plane of the substrate. So that means we can say the director is actually aligned in the plane of the substrate. Then this is called planar, or we can say homogeneous alignment. On the other hand, if the polyimide has the character to align these molecules or the director vertical to the substrate, then this is called homeotropic or vertical alignment. I mean, these two different alignment geometry are basically used in different types of display devices that we can think of. Now, after this, I will directly jump into carbon darts, because the topic includes the carbon darts. We have explored the doping of these darts in this system and try to look at what they are doing with the solar system. So carbon darts are basically, it's very, very, they are carbon nanomaterials which has size less than 10 nanometer, and they have a wide application starting from photocatalyst, phototherapy, drug delivery, cancer therapy, biosensor, and bioimaging. I mean, there are many more applications on these darts actually. But the question comes again that can we use these carbon darts as a dopant to actually tune the properties of pneumatic liquid crystals? So under that framework, actually we thought of trying to actually test the doping, or we can say dispersion. I mean, doping will not be a right word to use here, because doping is something different, but it's kind of dispersion of these carbon dots in a very well-known room temperature pneumatic liquid crystal that is called 5CB, and its name is 4-cyano-4 pentyl biphenyl. This is a very, very important compound, and it has a pneumatic phase actually starting from 22.5 and it lasts until 35 degrees Celsius. So in this is basically going to be like a matrix or host, we can say, and these are the carbon darts which we actually have taken from a collaborator from Raman Research Institute, Bangalore, and they have made these dots, and and the TM shows that the size is actually lying between around 7 to 8 nanometer. So I mean, we have a very simple recipe to make the composites. You can actually weigh some amount of this 5CB compound, and then you can accordingly we can add let's say the different weight percent of these darts, which are actually dispersed in a solvent, and we have used the chloroform, which is a very, very so that once we mix that and put it there in this 5CB compound, and we can mix it with the help of sonication and all the process. And of course, we have to ensure that once we mix this carbon darts dispersants, this solvent into the liquid crystal, we have to ensure that the solvent should not be remained in the mixture at any condition. So we have to evaporate that. And then once it is there, so once we prepare all these composites of different concentration of carbon darts, then first of all, as I said, alignment. So we have to quickly go and look at these and test that what is the effect of these darts on the alignment of this liquid crystal. So the interesting story begins here, that what we were trying to do something different, but when we are doing this experiment, we got some different results. Actually, as I said, that we are using a sample cell of thickness 5 micrometer, which is actually already having the alignment layer, which is going to provide all those molecules. And they say that you have to align in the plane of the substrate. So it's called planar aligned sample cell. So anchoring is already there. But so as you can see, these are the optical textures recorded through a highly resolution optical projection microscope at the room temperature for the pure CB. And of course, these are the different composites right over here. So as we can see, the figure A here, it is a very, this is called the planar textures seen through the optical microscope. And as we keep add on these darts, so I can see that as the concentration is less, very small, then it doesn't really show any change, much change at macroscopic scale. But as the concentration goes up and we reach around close to 0.18%, we start seeing some sort of diminishing of the optical intensity of transmission coming out from the sample, which tells that something is going to happen with the sample at this concentration. And as we go on further, let's say 0.25%, we can see that there is a drastic change in the appearance of the optical texture, which seems to be like it is going to be some different kind of optical state. And as we increase the concentration more than that, the entire sample, which looks bright, and of course it has some color, it is totally converted and goes to the dark state. I mean, dark state means that now the molecules which are lying in the plane of the substrate, now they stand upright. And because we are looking these texture under the cross polarizer, this is a polarizer and this is an analyzer. So in this case, when the molecules lined up like this, because the molecules are aligned in one of the polarizer parallel, so it looks dark. And if you rotate the sample, even if it remains dark, because there is no birefringence in that direction. So after at 0.38% concentration, beyond that, we end up having this dark texture, which really gives a preliminary confirmation that okay, this sample has actually gone to a homeotropic state in the alignment condition. So that was quite interesting, and we thought, how could it possible that we already have a very highly anchored surface, which will be promoting the molecules to align the planar alignment. However, after certain concentration, these darts are able to break that anchoring and ask the molecule to stand up right to the substrate. So that was quite interesting to see. So then after that, actually, we also thought to look at this kind of quantification through different setups, saying, okay, let's look at the optical transmission at room temperature, so we can place the sample cell under cross polarizer and apply some external voltage from the power supply, and look at the optical transmission from each sample. So what we can see here, that here on the x-axis we have the voltage, and on the y-axis we have the intensity of optical transmission, which is coming out from the sample, which is placed in between the two cross polarizers. So we can see this for the pure sample, we have a special, it's a very well-known transmission versus voltage curve that we can see here, and we can see this even remains until 0.25%. You can see this is high. This is the point. This is the highest transmission, and it decreases and goes to dark state here. But as we go on further, more than 0.25, let's say 0.38%, 0.5, and 1.0, what we can see that the intensity of transmission is totally zero. It's close to zero all over the places. I can see it throughout the voltage. And so this is again a confirmation that okay, well, our sample has totally changed from the planar to vertical direction. Now, as I said, that when we look at the sample through microscope, it's kind of looking at the microscopic thing. We don't really see what happens at the molecular scale. So we thought of looking at whatever we are seeing microscopically, we would like to see, is it happening at the molecular scale? So to do that, we have a very good technique called dialectic spectroscopy, because it's really detect the molecular dynamics very nicely. So we have done the dialectic spectroscopy for all these samples, and here is the slide for showing that we have measured this frequency and concentration dependent. This is called relative dielectric permittivity of the pure sample and the composites. So the first case, we have not applied any external voltage outside from the sample, meaning that when we do this dielectric measurement, of course, we have the setup itself will apply some AC voltage of very small amplitude, and that is called the excitation voltage. And then you sweep the sample throughout the frequency and then see how the permittivity changes. So as we can see on the left panel, that this dark line, this dark color, this is called the pure 5 CV. So we can see that the value of the permittivity, almost remains around 6 or something. And then of course you go here, higher frequency, you got a deviation due to ITU and so on and so forth. But as we increase the concentration, we start doping this carbon dart. So of course, in the beginning, what we actually observed that when we have a low concentration, very low concentration, so definitely, I mean, you got a sample which is very highly aligned, and then we are putting something in there. So they are gonna disturb those alignments. So that's how in the beginning, the permittivity is slightly lower as compared to pure sample. But as you keep increasing more and more, then what happens now, the interaction between the carbon darts and the NLC molecules becomes very stronger and stronger. And then now it may happen that the carbon darts is going to leading over those NLC molecules. And that's how you can see that as we increase the concentration, the dielectric permittivity is going to increase. It's increasing actually. And if we really compare, because we already know what are the permittivity of the 5 CV in this case, so we can see that the permittivity really goes up to around 18 or 19. And please do see this here, that whenever we talk about dielectric permittivity, when you look at that, when we quantify, we really have to find out that region in the graph where the permittivity becomes independent of frequency. So that is the point. We can, so all these parts which is be bumping around here, this is actually basically because of the some contribution coming from, we can say, ionic contribution, or maybe you can say we can have the electrode polarization effect also. But overall, what we see that, so the interesting thing is that after certain concentration, what we are seeing that in the beginning itself, these molecules are trying to push those molecules which are lined up in the plane, that they have to stand up. And once they stand up fully, so without applying any particular field to change their orientation, they automatically change the orientation from planar to vertical due to the carbon dots. Now, just to confirm what happened, so we applied 30 volt DC voltage, because that is quite enough to change the orientation molecule. So what we see in the case of pure sample, of course, this is the 0 volt. We apply 30 volt to totally change to homotropic alignment. So if we really look at that, so what we find that at higher concentration, let's say close to 0.3, 0.5, and 0.1, so whatever the permittivity value you have at 0 volt, it is gonna overlap with the 30 volt. So that is again confirming that this sample is actually reached, reached to the homotropic state after a certain doping concentration. This is again a quantification stuff. So we have plotted here with the concentration and the relative dielectric permittivity on the y-axis, which we have selected at 10 kilohertz. As I said that when we have to compare, you have to look at that state portion where the permittivity remains stagnant in that region. So we have taken 10 kilohertz frequency and we plotted that. So what we see that at 0 volt, of course, I mean, we don't apply the field, so it's like no perturbation from outside, only to see the effect of the carbon dots. So in the beginning, start increasing and so on and so forth. And then when you apply 30 volt, what you see that after like 0.38% concentration, you can see these points are they are overlapping together. So now there's no difference between the value of the permittivity at 0 volt and 30 volt. So that's again a confirmation that the sample goes to perfectly homotropic state after certain concentration. Now, I then keep saying that we are talking about the homotropic or vertical element. So whenever you look at the liquid crystal molecule, so it's like a dot, like molecules, like a pen. It's a long axis and this is a short axis here. So now the moment when you align them like this, so what happens? This relax is, it will rotate like this. So this is called the rotation around the long axis, very fast. Now the molecules are aligned like this one here. It's very difficult for them to do this motion actually. Okay, so now when they have this kind of alignment, so what happens now? They can do this kind of motion because all of them is standing like that. So this is called the orientation of the molecule around the short axis. So that is the characteristic feature that if you observe this kind of relaxation in a sample, that confirms again that the sample is in homotropic state. To test that, we have plotted. This is called dielectric loss versus frequency at 0 volt and 30 volt. So you can see that the peak will come somewhere here. So we can see that at the pure sample and 0.03, 0.5, and so on and so forth until 0.1. I mean, these peaks are like way beyond. We don't, and that is not there. But when you increase the concentration, so after let's say 0.3, 0.5, and 1, we can see a very clear peak for the this relaxation, which was not there for the pure sample and until let's say 0.05, and of course 0.1 also is coming a little bit here. But so just to cross check with that, we apply 30 volt bias voltage. So what you can see when it apply 30 volt, the sample already in homotropic state. So definitely you will see this relaxation. So this relaxation is already available at all samples at 30 volt bias. Now this is again a quantification. We have plotted the relaxation frequency corresponding to this particular mode, which we call it this short axis relaxation at 0 volt and 30 volt. So when you have 0 volt actually, so you don't see as very clear peak until probably 0.3. But after, so and beyond that, we are able to see those peaks right over here. But then when you apply 30 volt, because sample is already in homotropic state, so you will seeing that. So this is how it is vary with the concentration. Now the question that is very important, we have asked ourselves that if we are getting this kind of alignment, this is very good result. So is it this alignment what is actually coming because of carbon dots? Is it really thermally stable? Is it really remains stable throughout the nematic phase? So to test that, we have done the temperature dependent dielectric study also. So what we find that whatever we are observing at room temperature with the help of the optical microscopy and then of course the dielectric, that remains throughout the nematic phase, and that was a very good thing that we can say strongly that whatever we are obtaining the alignment because of this carbon dots, this is thermally stable over the entire nematic phase. Now, once we have all these results, we thought how to actually think about, I mean, what could be a possible mechanism to understand the effect of these dots to align the molecules vertically. So, I mean, here are these three pictures we are showing here. And you can see in the beginning that the first picture right over here on the left top corner, that I mean, of course, we are having very less number of carbon dots. This green colors is pairs right over here. So as I said in the beginning that when you have less number of these dots and you have more number of valency molecules, so then of course when they were bumping around in the entire space, and so they will actually disturb. It's kind of disturbing, not supporting something. They will disturb actually here and there, pointing out something like that. But as you increase the the dots, so of course when you do that, so then they will start piling up at the bottom substrate, or and then when you are more and more, so then they will have the interaction between these molecules, and then of course these dots are interacting directly with your polyimide surface, which is highly anchored. And so now the interaction going on, then somehow this carbon dots is going to actually overcome this anchoring force, which is actually applied by this polyimide, which says that no, you have to align parallel substrate. But now when these people got in here, they are overcoming that. And so when we have little more concept, we can see that it will start at the bottom. So first of all, these carbon dots will ask to those people which are lying at the bottom of the plate, say them, okay, well, you need to get up and stand like this. And because as we know that liquid crystals are basically, they are self-assembled system. Now what happens basically, if you actually, whatever you give at the substrate level, like if the one layer say, okay, now stand like this, now automatically this alignment will propagate throughout the sample in the bulk also. And that's how when you reach a certain concentration, let's say 0.38%, and that is quite enough that to break the entire that we already have the surface anchoring, which was causing them to align in the planar substrate, and saying that now you get up and say stand upright. So that will be a concentration which decide. Now they will totally overcoming the surface anchoring force and make them.
Excuse me, sir.
Yes, ma'am.
Yeah. Only you should conclude your.
Yeah, I'm. Yes, ma'am. I'm on the conclusion
Okay.
slide. I'm done. Thank you so much. So as a conclusion, actually, we have trying to understand the doping of carbon dots, that it could change the alignment of a highly anchored planar sample cell to homeotropic alignment, and for the concentration which is quite more than or equal to 0.38%. Now once we got, so the confirmation has been done using the cross-polarized optical microscopy and dielectric spectroscopy, and of course some electro-optical measurement as well. And the thermal stability of such induced homeotropic alignment throughout the nematic phase in these highly anchored sample cell was also confirmed with these techniques. And we think that such induced homotropic alignment could be due to the plausible interaction happening among the dopant carbon dots and these LC molecules, which actually eventually leading to overcome the very strong planar anchoring force. And we certainly believe that such composites will be highly useful for making the tunable electro-optical and sensing devices. This is the team that is involved in this entire work. And this is my group at the MIT Institute of Applied Sciences. And thank you for your kind attention.
Thank you so much, sir. It was a wonderful presentation. Now I would like to audience to ask the questions.
Excuse me, sir.
Yes, please. Yes.
I have one question, sir. You are saying now, like if you are adding a small amount of quantum dots or the carbon dots in your CV, so they are small amount of this carbon dot decreases the permittivity initially, but when you are
in the
adding
beginning
more,
very small. Let's say it's very small amount.
But when you are adding this more amount, it increases the permittivity. So
yes.
Why it is happening? Because surface area also play a role here. Because if you are adding, as we are saying, and when we are going from top to bottom, the surface area to volume ratio increases. So why we are in the initial addition, why permittivity decreases, and why we are not getting the alignment?
No. Okay, let me state this question again. The first thing that, first of all, we have a sample cell, I just mentioned in the beginning, which already has the anchoring, which will force the molecules to align in the substrate. Okay, so we have well-aligned samples in the beginning when we don't have any carbon darts, right? Now, when we take carbon darts, what happens, as I mentioned in the beginning also, because these are the material which are anisotropic. And I mentioned that we need to look at the directed direction n. So the moment when you have this sample planner, you have, this is the n, ITO here, ITO here. You apply the field that we're applying for spectroscopy. Small field is this direction. Okay. So now what happens? This is called the measuring direction of the measuring field direction. It means that if you don't apply any DC bias voltage, this field is very, very small, only excite the dipole. So you are measuring the perpendicular component of the dielectric constant. Okay. Now, when you add a very small amount of carbon darts, so because what happens when you have something very few numbers, something which are adding, so they are very random actually. They can move anywhere. I mean, they don't have any kind of control. So what happens, because you this NLC also has dipole, your darts also has some dipole. So I mean, it's something like they are not going to add on that part. So that's why the slight decrement will happen to your dielectric permittivity. That's what we have seen. Now again, when you increase a little more, so what happens when you have something more concentration, then the packing will be totally different. So somehow things will getting changed. But now the increment what we see, this is not because of actually carbon darts as such. This is happening because the carbon darts has asked the molecule to start from here to try to do like this. Okay. Now what will happen? Now you will not measure the component of in the perpendicular direction. You are measuring the parallel direction. So it has to add on actually. That's why when they become like this, now they feel parallel. So what happens? You will get the parallel component. Okay. So now here the carbon darts are playing the role to change their orientation. That's the difference between this experiment and what people have done.
Thank you. I got, sir. Thank you very much.
Thank you so much.
Thank you, Gautam. Next, we are moving to the participant. That's Dr. Tejendra Kumar Gupta. He is from the Department of Chemistry, Amity University, Noida. And his topic is research progress of strong and flexible carbon nanostructure-based polymer nanocomposites for piezoresistive strain sensors. So you can start.
Am I audible, ma'am?
Yes.
Yeah. So I shared my slides. So thank you very much for giving me the opportunity in this conference. I'm thankful to the organizing team. Actually, I'm Dr. Tejendra Kumar Gupta, Assistant Professor in MIT Institute of Applied Sciences, Department of Chemistry, and I am working actually on polymeric composites for EMI shielding applications and strain sensing applications. So today I will discuss the things like the development, recent advancement in the field of strain sensors, and what are the things I have contributed till date in this part that I will discuss. So actually, how to change the slides? Yes, my slides are changing, ma'am. Okay.
Yes, sir.
Actually, the strain sense, I am working on strain sensor. So first I will discuss what is meant by strain sensor and how we can use these strain sensors in structural health monitoring as well as human health monitoring. So actually, generally in the structure, if we have some kind of structure, like if you will see this railway track or some flyover bridge, so sometimes we put some kind of metallic strain gauges on to measure the health every time. So the strain sensor generally used to measure the some structural failure that takes place in the structure, or same thing happening in the body parts also. So actually just some kind of damages that generally occur in the structure are maybe due to some kind of mismanagement in the constructions, or lack of quality control, maybe sometimes temperature variations, or poor machining. If you are making some parts, so machining things are not proper, so sometimes some kind of small damages takes place because of that. So we need to identify such kind of damages in the structure to protect the structure as well as human life. So structural health monitoring generally improves the life of the structure. If you have any kind of structure, we can improve and we can monitor the the things on the basis of the performance of the structure, so that we can improve. We can improve the quality of any kind of structure for future, so that we can protect the things and human life as well. Huh? So so some kind of importance, like these are the importance. So structural health monitoring has applications in many fields like civil, mechanical engineering, military, aerospace, and power generation, oil and gas pipeline. Oil and gas pipeline, many times some kind of small cracks takes place. Because of that, some these gas pipeline catch fire. So we need to identify such kind of minor cracks before failure. So the structural health monitoring systems are generally used to identify such kind of damage and to monitor the development of these damages using the structurally integrated sensors. So if you will put some kind of sensors between in those parts, so we can identify the initially we can identify the failure in advance, so that we can protect. So if you will see in the previously sudden structural failure takes place, if you will see this bridge in the Korea, and that is in the Korea's Songsu bridge that collapsed in 1994. Recently, I-35 bridge that collapsed in 2007 in USA. This is because of sudden structure failure takes place, and the team, this inspection team could not identify properly the region of the failure. So and if you'll see now people are using this metallic strain gauges, but the problem in the metallic strain gauges is that we cannot, they don't have good sensing sensitivity, means the sensitivity is very low, and also we do not have any such kind of material, do not have any stretchability. So we need to put large number of strain gauges in any kind of structure, that increases the cost. And also you cannot if you will put the sensor in large strains, sensitivity will be poor, and we cannot identify many kind of minor cracks by using such kind of sensors. So people are trying to work, people are trying to prepare such kind of flexible, stretchable sensors, strain sensors, or pressure sensor. They can identify the such kind of damages initially in long range and in the elastic region. The elastic strain limit is very low in case of metallic strain gauges. That is in around less than 3 or 4%. And we are using epoxy resin in many structural components. Epoxy resin also have this strain limit around 4 to 5% only. So in this very less strain limit, we cannot we can identify this failure up to the 4 to 5% limit if we have epoxy resin composites. But higher, if you will go beyond the limit of strain level, we cannot measure that the changes. So we need to people are trying to prepare such kind of flexible sensor, so that we can identify the this damages or minor cracks in the structure in a long strain range, like up to 100% or 50%, like that. Similarly, in the such kind of material can be used in human health monitoring to monitor the motions in the body parts, like knee bending, or if we are moving our fingers, we are laughing, or breast movement. These are all the heartbeat monitoring, and any kind other kind of joint movement. People are also making some kind of sensors in this you can say this body part, like biomedical implant materials, if you see. So implant material generally in the in USA every year more than 1 lakh people generally go for the implantation of such kind of material. So if you make the material like polymeric based material having very good sensitivity, we can identify the cracks in advance, so that we can like protect our parts from the kind of failure. We can protect our part from such kind of failures. Okay. So then, there are kinds of sensors like piezoresistive sensors, capacitive sensors, and piezoelectric. But I am working on piezoresistive strain sensors. So I will discuss on that part, why piezoresistive strain sensors are important, and how we can monitor this change in monitor this sensitivity on the basis of changing resistance. So piezoresistive strain sensors are based on when we are applying some kind of mechanical load, like it may be tensile load or it may be like compressive load. We generally monitor the change in resistance during the application of load. So the change in resistance will provide us the sensitivity. Sensitivity means that is gauge factor that is equal to the change in the resistance divided by the strain. So if we will by using such kind of mathematical formulas, we can identify the sensitivity of the material, and we can also measure the sensing properties. So previously, metallic based material people have used polymeric based structural materials, but now people want to prepare some advanced composite materials. They have very high stretchability, they have good sensing property, they have like also have self-healing property. So if we'll incorporate the self-healing property in any kind of material, we can protect our material from minor damages. If damages are very minor, okay, means micro level damages, we can protect our samples. So metallic foils, as I discussed already, have some disadvantages like complex in the processing, and they have very poor stretchability, low sensitivity around the gauge factor having value around 2, and they are also sometimes sensitive to temperature. So we need to modify the things, and people are working on that. So nanoscience and technology, generally, because of nanomaterials have very high surface to volume ratio, used here to enhance such kind of sensing properties on the basis of the high electrical conductivity and mechanical performance. So if you will see the one-dimensional carbon nanotube and also two-dimensional graphene nanomaterials can be used because they have very extraordinary mechanical performance as well as extraordinary electrical conductivity because ballistic transport of the electrons. So if we will see large number of applications and manufacturing, there are many manufacturing methods for the nanoparticles, top-down methods, all the physical method and bottom-up. So generally people prefer bottom-up methods for the synthesis of nanomaterials. So nanomaterials in carbon nanotube, which are single wall and multi wall, discovered by Sumiyojima in 1991, having very high mechanical property like tensile strength around 500 gigapascal, and they have electrical conductivity around 5,000 Siemens per centimeter. And they also have very density is very less in this case. In case of nanomaterial, they are around less than around 1 gram per cc. So such kind of material can be used, and if we use such kind of material, we can enhance the properties of the polymeric material and can we use such material in making strain sensing devices. So arc discharge and chemical vapor diffusion are generally preferred method for synthesis of single wall and multi wall carbon nanotube, which provides good quality and high yield material. And graphene is another newly discovered material that also have equivalent property like carbon nanotube, and we always try to incorporate graphene inside the material along with the carbon nanotube because these carbon nanotubes have wonderful force of attraction, and these carbon nanotubes generally get agglomerate inside the polymeric matrix. So if we will add graphene structure inside along with the carbon nanotube, this graphene generally used behave as a bridge between two CNTs, and they will not allow them to agglomerate again. So we can get better mechanical as well as this electrical properties. So I have worked, I have designed the structured thermoplastic. I have prepared some kind of material with thermoplastic polyurethane in which I have incorporated the carbon nanotubes. So change in my work is that I have synthesized the carbon nanotube by some different modified method. In the chemical vapor diffusion system, what I have done, I have put the fiber inside, and we have synthesized we have grown the carbon nanotube on the surface of fiber. Okay, so here in this way we got good quality of carbon nanotube having high length and very high aspect ratio. So if you will see in my results, this is actually design of the sensor. How we can measure the sensing property. This is the tensile system. If you will see like instrument tensile testing machine. So if you are stretching, we put the sample inside and we connect two wires. We connect two wires here on the electrode, and then these wires are connected with the electrometer, and we measure the change in resistance in the electrometer when we are starting stretching. So same time we start our system in this mechanical instrument, and same time we start our this electrometer, so that we can compare the data properly, that match properly with the result of mechanical properties. So this is the system design and how we are measuring the things. And because of this very high length, this because of this high aspect ratio, we got change in resistance at very low loading. If you will see 0.05% loading of carbon nanotube enhance our mechanical performance as well as piezoresistive response. Only by adding the 0.05% of CNT inside the polymer matrix, we got the gauge factor around 47, and we got the strain level, means this property up to 30% strain level. This is very good as compared to metallic foil-based strain sensor, in which sensitivity is very low, around 2, and also this strain change level is around 4 to 5% only. So means by using such kind of sensors, we can measure the micro level damages up to 30% strain level. And there are two things here. One is we need to measure the things in elastic as well as inelastic range. Okay, but here I have measured this change in gauge factor only in the elastic range. I have not measured in inelastic range. So same thing, if you'll see the gauge factor for by adding the 0.18% of CNT, gauge factor, the sensitivity reduces here, but we got the property up to 90% strain. And further 0.28% of CNT loading, we got gauge factor, better gauge factor as compared to metallic foil, and also we got the strain level up to 100%. So we are trying to prepare such kind of material. So here the properties was good as compared to the metallic, and I have published this article in Composite Party Journal of the LGWare, and this is the cyclic property that also we need to measure, because if we will not measure cyclic property, we cannot identify the reproducibility and stability of the material. So up to 100% cycle, if you see, our sample is performing good, not excellent, but it is giving good result up to 100% cycle, and also showing single peak pattern. And this reproducibility is also good when we have changed up to in the first cycle and in the 100th cycle, and when we compare the result, the reproducibility we got very good here. Similarly, we have prepared this another composites by solution mixing method, in which we have dispersed this long multi-wall carbon nanotube into the TPU granules. But what we have done change here, we have functionalized this carbon nanotube by some oxidation method by using nitric acid. Okay, and these because if you are not functionalized or carbon nanotube, or because carbon nanotube does not have any active site on the surface. So if you are putting inside the matrix and when you will applying the load, what will happen? Polymer will come out from the, when you are stretching, the carbon nanotube will come out from the polymer matrix, means they will come out, and polymer cannot achieve the properties, or means carbon nanotube cannot transfer their property to the polymeric material. So when you will functionalize these carbon nanotube by any desired required functional group will attach on the surface, you can make a better interface, because interface is very much important to identify the surface to increase the mechanical property. Because if surface will be strong, your nanomaterial will like bond chemically with the surface, and when you will apply the mechanical property, what will happen, your carbon nanotube or any nanomaterial will not pull out from the matrix, and this can improve the mechanical performance. So here what I have done, I have functionalized the carbon nanotube by carboxyl group. I have attached on the surface, and I have incorporated in the TPU, thermoplastic polyurethane matrix, and I have prepared the composite film. You can see here, and we have measured the, you can see here SEM micrographs, scanning electron micrography graph images. Here you can see the magnified area of this part. You can see this CNT has been broken, not pulled out from the surface of the polymeric matrix. So it means we got better surface bonding with the polymeric material or polymeric assembly, and we have actually this confirmed from the SEM micrograph. And if you will compare the electrical conductivity, we got good electrical conductivity here, not equal to the pristine CNT. In pristine CNT, conductivity was very good, but here we got the conductivity that is sufficient to enhance the piezoresistive response as well as sensitivity of the polymeric material. Okay, so you will see the piezoresistive changes and the sensitivity or gauge factor of these TPU nano composites initially in low strain range. If you will see here, up to the 15% strain range, it is showing the linear pattern. Means this is the elastic part, because thermoplastic polyurethane have elastic range up to 16%. So I have measured in this 16%, and at this 16% change in resistance was very good. And we have measured the gauge factor here, which was around 30 to 40% in case of 1.3% CNT loading only. 0.3% CNT loading means, if you will see the curve, that is blue line. If you will see, blue line represent the 0.3% CNT loading. This red line represent the 0.58% CNT loading, and orange represent the 1% CNT loading. So 0.38% CNT loading composite shows better performance as compared to 0.5 and 0.3. And the sample was very good, and we got good sensitivity around in the linear range, that was around 30% and 30, that gauge factor. And I have measured the gauge factor in non-elastic range, or you can say in inelastic range. So gauge factor was very good, around 2600, which was good. And I have measured the sensitivity up to 20 cycle. The sensor shows very good response here, and there was no decrease in the change in resistance and also in the strain. So you can see, if you will see here, the graph was exactly same from 0% to 20%. First cycle and 20 cycle trend in the change in resistance was almost same. So the sample shows very good response. I have prepared the PDMS. This previous work I have published in Composite Part B, Elsevier Journal. And in third part, I have prepared PDS composite for making pressure sensor. So we have prepared the formed structure.
Excuse me,
I am
sir.
just concluding. So we have prepared the formed structure here, and we have measured the sensing, and shows very good sensing performance here. In this case, this is because of the this change in the piezoresistive response as well as the sensitivity is due to the tunnel effect. When we are stretching the polymer film, what happened, initially the CNTs are connected with each other, but after some time some gap increases between the CNT, and due to the tunnel current, we got the good sensitivity in this place. So people are I am trying to prepare such kind of composites like self-filling composite, in which we can fill the crack if we are adding some type of resin. That resin incorporated with the microcapsules. If you will put inside the composite along with the carbon nanotube, that microcapsule filled with the resin behave as a self-healing agent. Once micro crack will generate, that agent will fill that crack and it will not affect the sensitivity of the material. So such kind of, there are lot of advantages. Such kind of materials are very inexpensive and also environmental friendly. So these are other applications, so I am not able to discuss because of time is very less. So we can prepare, if we will use the stretchable polymer matrix, we can prepare the functional polymers with sensors which can be used to in human motion detections to identify the signals during the any kind of movement in the body of the body. So we have these are many applications people have work on that and thus on such kind of materials. So we have challenges and future opportunities. So piezoresistive strain sensors, the challenges, main challenges, the piezoresistive strain sensor require some external power source. Without external power source, we cannot identify the sensitivity and any kind of deformation in the structures. So this is big challenge for us to how to integrate such kind of sensors with power sources into the storage devices. And in the thermoplastic polymers, temperature is another big challenge. So we cannot use the material in structural health monitoring. So people are trying to work on this. And once in the conclusion part, if you increase the market size, increase the mass production and the technology growth, and then we can get the cost of the unit is that will be very very cheap. Okay, and this structural health monitoring technology will become more effective if we add the self-healing agent inside the material, so which can enhance the property, and if we can healing agent can protect our structure from minor failures. Thank you very much, ma'am. Hello. Hello.
Thank you, sir, for the wonderful presentation. I would like audience to ask some questions.
Sir, I have one questions to you.
Yes, sir.
Because you're talking about this making sensors and all that with the help of CNT, everything. So I wonder if you have heard about this liquid crystal elastomers, LCE elastomers. So do you think that how between these two, like LCE and the one that you are making the composites, and so because there the liquid crystal is already soft and it can actually do things. So do you think that
we can try with the liquid crystal also, because good thing in the liquid crystal is that if you let the liquid crystal can align our CNT, and liquid crystal can resolve a big problem, because people are trying to align. If CNT will be aligned, we can get better conductivity without any agglomeration effect. So
yeah, because elastomer is something like it's already a kind of polymer kind of thing, and in that is you got a film, and we stretch that, and we can align the domains. So I was thinking,
actually our elastomers are showing this hyperelastic behavior. So when we are stretching continuously by applying the tensile load, it does not fail at the end.
Yes. Okay, thank you so much.
Thank you very much, sir. Thank you, ma'am.
Thank you, sir. Now, I would like to invite Shireen Masroor for the session of nanotechnology in science and technology. And Shireen Masroor is from Department of Chemistry, AN College, Patliputra University, Bihar. And the topic is role of nanotechnology in science and technology.
Hello?
Yes, ma'am. Ma'am, you are audible. You can present your slide.
Okay, I'm sharing. Yes, I'm sharing my screen. Hello.
Yes, ma'am, you are audible, ma'am.
Actually, I'm trying to share my screen.
Yes, ma'am.
Okay.
Okay. Excuse me, ma'am.
Yes, is visible?
Ma'am,
My
do you
screen
have any
visible?
trouble? Okay, okay.
Hello.
Ma'am, can you just cancel it and share again, because you have to share entire screen. Then only your screen will come in full.
Okay, okay. Actually, it's not selecting in the entire screen.
Ma'am, right side of the raising hand in the screen, there is a square
Visible?
shape. Huh. No, no. Ma'am,
Visible?
can you make it in full screen mode?
Yes, yes. Is it visible?
No, ma'am. Ma'am, actually, you please cancel this and I will guide you. Can you follow that?
Okay, okay.
Okay. Ma'am, right side of the raising hand in the screen, there is a square shape that says present now. You have to click on that.
Which one? Raising hand. Present now. Raise hand.
Yeah, next to that is a present now. You have to click on present now.
Yes, I am present now.
Then you have a multiple option there. You can select entire screen, share entire screen. When you click on share, it will show share entire screen.
Yes, yes. Share, but Chrome want to share content of your screen with Google Meet. Share.
You just select.
I'm not able to select the option share.
Have you
Actually,
clicked the share entire screen?
Yes, I have shared.
Now, ma'am, you just minimize it and you open your presentation.
Minimize. Actually, no option is coming over the entire screen.
Ma'am, have you opened your presentation?
Yes.
Is it visible in your desktop?
Actually, yes. Earlier, I have okay.
After present now, you have to click. There will be a share option. You have to click on share. It will
Yes,
show
it's
the
visible
entire.
on my screen. Yes.
Now wait, ma'am. Wait.
Is it visible?
Slideshow. Ma'am, it is not in the full screen mode actually. No, can you move the slide once?
Let me check. Is it changing?
It is changing, but the slides are not in full screen mode. In the slideshow mode.
It's coming now?
Slideshow. No, it is not coming. No problem, ma'am. You present like this.
Is it visible now?
It is visible. But it is not in full screen mode. But you can present as such.
Okay, okay. Thank you. So my name is Dr. Shivi Mastoor, and I have been working in Department of Chemistry as an assistant professor since 5 years. Actually, earlier I was working on material science and the corrosion, but now I'm trying to switch my work over the nanotechnology, as it is a flourishing field of the nowadays. This is a kind of a review only that how the nanotechnology is working well uh, in the latest scenario of the science. Okay. So for this, this is the role of nanotechnology in science and everything science and technology, engineering or anything. So first we have to to know that what is nanoscience. It is anything or any object, any phenomena which is working on a scale which is on the nanometer side. Now the similar term is nanotechnology. So it is also a science, especially calling if we call it in engineering or in the technological world, which is conducted in between the range of 1 to 100 nanometers. And collectively, if we conclude both the term like nanoscience and nanotechnology as the study and application of extremely small things, which is in the range of that 1 to 100 nanometers. And from the history of nanotechnology, we can come to know that father of nanotechnology is Richard Feynman, who is the physicist, and the term nanotechnology was coined in the year 1974 by Professor Norio Taniguchi. And nanotech is a concluding term, means we can say nanotechnology in a shortened form as a nanotech. And the any matter, like if it is an atomic, on the molecular or the supramolecular scale, and they can be if they are lying in that range of nanotechnology, that all can be used in for the application in science and technology. And the application of nanotechnology is vast, like it can be applied to the surface science, to the organic chemistry, to the molecular biology, physics, semiconductors, energy storage, engineering technology. And no doubt the range is like 1 nanometer is 1 billion part, or it can be said that 10 to the power minus 9 meter is your 1 nanometer. Hello? Hello?
Yes, ma'am, you are audible, ma'am. You continue.
Visible? The screen is visible?
Yes, ma'am, it is visible.
Okay. Now the thing is why we are opting nanotechnology for our next research. Actually, by applying what we have seen, that by applying the nanotechnology and its different application, we can mold our object or the reactant to get the desired products. After molding, we can get any material with a stronger properties, with a lighter weight. Wherever lighter weight is applied, more durability, more reactivity, or the sieve like. If we want the material like a sieve like, or better electrical conductivity for any specific use. Nanotechnology has been evolving since many decades. For the first revolution came up to 2001, where different synthesis and different applications were happened for the top-down approach, nanostructure metals. These have been discovered up to the 2001 period, and that is called as passive nanotechnology time. And now next revolution comes around 2005, which is called as active nanotechnology, where new synthetic routes or new applications were discovered at that time, like their application in transistors, sensors, and different synthetic routes were applied to synthesize all these things to get the better application. Next comes is nano system technology, which is in between 2005 to 2010. Then the latest comes around 2015, which is the application of nanotechnology at the molecular level. There are three different synthetic routes. Either we are doing it in chemical science, or in physical science, or in the biological science. As the chemical synthesis requires the need of chemicals, the physical methods needs the application of physical modes, and the biological synthesis means we need some biological samples for the synthesis. And the rest, everything can be concluded by getting the different levels and the different structures of nano composites. These are two basic approaches what we are opting to synthesize any nanotechnological product, like top-down approach and bottom-up approach. For the top-down approach, we have to take a bulk, means a more mass, and that can be transformed by the energy transformation into smaller fragments by any kind of application, exfoliation. What here it is given, exfoliation of multi-layer, and finally we will get our nano composite. The same happens with the bottom approach, where we are using the precursor containing molecule, ionization of the energy of the ions from them, then condensation and formation of cluster, and these all cluster will transform into different levels of nano composites. After synthesis, we have obtained a different nanomaterial. It's not general that we are getting a 6 only. Here I am showing only 6, like carbon-based nanomaterial, which are fullerenes, carbonatoid, graphene, and their derivatives. Next comes material-based nanomaterial. Means the metal are incorporated with different nano material particles. Next is dendrimers, molecular nanotechnology, smart materials, nanobiotechnology, where we are getting polymeric nanomaterials, and then finally is nanocomposite. From there, we can get different types of nanoparticles, nanofibers of different range and of different size. Now, before making or after making, we have to screen our products or the reactant, that how they are affecting our environment, society, or the economic impact, because every synthesis needs some effort, and that effort cannot be affect to our economy. So, like first we have to see the fabrication of the nanomaterial based products. Like we have to see the different sources what we are taking the reactant. They must lie in between 100, less than 100 nanometer, what they are giving to the environment, the use of renewable energy, the workplace exposures, like means how it is providing the employment and the economic value generation. Next is general use of nanomaterial. What we have synthesized, what is the use of these products. So by the use of these products, we have to see the if they are benefiting to the society or the environment, how durable they are, how reactive they are, and how its toxicity nature, if they are affecting our society or human or animals or not. The next is end of these. How we have to dispose these things to the environment. So we have to see the recycling capacities, their nature, their ecological exposure, their digestion, their indigestion, and finally the toxicity of these nanoparticles. If we are applying the nanoparticle in commercial products, if we are adding surface treatment, if you are doing surface treatment to the fabrics, they will give your anti-wrinkling, staining, and less bacterial growth. If we are providing the films to different electronics, they will resistant to ultraviolet, infrared, antimicrobial, anti-reflective, scratch resistant. If you are adding nanocomposite to the polymer, they will be more durable for different purposes, like they will be lightweight, they can be easily used for the helmet, for the automobile, best functioning for the automobile parts. If you are providing them in a ceramic coatings, they will be wear resistant. If you are applying in lubricant, they will provide a good lubrication properties, and the moving parts will be best if they are present in between. For the personal care, they can be provided in the sunscreen or the what beauty creams have been selling in the market. If for the electronics like transistors or any other component, they will work as faster in nature as compared to other, and the portability will be also easy. For if you are applying in television, like we will get more vibrant colors. For the electronics, like flexible electronics is portable, we will need nano membranes, and that can be applied in smartphones. If we are using the nanoparticle copper suspension, that can be developed as more safer, more cheaper, and reliable component, and can be replaced lead-based holders, which are hazardous to the environment. And the graphene and cellulosic materials, which are now we are getting a good sensing property from these components. For the medical healthcare, like we can early we have had good diagnosis by applying these nanoparticles for the better therapeutic success rates. Like gold particles have been using in cancer and other disease for the treatment of diagnosis and treatment of arteriosclerosis, and that can build up of the plaque in the arteries. And now some researchers have been using the nanoparticle, which have to shrink the flakes, whatever we are cutting to the HDL cholesterol. And some nano medicines have been applying to improve the shelf life or the effectivity of vaccines. If you are seeing the application of nanotechnology in engineering, engineering to improve the energy applications, like by getting the more intake of nanotechnology and nanoparticles, the efficiency of fuel is enhanced. These particles have been used to detect the downwell, means early fractures. Wires containing the nanocarbon tube have much lower resistance than high tension wires currently used in electric grids. Incorporated into solar panel to convert the sunlight more efficiently, conversion of sunlight into into the electricity that is more inexpensive. And new kind of batteries have been introduced for the quicker charging, for the more efficiency and the light in weight. For the environmental remediation, or the means cleaning the waste product from the society or the environment, we are applying different nanoparticles which can be more affordable, which are replacing the big machineries and the clean, and they are providing the more cleaner water, or means they are also getting glucose detection of impurities. Development of new clean industrial water pollutants at the ground level water by the different chemical reactions. There are so many mechanical filtrations have been made, which are present at the nanoscale pores, which can trap the particles larger than size of their flat pores in different air filters. The application of nanoparticles have been used in the sensors for to detect different impurities or different anti-environment agents which are present in air or soil. If we are seeing in the transportation, we are developing multifunctional material that can best contributing to the development of big structures, buildings, or the roads, or anything bridges for more efficient transportation and cost-effective continuous monitoring of the structural integrity and performance of the bridges, tunnels. And if I'm talking, as I'm from chemistry background, so I'm seeing the different nanoparticle use in different types. Like if we are incorporating them with the metals like silica, titania, alumina, iron oxide, zirconia, zinc oxide, and we are having good application of them in the general life, like polymer composite production from UV visible light, and solar cell, enhanced efficiency of solar cell, pharmacy additive, for this means making a good resistance coating for any for the if we are applying them to resist corrosion. Fullerenes, mechanical, means if you are adding fullerenes, different mechanical or tribological properties have been changed. If carbon nanotubes, single wall or either multi wall, they are giving a best quality for the electronic fields, batteries, fluoropolymer composite, and compounds. If you are incorporating with the semiconductors like cadmium telluride or gallium arsenide, they are getting a best implications on the optical devices. Organic nanoparticles means if you are adding the other component as organic material like drugs, chemicals, vitamins, pigments, and polymer dispersion, catalytic. If you are adding metals with different nanocomposite and applying them in different reactions, they are giving the best catalytic properties. There are some challenges for the nanotechnology. To tackle these, we have to look afterwards that what we have to do, like means we are getting different gadgets by incorporating nanotechnology, which can get a prior result to health, but it is also affecting. We are getting the sensors, self-healing structures, making big data possible. Means earlier we are scared of making big reactions in or big products without the use of nanotechnology, but now we are getting big results in a very nano level by the application of very nano level compounds. And by this, we are getting a different information relating our climate change. There are so many risks of using nanotechnology, like businesses involved in marketing, as we are getting the high products making nanotechnology, and we need big markets and big they are marketing. Yes.
Ma'am, please can you wrap your session because we are running short of time. Can you please conclude?
Yes, it is Rafat. Actually, I have just concluded.
Okay.
So, uh, next is protection of intellectual properties. Political risks are incorporating for different countries and regions. Privacy, environmental risk, status of the nanoparticle for the work and consumer. These are some references from where I have taken. Thank you.
Thank you for the wonderful talk, ma'am. Can I invite audience for the questions? The session is now open for the discussion. Okay, if there is no question, then thank you so much, ma'am, for the wonderful presentation. We will move on with next session.
Okay, thank you.
I would like to invite Madhav Prabhakar Chauhan, University of Ostrava, Faculty of Science, Czech Republic, and Ashmita Datta, Department of Chemical Sciences, Ariel University, England, Ireland, to please share the next session.
Okay, can you hear me?
Yes, sir, you are audible.
Yeah, so I'm Madhav, and we have next session as a plenary session with plenary talk as a PL9 by Alina Sienkoskova from University of Torun in Poland. So I request Professor Alina to present the lecture.
Good afternoon to everyone. Can you hear me?
Yes.
Thank you very much. If you can hear me, probably you can also see me. I will try to share my screen now. Can you see my screen?
Yeah, it getting loaded. Yeah.
Can you see my presentation?
Yes, I can see, but you have to do in, yes, of course, yes.
Can you see full screen?
Yes.
Okay, thank you very much. So once again, thank you very much for inviting me to give the talk during this nice conference. So I will be talking today about biopolymer blends for fabrication of composites and nanocomposites. As the chairman said gently that I am from Nicolaus Copernicus University in Torun. In fact, I'm a head of Department of Biomaterials and Cosmetic Chemistry. So I show here the statue of Copernicus because what is famous about our city is that Copernicus was just born in the Torun. So for this reason, our university has the name of Nicolaus Copernicus. So today, the outline of my talk is as follows. I will talk about natural polymers, then about composites and nanocomposites. Later on about collagen and its composite, about biopolymer blends, and also composites and nanocomposites based on biopolymer blends, future application and conclusion. So in fact, it will be very short overview what we are doing in our lab in Poland. Just a short introduction about natural polymers. Natural polymers are polymers which are made in the nature. So in nature we have a lot of polymers, namely we can have polysaccharides like starch, cellulose, chitosan, polypeptides, proteins like albumins, collagen, elastin, keratin, or silk fibroin. Natural polymers are almost everywhere, but sometimes it's not really easy to get natural polymers from nature, which is rich in such a polymers, because sometimes just the purification of natural polymers costs a time and is of course cost money. So it's time-consuming procedure. However, for application of any natural polymers, we can use the waste materials, which are, for example, the waste of food production or the waste of leather production of other waste. So in fact, we can use the skin, we can use the feather, we can use the waste of bombyx mori cocoons with production of textiles, or even the fish scales. So using biopolymers, of course, we can prepare several other compounds. Also, we can prepare composites. So it is commonly known that natural biocomposite in nature is the bone tissue. Bone structure is a very typical composite, or let's say maybe even nanocomposite, which is built of natural polymer. This natural polymer is collagen, and it's built of the crystals. The crystals are hydroxyapatite. So in fact, if you want to fabricate such bone structure in the laboratory, so we have to use polymer matrix, and we have to use inorganic particles, so it will be similar to hydroxyapatite, or if they be just hydroxyapatite. We have to incorporate as much as possible into polymeric matrix. However, we have to remember that when we have the bone tissue, in fact, inorganic parts contains much more than organic parts. So usually is about 65, even more in dentin and enamel inorganic parts than organic parts to produce that composite. So we decided to work with collagen. In fact, we worked for many years with collagen. So collagen is a natural polymer, which is widely found in the nature, because every living body is built of collagen. So collagen can be found in the tendons and the skin, of course, is the fish scales and other marine source. So what is very typical for collagen, that collagen itself forms nanostructure. So in fact, this is something like hierarchical structure of collagen. So we have primary structure, which is built of amino acids, then secondary structure, which is just the orientation of the chain around the axis, and then we have three chains which are joined together in the trip helical structure, and then we have much more sophisticated arrangement. Then we have ternary structure, next structure which form the fibrils, and then fibers. So in such collagen molecules, we have several interactions, but mainly the most important interaction are hydrogen bonds, which can be formed between OH group, for example, of hydroxyproline, which you can see here, and also amine moieties or carboxyl moieties or other moieties. So collagen is widely studied. So if you go to the any web of science database, there are a lot of publication about collagen. In fact, we prepare our materials using collagen from two sources. One was rat tail tendon, and another one was fish skin collagen. So when we started to work with collagen materials, at the beginning you have to wash the tissue. So we wash the rat tail tendons, or we wash the skin of the fish, and after then we try to soluble our collagen in acidic pH. It's worth to remember and remind that collagen became insoluble when it is organized in higher structure. Then appear not only hydrogen bond, but also a covalent bond, and it happened that collagen is not dissolved anymore. So in fact, we have to use collagen in its very young stage of organization just to get soluble collagen. So in fact, we have a big part of collagen soluble, for example, in acetic acid, but also we can use lactic acid and other very weak organic acids. And after then, we can get collagen solution. When we had collagen solution, we can easily form the films, or we can also produce 3D forms. The denaturation temperature of our collagens, which we use in our lab, is 39 degrees of 30 grade for lactate turdon collagen, and for fish skin collagen is 29 degrees of centigrade. So when we want to produce 3D structure, the simplest way is just to freeze dry the sample. So after lyophilization, which is called usually freeze drying, we can get something like a sponge. But when we use a typical mold to produce just a typical shape, we can shape our collagen samples into shape which can be required, for example, in tissue engineering. After freeze drying technique, we can get 3D structure, and you can see here in the same image. So it's highly porous structure, what is good enough for tissue engineering application. So after freeze drying, we get the material which is very flexible and which can uptake a lot of water. So in fact, its mechanical properties, it's not good enough. So we have to do any modification for improve mechanical properties and to improve degradability, just to properly assess the time in which the SEM can be active in the organism, for example, after implantation. The next important thing is that when we compress the sample, and then in wet condition, the sample can turn to the previous shape. So in fact, can meet the shape for example, in natural tissue, which we want to fill up. So then we can prepare just a composite. So to prepare the composite, for example, with nanohydroxyapatite, so you can see in the scheme, again, we have collagen from lactate tendon, and this freeze-dried collagen, we correctly weigh, and then we prepare a solution of collagen. And of course, we can prepare different concentration of solution. In this study, we prepare 1 weight% and 2 weight% of collagen solution, and we incorporated inorganic nanoparticles such as hydroxyapatite. And of course, after homogenization, then we frozen and use freeze drying to prepare our scaffolds, which in fact are biocomposites with nanohydroxyapatite. We cross-link our samples using EDC and HS, and also using the hydrothermal treatment to increase mechanical stability of the samples. So the SEMs look like that, and you can see here what kind of cross-linkers we usually use. We usually use a couple of NHS and EDC, but also we use tannic acid, starch dealdehyde, and chitosan dealdehyde. Especially tannic acid and starch dealdehyde and chitosan dealdehyde are the new cross-linker which we started to use in our lab. So using tannic acid, we cross-link our SEMs mainly by hydrogen bond, as you can see here in this picture. However, when we're using the aldehyde starch of chitosan dealdehyde, then of course we have here a chemical reaction and covalent bonds can be formed, which made our structure much more stronger than using other cross-linking agents. So after preparation of our collagen hydroxyapatite material, you can see here the scanning electron micrographs for collagen when we prepare the scaffold from collagen with concentration 1% with different amount of hydroxyapatite, cross-linked by EDC and HS, and cross-linked by the hydrothermal treatment. So you can see here that you get a different porosity depending on the amount of hydroxyapatite and depending on the way of cross-linking. When we use the higher concentration of collagen, just 2% collagen solution was freeze-dried and also freeze-dried with hydroxyapatite. So you can see here that the cross-section of the samples is completely different, the porosity is different, and of course it will give different properties of the scaffolds formed with different concentration of collagen. So you can see here the swelling properties of our scaffold. So the swelling properties are much higher when we cross-link scaffolds with dehydrothermal treatment, because in dehydrothermal treatment we increase temperature. So by this reason we remove some part of water which is usually around the sample. So the swelling of scaffolds which are cross-linked in this way is much bigger than the swelling of scaffolds cross-linked in chemical way. So you can see here that also by addition of hydroxyapatite, the swelling properties are much smaller than before application of hydroxyapatite, because in fact hydroxyapatite do not uptake as much water as collagen can does. So compressive modulus and mechanical properties, which are very important for any medical treatment with any implant or tissue engineering scaffold, you can see here that much better mechanical properties we could get when we use collagen with higher concentration. And in fact, when the amount of hydroxyapatite was high enough to be strong enough to be used, for example, as a spongy bond, which could be applied in biomedical engineering. Of course, the mechanical properties differ when we measure mechanical properties for dry scaffolds and when we measure mechanical properties for scaffolds soaked in PBS, because of course they are much more elastic than. Next work which we do in our lab is incorporation of magnetic particles into collagen materials. So again, we prepare a collagen sponge, and again we prepare different collagen solution, and we prepare in the lab just magnetic particles, and then we incorporated magnetic particles into collagen materials. So you can see the size of the particles in the TEM image, and you can see our materials after freeze drying as the final materials. This kind of materials can be used, for example, as drug delivery system. So can be, for example, implanted, and then outside a magnetic field can arrange how, for example, any drug can be released from the matrix. So in the same image of such a scaffolds, we can see just the magnetic particles which are dispersed in the polymer. So mechanical properties, of course, you can see here, can be improved when we cross-link with starch the aldehyde. However, swelling properties are much smaller when we have cross-link and when we add 20 or 30% of magnetic particles into our collagen solution. But in fact, now we are not working on a single polymer and addition of any particles, nanoparticles, just to form composites. But in fact, we work with polymer blends, and then in the polymer blends, we incorporate inorganic particles or organic particles just to get a composite. We follow here, in fact, the nature as our inspiration, because in fact, in nature, several natural polymers are present together in one tissue. For example, collagen and elastin can be found in the skin, and they work together for a good skin structure. And mentioned before also the structure of bone structure is also just a natural composite of collagen and hydroxyapatite. So in fact, when we make the blend and composites in the laboratory, we work with the nature as our inspiration. And in fact, we try to mimic what nature in fact form in natural way and what can be used after such a fabrication, for example, in medical or cosmetic field. So when we have polymer or biopolymer blends, we turn them again into the structures. And of course, we can use to add particles or nanoparticles into such materials. But it was to mention here that scientists can be clever than the nature, because in nature we have already arranged mixtures of several polymers. But we do not know, but for any reason, the nature didn't mix together some of polymers, but in the laboratory we can do that. So for example, collagen and chitosan in nature usually do not exist together, but in the lab we can prepare just such mixtures and finally produce a biopolymer blend, and in such a blend we can incorporate several nanoparticles. So to prepare the blend we can get two solutions of biopolymers. Of course we need polymers just to be dissolved in the same solvent. We can mix an appropriate weight ratio, and then we can prepare polymer blend, and in such a blend we can incorporate an organic or organic nanoparticle just to form a composite. So in fact in our work we mix several polymers to collagen, for example keratin, chitosan, silk fibroin, hyaluronic acid, elastin, and finally we got new materials. So when we incorporate inorganic nanoparticles like hydroxyapatite, we can try to find the structure similar to human bone, or without hydroxyapatite, without any inorganic particle, we can get a sheet which can be similar, for example, to human skin, and can be used for exchanging the skin tissue, for example, for any injury of burns on the human skin. So in fact, when we prepare such a blend, so we can get materials for wound healings, we can get good materials for cosmetic creams, we can also prepare artificial skin, dermal filler, several hydrogel. Also, one of PhD students is working to get good beauty mask, and several materials can be prepared for tissue engineering and regeneration. So the possibility for production materials using polymer blends is quite high. But of course, each of polymer or biopolymer blends has to be carefully studied, because what is the very important aspect here is miscibility of two polymers. So we have to study when we use two polymers or biopolymers, if we really have homogeneity of the mixtures. So the homogeneity is just the first observation, but then we have to use several physicochemical methods to assess miscibility in the blends, like for example assessment of glass transition temperature. Of course, if biopolymers have such a glass transition temperature, or we can have use, for example, FTIR spectroscopy and sometimes NMR spectroscopy or viscometry methods, just to assess what kind of interaction can appear in such a blend. Usually, the most common interaction are hydrogen bond. So you can see here just an example of the structure which we obtain for the blends of collagen and chitosan. So without cross-linking, cross-link with tannic acid, so you can see then we can get the structure with a different shape and size of pores. So we can increase porosity of the materials using the blend. We of course can change mechanical properties of the virgin and natural polymer. So you can see here just an example, we mix collagen and chitosan. So the mechanical properties for some blends can be even better than for that one which are not a blend. And when we additionally use cross-linking, so we can even improve the mechanical properties of the materials. Of course, very important for any medical, biomedical application are biological properties. So we usually study biological properties not in our lab, but in collaboration with Department of Cell Biology and Imaging Institute of Zoology, Faculty of Biology, in Jagiellonian University in Krakow. So you can see here that our blends, just collagen chitosan blends, have biocompatibility similar to, let's say, collagen. So they are good enough for biomedical application. So next biopolymer which we use for the blending is silk fibroin. So collagen blended with fibroin easily can film form and also easily can be turned into 3D structure with high porosity. So of course we can get materials with different mechanical properties, and of course we can incorporate into such materials also hydroxyapatite. Next, what we can do, we can prepare the blends of 3 natural polymers. So ternary blends is not easy to get because there are several interactions, and usually the interaction between 2 polymers are much stronger than between 2 another ones. So we have to study correctly what can we mix together just to have homogeneous mixture and finally homogeneous materials for preparation of the blend. So in our study we started from collagen and chitosan, which was mixed 50-50, so 50% collagen and 50% of chitosan, and then we added hyaluronic acid, and we found that this hyaluronic acid can be added not in very high quantity, because when we add too much, then our phase were separated. So you can see here just the porosity of our SEMS. Porosity is very high. The shape, of course, was after freeze drying similar to that which was found before, and after cross-linking with tannic acid, we improve mechanical properties of the sample. We also compare the cross-linking by tannic acid and with the aldehyde starch. Let's remind me, cross-linking with tannic acid is mainly by hydrogen bond. By when we use the aldehyde starch, the cross-linking is covalently bonded with another polymer, which means collagen, chitosan, hyaluronic acid, and this fact we use the mixture, so the mixture was crossing with the aldehyde starch. And of course, hydroxyapatite was added, but another approach was when we try to precipitate in situ hydroxyapatite in our polymer mixtures. So then we get similar scaffolds, but hydroxyapatite was not just the hydroxyapatite added during the experiment, but was precipitated during the experiment. So you can see here we compare mechanical properties and we compare biological properties for 2 ways of cross-linking. So mechanical properties are much better when we cross-link our scaffold with starch-dealdehyde. However, biological properties are much better when we cross-link with tannic acid. So it seems that tannic acid is much better cross-linking agent if we mean biological properties of our materials. Of course, for our scaffolds, we tested also porosity, density, and also after addition of hydroxyapatite, so we get different results. As you can see, mechanical properties has the value about 47% 30 kilopascals, so not very good mechanical properties, but good enough to replace a spongy bond in human body. Next blends which we are working now is blend of collagen, chitosan, and silk fibrin, ternary blends. So now we are at the beginning of the study, and we prepare already the film of such materials, but also we prepare 3D scaffolds, but without hydroxyapatite. Here we use a different cross-linking agent which contain just carbonyl group, was starch dialdehyde and chitosan dialdehyde. So, and we try to compare the possibility to crossing by starch dialdehyde and chitosan dialdehyde. As you can see in the picture, so the porous structure is different. So the porosity is different when we cross-link with the aldehyde chitosan than with the aldehyde starch. So depending on what we need to obtain, so we can use just cross-linking agent. And just short comparison, you can see here that some sample cross-link with the aldehyde chitosan has better properties than those which have been cross-linked with the aldehyde starch. So now I would like to sum up and conclude. Mechanical properties of polymeric and biopolymeric blends can be modified by the weight ratio of the components. So if only we can mix with different weight ratio, we can expect different mechanical properties. So we can, in fact, adjust the mechanical properties to our needs. When we need material for cosmetic application, so the mechanical properties are not necessary to be strong. However, when we use material for biomedical application, then we have to get appropriate mechanical properties. We found also that ternary blends are much more stable in aqueous condition, so which means that such material with after application, for example, on hair, on the skin, will not immediately dissolve after wetting with water and can, for example, be used for drug delivery system. We also found that freeze-drying technique can be used not only for preparation 3D sponges from single polymers, but also from binary and ternary blends, and also can be used for preparation 3D materials after incorporation in organic or organic nanoparticles into biopolymer blends. So several new materials can be formed. Such the materials can be used as scaffolds in tissue engineering or as drug delivery systems. So example of using as tissue engineering material, there are materials which contain hydroxyapatite, but those which can be used as drug delivery system are materials which contain magnetic nanoparticles. And of course, finally, I would like to thank you for your attention and all my PhD students for working on my project. So I am in Poland, so we are located, our Nicolaus Copernicus University is located almost a central part of Poland between Warsaw and Gdańsk. So we are open for collaboration. If someone of you have any idea to collaborate, so we can exchange emails. As I said before, Copernicus was born in our city. So our city is in fact from medieval times. So we have some architecture from the medieval time. Thank you very much for your attention.
Yeah, thank you. So it was a nice presentation. So it's a time for a question. Okay, so I can ask a question. You shown in your presentation nice SEM images. So at what scale the porosity is induced in such kind of composite materials?
The scale of porosity, you mean, yes? Okay, so we have, the scale is micrometers. From 50
micrometers.
from 50 to 500 micrometers.
Okay, so and how you measure such kind of porosity, by microscopy, or you are doing any other kind of technique?
Usually we measure using the microscope image, and we calculate the average from several parts of our scaffold.
Okay, okay. Thank you. Okay, so I thanks once again the speaker for a very nice presentation. And now our next speaker as a plenary lecture with PL10 presentation, Professor Akhilesh Rai from University of Coimbra and UC Biotech from Portugal. So I request Professor Akhilesh Rai to deliver his lecture.
Thank you very much. I will share my slide. I don't know how to share the slide.
Okay, on the screen you can see the upward arrow.
It is still showing that Elena is presenting. So
yeah. I request to Elena to switch off the presentation and
yeah, still it is showing that. Okay.
Elena, can you listen to us? I think you can share. I think
I can share.
Yes, you can share. You can click on the arrow.
Okay.
And you can share your screen.
Okay. No, I don't think so. It is not possible to show. It is still in the window. It said that this will allow you to take over the Elena's main presentation.
Okay, can you click
on that? Okay, yes, I can.
Yes,
yeah, now I can. Okay. I'm not okay. So
yeah, it's get opening here.
Oh, yeah. So I believe everyone can see the presentation, right?
Yes, yes.
And everyone can hear me properly.
Yes.
Okay, so hi everyone. I am Akhilesh Rai from Faculty of Medicine, University of Coimbra, Portugal.
Just to disturb, can you do the presentation mode? Can you?
It is in the presentation mode.
Okay.
Can you see full presentation?
No, you have to.
No, in my computer I can. It is full presentation.
Okay, no problem. Yeah, you can carry on.
Maybe if the problem I can. Okay.
Yeah, it's okay.
Okay, so it is. I will say good afternoon because it is just midday in Portugal and good evening in India. So basically, today I will talk about nanoparticles which are responsive to near infrared light and how they can affect, how they can modulate immune response, and if they can affect the integrity and function of blood-brain barrier. So, so the topic of my talk is evaluation of immunotoxicity evaluation of light responsive nanoparticles to the integrity of blood-brain barrier. So,
Dr. Akhilesh,
yes,
you can start your presentation.
I have already started. Can you hear me? Hello. 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 Can you hear me? Hello. Hello. Hello.
Yes, we are hearing you. You can start your presentation.
Somebody told that they cannot hear me. So
no, I think it.
Sorry, just a minute. I don't know what is happening. I will do it again. The presentation. Okay, so okay, I will start now. So, due to the advancement of medical technology, the death rate of human being is continuously decreasing, and therefore the population of old people have been increased significantly in last few years. If you see the population of old people above 60 years.
Dr. Akhilesh, excuse
Hello.
me, sir. We can't hear you. Your voice is not audible to us.
You can't hear me.
No,
But
we
I
can't
can.
hear you. The presentation is visible, but your sound we can't hear.
You cannot hear.
Sir, it's okay. We can hear you, sir.
Okay. Oh, okay. Somebody telling that they can't hear me, and okay, maybe I will continue. Otherwise, it would get delayed. The population of old people, if you see the data over here, the population of old people above 60 years is around 12.3% of total world population in 2015. And it is predicted that in 2030, the population would be around 16.5% of total world population. And similarly, in year 2050, the population of old people above 60 plus would be around 21.5% of total world population. So, since hello,
we
hello,
can't hear you.
Somebody telling that they can hear me, and then you are telling that you can't hear me. Hello.
Yeah, madam. For me, it's loud and clear.
I will request Dr. Madhavan. Madhav, can you hear me?
Because we have tried with both systems and we are not able to hear. Maybe we will check the connection.
Dr. Madhav, can you hear me?
Dr. Sonal, can you hear the presentation?
Hello.
Dr. Sonal or other delegates, can you please inform whether you can hear?
Yes, we can hear.
No, voice is not audible. Not audible.
Yeah.
I don't know.
Professor, can you please check your microphone? Maybe there is some internet connectivity issue with us, but since others also can't hear.
I don't know if there is any kind of setting which I can change and
are you using two systems?
no, I'm using just one, my computer. I'm not using other system.
But you can you please log out and log in again, because I can hear you clearly. Some others say they cannot hear you. I think better you log out and log in again so that let's check.
Yes.
Sorry, can you repeat it again?
You lock it out and log in again, so that there is some problem in the sound. I can hear you very clearly.
Okay, I will just leave the call and then I will join again.
Better.
Yeah. Hello. Hello.
Yes, you are audible now.
Yes, now it's audible.
Okay, so I will present now. I will just share my screen. So you can see the slide, right? Hello. Hello.
Yes.
And you can hear me well, right?
Yes.
Okay. So so I was telling that number of old population above 60 years have been continuously increasing. And if you see the slide data over here, it is predicted that in year 2050 the population would be 21.5% of total world population, which means that when we have higher population of older people, there is high probability of having different kind of brain diseases. So it is estimated that in the life expectancy of Europe in 2004, the average life was around 78 years. In year 2014, the average life was around approximately 81 years. So overall, in 10 years, we have gained 2.48 years. So, since the topic of my talk is to deliver to target the brain, I would like to to draw your attention on the blood-brain barrier. In our human body, we have several kind of biological barrier. One of the barrier is called blood-brain barrier. So, if you see picture over here, this is the kind of schematic diagram of blood-brain barrier. So basically, this is the blood vessels, and the outside this is the brain. So the blood vessels is mostly composed from the endothelial cells, and these endothelial cells, they make kind of monolayers in the blood vessels. And when they two cells when they join here, they call it is called tight junction. This is the one of the characteristics of blood-brain barrier. So basically, blood-brain barrier have endothelial cells which also make tight junctions. They have pericytes which cover the blood vessels. They have astrocyte, and they have extracellular matrix. So overall, this compositions, they make the blood-brain barrier. So basically, the property of blood-brain barrier are mostly manifested within endothelial cells, but they induce and maintain the critical interactions with the pericyte, immune cells, and neuron cells. So I told that the increase in life expectancy leads to higher number of brain disorder, and therefore we need advanced therapy and drugs and drug carriers for the treatment of brain diseases and the repairment of neuronal cells and improve the function. You might know that approximately 98% of small molecules and 100% large molecules drugs do not cross blood-brain barrier. When I say small molecules, which means that the size of molecules, if it is above 400 to 500 Dalton, they cannot cross blood-brain barrier. On the other hand, when the molecules are below 4 to 500 kilodalton and they have high lipid solubility, they only pass through the blood-brain barrier. Therefore, it is important to develop an innovative carrier which can promote the transportation of larger size of drugs inside the brain. Nanoparticles are very effective in penetrating blood-brain barrier. And of course, nanoparticles can be functionalized with molecules, drugs to specifically target brain region. At the present, there are no nanoparticle formulation are approved for the treatment of brain disorder. So currently, there are few approaches which have been used to deliver drugs in the brain. First is called invasive approach. Invasive approach means it requires surgery in the brain to deliver the drugs at a specific region. So there could be several approaches for the invasive method. Then there is non-invasive method, which means that we can deliver the drugs through the intravenous injection, and then the drugs can reach to the brain. So there are, again, in non-invasive approach, there are few different approaches which have been adopted. First is chemical approach, which means that we can make drugs more lipophilic so that they can cross the blood-brain barrier. Another is the biological approach, which means that we can use exosomes or extracellular vesicles, bacteria, or viral vectors to deliver drug to the brain. And then we can use collider drug carriers such as liposomes, nanoparticles to deliver drug to brain. There is alternative approach also to deliver drug to the brain that is called intranasal delivery, which means that we can deliver drug to the nose and that can pass to the brain, and then inotophoretic delivery. So there are a few pathways in the blood-brain barrier which play an important role for the transportation of drugs, small molecules, and nanoparticles to cross to the to reach to the brain. First is called paracellular pathway, which means that small molecules which are water soluble, they can pass through the tight junctions and then they can reach to the brain. Another is called transcellular lipophilic pathway, which means that those molecules, they interact with the biological membrane and then they pass through the cells and they reach to the brain. Then there is called a transportation pathway. We know that our cells have transport carriers or receptors. So, for example, blood-brain barrier, they have the receptors for the glucose or for the nucleoside. So, if we those molecules can interact with these receptors and then they can reach to the brain. Then there is a specific receptor present in the blood-brain barrier, especially in the side of the blood, that we call the receptors. Okay, and so we can use receptor-mediated transcytosis. For example, there is insulin or transferrin receptor present in on the side of the blood vessels, and so these molecules can interact with the receptors, and then these receptors, they go inside the biological vesicles, and then these biological vesicles, they release the proteins or peptide to the brain. And then another pathway is called adjunctive transcytosis, which means that here the molecules or the nanoparticles which are positively charged, they interact with the negatively charged biological membrane, and then the cells engulf those drugs or nanoparticles, and then they interact inside the vesicles. And later on, these vesicles release the drugs or nanoparticles to the brain. So these are the cellular pathway for the crossing of drugs and nanoparticles to the brain. So in the last few years, there are a few hypotheses to temporarily open the blood-brain barrier in order to increase the accumulation of drugs in the brain. So one technique is called focus ultrasound, in which we can use a microbubble and then we expose to the ultrasound. What happened that in presence of ultrasound, this microbubble, they start, they expand. And what happened when they expand, they temporarily open the brain barrier, and so drugs molecules can reach to the brain. Then another approach called hypothermia, it means that we can locally increase the temperature, and because of the little higher temperature, blood-brain barrier will open and the nanoparticles can pass. And a few years ago, we have published a paper where we have shown that gold nanorod, which have property to emit thermal energy under the exposure of near infrared light, can be used to deliver nanorod to the brain. The third approach is called chemical approach, in which we can use hyperosmotic solutions such as mannitol, which can temporarily open the blood-brain barrier, and drugs can be delivered to the brain. So today I will talk about different approach using polydopamine nanoparticles for the delivery of polydopamine nanoparticles to the brain. And why we have selected polydopamine nanoparticles? Because they are biocompatible, they have antioxidative properties. It is very easy to do the optimization of polydopamine.
Sorry to disturb you. Excuse me, sir.
Hello.
Sorry to disturb you, but your slides are not moving.
Hello.
Hello, Akhilesh. Akhilesh, you have to play your presentation mode.
It is in the presentation mode. I don't know why.
Because you just open your presentation and the slides are not moving. So you just have to do a slideshow play.
Slides are not moving.
Yes, so you have to do show play. I can see from your screen there is a green button with the play. So you can just you can do from your screen.
Sir, you can directly click on the slides also. They will change. You just
Yes.
now they are changing.
Yes.
Can you see
Yes,
changed?
yes. Now it's changing. You can you please continue?
Okay. Oh, sorry.
Yes.
Sorry. I didn't know that it is not changing. Okay. So today I will talk about polydopamine nanoparticles. So as I was telling that it is very easy to do the surface functionalization of polydopamine nanoparticles. Addition of SIP-based reaction or pi-pi stacking interaction. So we can immobilize or conjugate different kind of biomolecules on the surface of polydopamine nanoparticles. Polydopamine nanoparticles act as a semiconductors, and so they absorb near infrared light, and they have around 40% of photothermal energy conversion efficacy. So what we did that we used a very simple approach to make the polydopamine nanoparticles. So we took the certain concentration of dopamine precursors, and in the alkaline conditions, dopamine polymerize and they make polydopamine nanoparticles. So to functionalize, then we functionalize the polydopamine nanoparticles with the transferrin peptide. Why? Because as I told previously that blood-brain barrier have the transferrin receptor. So we can selectively target nanoparticles to the blood-brain barrier. So for this purpose, we use specific surface chemistry. So here we use linker, amine pegmelamide. First we conjugate with the transferrin peptide, which has a thiol group. Okay, and once we have this conjugate, then we conjugated the transferrin functionalized with amine pegmelamide to the polydopamine to prepare the transferrin conjugated polydopamine nanoparticles. I will just ask if you can see the slide moving, right? So then we did the characterization of polydopamine nanoparticles. I see that temperament, the polydopamine nanoparticle was around 55 to 60 nanometers. When we did the functionalization of polydopamine nanoparticle with the transferrin peptide, we didn't see any increase in the size of nanoparticle, which indicated that nanoparticles are very stable. And I would like to draw your attention that we have conjugated around 180 transferrin peptide per polydopamine nanoparticle. Then we studied the stability of nanoparticles in different conditions. So we found that polydopamine nanoparticles or transferrin conjugated polydopamine nanoparticles were stable in water, in cell culture media, that is DMM. And when we expose polydopamine nanoparticles or transferrin conjugated polydopamine nanoparticles to near infrared light for 5 minutes, still we did not see any change in the size of particles, which indicates that nanoparticles are stable. So in the you can see that the polydopamine nanoparticles were negatively charged. On the other hand, transferrin conjugated nanoparticles. Okay, see over here, we did the data potential so that transferrin conjugated nanoparticles were positively charged. Then we did the TIR analysis. Indicate that we have successfully conjugated transferrin peptide on the surface of polydopamine nanoparticles. Further to understand the photothermal polydopamine nanoparticles, we expose dopamine to near infrared light for these specific parameters, and then we use to measure the profile. You can see that in room temperature we did not have any increase in the temperature. When we expose to the near infrared light, you can see the increase in the temperature. And what we found that polydopamine nanoparticle or transferrin conjugated nanoparticle, both nanoparticles increase around 5 degrees the reaction solution after the near infrared light. And when we switch off the near infrared light, it takes approximately 10 minutes to reach to the crystal level. Then we move to develop the in vitro blood-brain barrier model. So here we use monoculture model. So we took the mouse endothelial cells and we made the monoculture BBB model. It generally takes 6 days. And when we did a specific characterization of this blood-brain barrier, so we use confocal microscopy, we use permeability to chloride called Lucifer yellow, and then we based on the literature data, we found that the value of permeability and tear is equal to the previously reported data. And if you see over here, confocal microscopy, we can see very uniform and very nice. Okay, just for the so we use a specific marker that is called Jo1 and Claudin 5. These are the particular protein which is expressed in the tight junction of the blood-brain barrier. As you can see in the green, we can see highly expression of both markers, and we don't see any kind of damage in the blood-brain barrier, which indicate that we have prepared intact and functional monoculture blood-brain barrier model. Then we study the biocompatibility of our nanoparticles. So we incubate the nanoparticles for 4 hours, and after 4 hours we remove the nanoparticles, and then we expose to the light for 5 minutes, and then we did the biocompatibility assay. And you can appreciate that the nanoparticles with light, without light, or peptide and exposure to the light, all the conditions, they are stable, they are biocompatible to the blood-brain barrier cells for 72 hours. So, which means that nanoparticles, polydopamine nanoparticles are transferring conjugated polydopamine nanoparticles, and the exposure of near-infrared light do not induce toxicity to blood-brain barrier. Then we wanted to study the internalization of nanoparticles. So we found that this mouse brain endothelial cells, they internalize very small amount of polydopamine transferrin conjugated nanoparticles. So transferrin conjugated nanoparticles are 3 times more internalized by the endothelial cells. Then we studied if nanoparticles and exposure of light damage BBB or not. Okay, so we as you can see in the schematic diagrams, we incubate for 4 hours, and then we expose to the near infrared light, and then we could do the characterizations. So basically, we measure the permeability with the Lucifer yellow and the tear measurement, which I told in a few slides ago. So compared to the control, what we found that little increase in the permeability when we expose to the transferrin conjugated polydopamine nanoparticles and exposure of light. However, the increase was not statistically significant. In case of tear measurement, we did not see any difference in the tear value compared to the control. Again, it indicates that the combination of transferrin peptide and near infrared light increase the permeability. However, it doesn't damage the integrity of blood-brain barrier. As you can see over here in the confocal microscope images, compared to the control where we can see intact monolayer, when we expose to the PDA nanoparticles and the light or transferrin conjugated PDA nanoparticles and light, we do not see any damage in the blood-brain barrier. Then we evaluated. We went in the more molecular pathway to understand the expression of different kind of tight junction proteins using quantitative RT-PCR. So we did the gene analysis of different protein marker which is present in a tight junction, like PCAM, tight junction 1 protein, occludin protein, Claudin 5 proteins. As you can see, compared to control, we did not see much difference in the expression of those genes, which again indicate that transferrin peptide, conjugated polydopamine nanoparticles, and exposure of near infrared light do not damage the integrity of blood-brain barrier and do not change the profile of tight junction proteins. It is also important to understand that if nanoparticles if they cross from the top bottom from the top chamber to the bottom chambers, which means that then we can understand the crossing ability of nanoparticles through the blood-brain barrier. So what we did again, we exposed for 4 hours, then we removed the non-internalized nanoparticles, we exposed to the light, then we waited for 24 hours, and then we quantified the nanoparticles which were present in the bottom chamber, and then we calculate the apparent permeability. So what we found that nanoparticles, transferrin conjugated nanoparticles and exposure of light it induces higher crossing of nanoparticles compared to the other conditions, as you can see over here. So we have more transportation of polydopamine nanoparticles conjugated with the transferrin peptide and exposure of light compared to just transferrin conjugated nanoparticles or polydopamine nanoparticles just exposed to the light. So overall, we found that receptor-mediated endocytosis and photothermal effect are the best condition to enhance the transcytosis of nanoparticles across the blood-brain barrier. So, now I will talk about the immunological response of nanoparticles. So we know that when we have infection or inflammation in our body secretes lots of pro-inflammatory cytokines to kill the bugs or bacteria or virus. So what happens when we have high amount of pro-inflammatory cytokines, like for example TNF alpha? They basically they facilitate the expression of PGAP. Okay, this is the particular proteins in the blood-brain barrier, and when they high expression of PGAP proteins, they make the blood-brain barrier very stiff, and so the molecules do not cross from the blood to the brain. Okay, in normal conditions, molecules can cross through the blood-brain barrier. In another case, in last few years, there is a high interest to do the immune modulation using photothermal therapy approach to treat cancer. So basically, we can inject nanoparticles in the tumor region, and when we expose to the near infrared light, the photothermal converging nanoparticles, they emit the thermal energy, right? And so they promote the switching of macrophage to pro-inflammatory macrophage, which means that pro-inflammatory macrophage, they can kill the tumor cells. Okay, so because they secrete lots of cytokines and they are like and so they kill the tumor cell. That is another approach for the treatment of cancer. In our work, what we thought that since we are using photothermal conversion nanoparticles, if we expose to the near infrared light, what might happen that light might promote the switching of macrophage to the pro-inflammatory macrophage in the blood, and so the pro-inflammatory macrophage will secrete pro-inflammatory cytokines that might damage the blood-brain barrier. And if there is damage in the blood-brain barrier, lots of cytotoxic molecules from the blood can reach to the brain, and it could be cytotoxic to the brain. So we study the parakine effect of our nanoparticles under the exposure of light on the integrity of blood-brain barrier. So what we did that we took the mouse macrophage cells, and then we incubate with the polydopamine nanoparticles for 4 hours, and then we expose to the near infrared light. Okay, and then we leave it for 24 hours so that the macrophage can secrete cytokines or chemokines in the media. Then we collect the media that we call conditioned media. Okay, and then we took this conditioned media and then we expose to the blood-brain barrier models. And then again we incubate for 24 hours, and then we study the permeability to the Lucifer yellow dye. We measure the tears, and we also did the immunofluorescence analysis. So in the condition, so what we did that we did first we did to understand what kind of cytokines are being released in the by the macrophage. We did the quantity PCR analysis, and what we found that mouse macrophage cells, they secrete when we expose to the polydopamine nanoparticles or polydopamine nanoparticles with the light, they do not secrete much pro-inflammatory cytokines like TNF alpha as compared to the positive control that we use lipopolysaccharide. You know, the lipopolysaccharide are found in the bacteria and they induce pro-inflammatory conditions. So the LPS generally secrete huge amount of pro-inflammatory cytokine. On the other hand, our nanoparticle, but with the light, it doesn't induce the secretion of pro-inflammatory cytokine. We also did not find, compared to LPS, we did not find higher secretion of IL-1 beta or IL-10. Okay, so that is good signature. And then we also did the quantification, internalization study, how much nanoparticles are being internalized by the mouse macrophage cells. And we found that out of 50 microgram per milliliter, approximately 15% of nanoparticles are being internalized by the macrophage. So from the gene analysis, we went to the protein analysis. So we did cytokine microarray analysis to understand expression of or the secretion of different kind of cytokines or the chemokines in the
Akhilesh,
conditions media.
can you please
Yeah.
conclude your presentation, because we are
Yes,
running out
just
of
in
time.
2 minutes. I will just finish in 2 minutes. So what we found that in conditioned media we have a higher secretion of TNF alpha and TNF alpha R1 and R2 and IL-6, and there are other cytokines that I don't want to explain it now. So then we did a parakine effect. Okay, so we measured the permeability and tear measurement, and as you can see that the conditioned media, which is we obtained from the polydopamine nanoparticle plus light, do not affect the permeability and tear compared to control. On the other hand, conditioned media from the LPS, they increase the permeability and they decrease the tear value. As you can see in the confocal microscope, this is the control. This is the blood-brain barrier model when we expose to polydopamine nanoparticle plus light, okay, in conditioned media. And this is the BBB when we expose to the conditioned media obtained from the LPS condition. As you can see over here, the BBB is completely damaged compared to the control or compared to the nanoparticles. Okay. So I will just go for the last slide. So we went to the animal model to see if nanoparticles can indeed cross to the brain. Okay, so we did intravenous administration of 1 milligram of nanoparticle, and immediately we exposed to the 5 minutes. And after 2 hours, we sacrifice the animals, we collect the organs, and we study the nanoparticle accumulations. So what we did there, we did the in vivo imaging analysis of the accumulated nanoparticles. Nanoparticles were conjugated with the fluorescent molecules. As you can see that lots of nanoparticles were accumulated in the different organs like liver, kidney, and lungs. But we also have some amount of nanoparticles accumulated in the brain. That is case for the transferrin conjugated nanoparticles with the light exposure. In case of without light exposure, there is very non-significant accumulation of nanoparticles in the brain compared to the when we expose to the light. And this is the image. As you can see that we have the accumulation of nanoparticle in the brain over here, and of course we have lots of accumulation in the liver and kidney. So I will not go. I think I don't have much time. Yes. But we just quickly we have also worked with the metallic nanoparticle like gold nanoparticles and gold nanorod to target the brain. So I will just go for in vivo data. And what we found, what we did that we functionalized the gold nanoparticles and gold nanorod with the transferrin peptide. We inject in the animals. In case of gold nanoparticle, we incubate for 2 hours, then we sacrifice the animal. In case of gold nanorod, we administer for